to this computer because I don't really
This is
trust
Daniel
cloud
Block in
recordings.
Wilmington, North Carolina.
Okay, so you're not missing. That's good.
Morning.
Good morning. All right, it is now 9 o'clock, and good morning. And I can't believe I'm awake. And Tomislav, it's let's see, it is probably
6 p.m.
6 p.m. there. Yes, or 1800. So this
Yep.
class ends pretty early in the morning for you, and I'm sorry about that. Um,
Don't worry, I have plenty of coffee
yeah, okay, yeah,
and
so
I'm
do I.
ready.
So, good morning. My name is Scott. My call sign is N7JI. That will make more sense as we go. I never know how many people are going to show up to these classes. And honestly, it doesn't matter because I'm going to teach it anyway because I enjoy doing that. Um, I hope everybody gets something out of this. For some of you, this is a repeat. For some of you, this is a refresher. For some of you, this is the first time you've ever gotten involved in anything like this, and it might be completely confusing. So, for those of you for whom this is a refresher or a a recap or you're just like you feel like a retread and you gotta send the tire in and get those treads cut again. Uh, you've probably heard a lot of this before, and just keep in mind that there are some people in this class for whom, and I know this sounds weird, but for whom high school mathematics was 50 plus years ago and haven't really thought about what trigonometry is because they haven't had to in a very long time. Um, every so often, I have one of these classes. Actually, virtually every class has at least a few people in it for whom getting in this class and getting a ham license is the completion of a 50 plus year old dream that they had when they were a kid. Like, I almost did it when I was in high school and I just didn't. But now I'm retired, so now I'm doing it finally. So if you are in that boat, don't feel weird about it. Don't feel bad about it. Congratulations for doing it. Um, you are not alone. If you're on the other end of the spectrum and you haven't taken high school mathematics yet because you're young, this will give you a nice head start into some of the high school mathematics that you're going to do. And you will get something out of it. You'll enjoy it, I hope. I try to teach this class without any really high level math. Again, we're going to do some trig, we're going to do some logarithms because you can't really explain a lot of this stuff without trigonometry and logarithms. But don't let it kill you. When it actually comes time to the exam, if you feel like there's an area that you're not strong on, has anybody started studying for an exam yet? Started taking practice tests to see what it's really like? So,
Yeah, I did.
okay, so what you'll find is that when you're
I have
going
on ham study.
excellent. So what you'll find is that as you go through the exam, you basically have this thing called the question pool, which is for a 35 question exam. The question pool is 450 questions long. Of those 450 questions, only 35 get asked. And you never know which one it's going to be, but you do know that from the question pool, which is broken up into lots and lots of little pieces, you typically will only get one or two questions out of any particular section of the question pool. Which means that if there's an area that you think, oh, I'm just not very strong in this area, well, that's okay because the whole exam is not going to contain every question from that area. It's going to be one question from a particular area. So I guess what I'm saying with all that is get studying, get practicing, practice. And when you get to the point where, I still continue failing questions in this area, don't worry too much about it. You know, the the process of learning that you're starting right now is really the beginning, not the end. The end goal of this class is not to get you a ham license. The end goal of this class is to get you licensed so that you can go further. Because having a license does you very little other than the fact that you can get on the air. What you really want to do is get to the point where you can get on the air where you can start building things, where you can start experiencing and practicing and knowing people from being on the air, because that's where you build your community, that's where you come up with more ideas, that's where you start to really experiment with things and start to understand the world that is amateur radio. And I know that sounds a little weird right now, but you will see that it's actually not. For those of you who are licensed, you know what I mean. And do we have any questions before we get started? This is an excellent time to ask because you're not the only one thinking them.
Hello, Scott. I got a question.
Take it away.
This is not the first time, so I take the class with you. So I want to say thank you, and always. But I kind of always wondered. You started the class at different. When I read the book, that you send us,
Hmm.
the book starts in a different
Sure does.
time, and you start in a different way. So I kind of myself, and I know we are all different, but I'm kind of in the army, and we're kind of used with kind of a structure. Like, okay, we start A always with A, B, C, D, and et
Hmm.
cetera, et cetera. So, and I know you have your style, and I know you have your reasons. So, and I know you said it once, Brian, but can you repeat it once? Why you started the class?
Yes.
Where you started?
Okay.
Thank you. Thank you.
So, okay, what I try to do is start in a manner that, okay, so let me ask this question. What is amateur radio? I mean, what is amateur radio? Somebody try to give me an answer.
Well, I mean, first thing that comes to my mind is, well, this is amateur, not for professionals. It's for, everyday folks like us.
Right? Okay. Keep going.
Well, it's supposed to be fun. Um,
Yeah.
and uh, well, I mean, I'm gonna stop there.
No, keep going. I like where this is going. You're on a
Well,
roll.
okay. So I was gonna say, supposed to be fun. I mean, it's supposed to connect, everyday folks all around the, community and the world, and but it's supposed to make sense for everyday people. And maybe, one of the reasons that uh, you choose you have your own style or choose a different direction to expand the classes to address it to more people, to the general common audience.
Yeah.
That's my thought. But
Okay. Anyone else?
Yeah,
There's
me.
no wrong answer.
Disaster response. I'm pretty sure when a disaster happens, the Red Cross shows up, but also sometimes ham radio operators get involved, sometimes even remotely to like relay messages,
Yep.
if that's right.
Yep.
It
Other
was a way for people to be able to talk to people all over the world.
and still
It,
is. Yeah. Other ideas.
and especially
Maybe,
during the
maybe,
war and stuff, it was a way to communicate for people to be able to
Well, actually,
find
during
out
the
what was
wars,
going on.
during war, we typically would get shut down.
Really?
Yeah,
World
as
War
a
II?
security risk. And I'm not good at raising hands. Like I said, if you just have something to say, go for it.
if I
Don't,
may put one, let's
yes.
say in our class, when we took it for our licenses here, we defined it as a non-commercial, non-professional use of radio waves of
Yeah.
some sort.
Okay, so everybody you see right here, can everyone see on the screen? This is a good first chance to make sure that your ability to see shared screens works. Can everybody see? All good?
Yep.
Okay. Basis and purpose. Well, here we go. Part 97 is the FCC rules because we're taking a United States license license class. The FCC is in charge of this. So these are the reasons that we are allowed to exist. When you think about it, we are non-commercial, which means we don't make any money. We can't make any money. We are a voluntary service. This is actually a licensed service. You know, I mean, yeah, we use it as a hobby, but it's a licensed service. And which means that we have to follow the same rules that TV stations follow, that commercial radio stations follow. So, Looks like apparently somebody made a scratch across my screen. Okay, notice value of the amateur service to the public as a voluntary non-commercial communication service, particularly with respect to providing emergency communications. Who said the Red Cross?
Oh, that was me.
Thumbs up, you got one of them. Okay, continuation and extension of the amateur's proven ability to contribute to the advancement of the radio art. A lot of different technologies, like single sideband and things like that we use throughout industry. A lot of digital communications have either been developed in the amateur radio service or have been applied from other areas and utilized in the amateur radio service. So people think radio is dead, right? Radio is boring, radio is dead. Who here has a radio? Who here is using a form of a radio right now?
Anybody who has a cell phone.
Yeah. Anyone on Wi-Fi? Is there anyone using Wi-Fi?
Just a couple.
I am right now.
Yeah.
Yes, I am.
What is Wi-Fi?
Yes.
That's a certain
The radio
frequency radio
signal.
waves.
It's a 2.4 or 5.8 gigahertz radio signal at extremely high bandwidths. It's a digital signal that's being sent over radio frequencies. That's why there's an antenna. So all those technologies came about somehow. Radio is definitely not dead. And in fact, we rely on it a lot more than people even stop to think. All these things that we take for granted. Encouragement and improvement of the amateur service through rules which provide for advancing skills in the communication and technical phases of the art. Okay, so that means the FCC makes rules that allow us to do things, like allow us to get on the air and experiment with long-distance communications, or come up with rules that allow us to have a modified Wi-Fi router, and we can change the frequency and bump up the power a little bit and send communications using a microwave dish over a distance of 30 miles, essentially using Wi-Fi over a distance of 30 miles. We're not allowed to encrypt it, but we can certainly try it. And people do, and that's actually something called Arden, which connects from mountaintop to mountaintop and serves as a parallel kind of like radio-based internet backbone to cables and wires, which also feeds into emergency communications. Expansion of the existing reservoir within the radio service of trained operators, technicians, and electronics experts. So that comes down to the fact that we are allowed to build things. Not only are we allowed to build things, unlike virtually any other service, we are given carte blanche to build something and then put it on the air. So the question will then come up, well, okay, why do we need to take a license exam? Even for a technician exam, why is there an exam? Well, when you go and you buy a cell phone, this has been tested. I'm going to hold up my cell phone. This cell phone has been rigorously tested by somebody to show that it does not cause interference with anything else. I mean, it's a radio. If every cell phone truly interfered with airplanes' avionics, right? If that truly happened, nobody would ever be able to use their cell phone in any way on an airplane, ever, right? Well, clearly we can, right? Which means that this has to be rigorously tested by some agency in order to be approved for use. As an amateur radio operator, you can basically, if you want, build your own cellular telephone on the amateur frequencies. You could do that if you really wanted to. I mean, you could build a radio that operated on 3.3 gigahertz, and somebody else could do the same thing. You can't encrypt it, but you can certainly send pictures over it. You can send data over it. You can send text. You can do all kinds of things with it. Does anybody look at that and say, well, we have to certify this to make sure it doesn't violate FCC rules?
I have a question.
Well, wait, before you do that, does anybody actually go and certify the thing that you build?
No.
No, you do. Your license permits you to build stuff, and part of getting that license is understanding that what you are doing could cause interference with other services, which is why even with a technician class license, you have to take a rigorous exam because this is not an appliance operator's license. This is a license to build stuff, and this is a license. You may only ever want to grab a radio, a handheld radio, which has been tested by someone else, and use it to talk to somebody else, but your license permits you to do all kinds of things, which is why we have to take that license exam. Brody.
Yes, I was just wondering, like you said, our phones are certified by, an organization. Would you be talking about like Underwriters Laboratories or Canadian Standards Association?
It's that and the FCC. The FCC
Right,
has specifications for spectral purity.
right.
That would probably be either tested by some laboratory that understood the FCC rules and put their stamp on it. That could be UL. That could be a group that works with CE for Europe. I do some of that for work. I mean,
Yeah, yeah. I'm studying the National Electrical Code because I'm in school
yep,
for the electrical union, but I was just wondering.
yep, yeah. They all feed into it. And so, finally, continuation and extension of the amateur's unique ability to enhance international goodwill. So, we are non-political. We are apolitical. You can talk about politics on the air, but we try to stay away from politics, sex, and religion. Those are the three things we try to not talk about. Just because, they can be polarizing. And radio is kind of, we try to think of radio as amateur radio as a safe space where we can all get along from country to country, even within our own countries. If
Just
we
like
have,
a wise person at Thanksgiving dinner.
that's right. Exactly. All right. So that is what amateur radio is. That's the broad picture of what amateur radio is. Essentially, amateur radio encompasses lots of other things, but it is not specifically all of those things. It is kind of, if you want to think of it, it is sort of like a Swiss Army knife of communications. One interesting thing about it is that just because you have, just because you have an amateur license does not mean that you exclusively have knowledge in the amateur license, in the amateur radio area. Somebody comes along and they say, well, we seem to be having interference and it's on this wireless microphone system. Well, you have some experience with wireless microphones. You have some experience now with electronics and RF, independent of the frequency being used, which means that the knowledge that you have gained is then applicable to lots and lots and lots of different things in the world around you. And I don't know if it's still true, but at least in the United States, at one point, roughly 90%, if I'm not mistaken, of radio station and TV station engineers were also ham radio operators. And where do you think most of them got their start? In ham radio. It sort of directed them into that, and it was an easy application of what they had already learned. Stephen, I see your hand up, very politely.
Hey Scott, I just had a quick question, but thank you for having us, by the way. I really appreciate this.
Yeah,
This
try
feedback.
to get a little closer to the microphone. You're a little muffled.
Can you?
Go ahead. Oh, now it's not working.
Mm-mm.
Uh, nope, well, we can't hear you.
All right, give me.
All right, well, I'm going to put your
All
hand
right,
down
can,
and
can,
pop it
can you hear
back
me
up.
now?
No, it's still kind of muffled. Put your hand back up when you want to try when you're ready to try again. All right, so are there any other questions before we get started? I'm sure people are going to ask about the actual process of taking an exam. No, there is no exam associated with this class because it is right after Christmas. Occasionally, we will try to do a class where we have a volunteer examiner corps that does a captive exam that's a part of the class. Except that in this case, it's so close to the holidays that we didn't want to put anyone under any stress. There are, and I included this in the email that I sent, there are lots and lots and lots and lots and lots of opportunities online to take exams. There are groups that are giving many exams today, many exams tomorrow. If you're totally ready, if you've been practicing and you're scoring 85% or higher every single time, you are ready to take a test. And you will more than likely pass it. You need to get 74%
I'm not too
to
far
pass.
off. I'm at 71%.
You still got some work to do. You need to be at
I know that's
85%
right.
every time. Every single time, 85%. That guarantees you to pass. The other thing is that when we are in the process of doing this, you will find that there are 3 exams. There's the technician, the general, and the amateur extra. No, I don't know why
Hmm.
it's called amateur extra. But what you'll find is that radio is radio. The process of getting your technician license means understanding electromagnetics to a certain degree, understanding the rules and regulations of getting licensed, and being able to operate legally. The general exam is a little more technical, but it covers a lot of those same basic rules, which means that if you are close to passing the technician exam already, or you know you're ready to take it, you should definitely take a look at the general exam because there's at least a 50% overlap in the material. It's just basically learning new bands, new frequencies, new power limits, new data rates, and things like that that are an overlay. And it doesn't cost any extra if you pass the technician exam to go ahead and take the general. So you might as well study for it and kill 2 birds with 1 stone and get to the point where
Hear
you're
that?
actually having a lot of fun on the air. Because having a general license is a lot more fun than having just a technician license. Steven, I saw your hand up.
Yeah, I was just checking. Could you hear me better now? Or
Yes, go ahead. Ask away.
I'm not sure. I think you kind of answered my question, but what I wanted to know is, let's say someone who knows nothing about radio, right? You're starting from scratch. What are the levels that you can get at through going through ham radio? And I wanted you to explain the different types of licenses you could get. What would be like get from ham radio?
Okay. So there are 3 license classes in the United States. In the other countries, the rules are different. In the United States, you have 3 license classes: technician, general, and extra. And one of the things that comes about is that there is something called something that is called incentive licensing in the United States. Incentive licensing basically means that there is incentive to do something more. The incentive is that as you progress, you will have more privileges. When you have more privileges, you can do more things. So,
Right.
for instance, I'm going to pop this up on the screen right now. If I can find I lost my Zoom. There we go. Okay, can everybody see this? Everyone see this
Yes.
band plan? Okay, so notice down here you have novice and technician voice, novice and technician CW, CW, gritty, data, general voice, advanced voice, and extra voice. No, you can't get an advanced class license anymore. You can't get a novice class license anymore, but they still exist. They haven't been grandfathered into anything else. But what's significant to note is that a technician can operate on any frequency, on any band, 50 megahertz and up in frequency. We're going to cover frequency in about 3 minutes, so this will all make more sense. But basically, these frequency bands right here, 6 meters and up, or 50 megahertz and up, as a technician, you have full access to those bands. However, when you look at long distance communications, medium frequency and high frequency, also known as shortwave, notice that these novice and technician areas, which are in the hatched areas, the blue and green hatch, you are very limited in what you can do on HF. These frequencies up here are largely line of sight and within a couple of 100 miles at most, maybe 1,000 or 2,000 if conditions are right. These are the frequencies down here that allow you to do worldwide communications on some bands at pretty much any time during the day into different areas. These are the ones that allow you to do ionospheric propagation covering thousands and thousands of miles. This, to me, is where all the fun happens. When you get your general license, you have at least some access to every single one of these bands down here. When you get an extra, you have unfettered access to everything. So the other thing is when you travel around the world, if you have an extra class license in any other country, if they give you a license to operate temporarily, translates to the highest class license in that country. So you have full privileges all over the world. You can also give any class of license exam, which is a great way to give back. So, okay. Everybody ready to get started? Other questions before we go? Feel free to ask. This is your last. No, it's not your last chance. Okay. No more questions. All right. Here we go. We're going to share a whiteboard. And the first thing I'm going to do is erase this whiteboard, and I'm going to really, really try to draw well during this class. Here we go. Okay, can everybody name that shape? That's your first exam. That's your first test. What is that shape?
Circle.
A circle, yes, okay. How many degrees are in a circle?
360.
360. Where
360.
is the 0 degree mark?
Very top.
Nope.
Would it be the center?
Nope.
Nowhere and everywhere.
Nope.
Everywhere.
Nope. By definition.
On the circle rim on the right axis.
On the right axis.
horizontal
By
axis.
definition, this is the 0 degree mark. Right? This is on the x-axis.
Okay.
On the y-axis, this is we wrap our angle going this way. So by definition, 0 degrees is on the positive x-axis. This is the negative, this is the positive y, and this is the negative y. Okay, so this is your basic definition of a circle. Okay, so now we're going to start traveling around the circle, obviously in the counterclockwise direction because we're following the arrow. What is our angle when we reach that first point of interest? That would be 90 degrees,
90.
which is on the positive y-axis. Okay, how about when we get all the way over to the left-hand side? What is our angle?
180.
180 degrees. Okay, excellent. How about when we get down to the bottom?
270.
270, yes, okay. And then, how about when we get back to where we started?
360.
360, but it also has another name. What's that other name?
0.
0, yes, okay. So we consider that we continually wrap around the circle. And so could I call that point also 720? Or negative 360? Or negative 720?
Yes.
Absolutely.
That one point has a ton of different names, right? But for the sake of argument, what we're going to do is say that we're just back to 0. But really what that means is that this circle doesn't ever end, right? The 360 is the same as 0, is the same as negative 360, just depends on which way we started. So the next thing we can do with this is say, all right, let's take a look at this circle, and we're going to do something interesting with it. We're going to say that we are riding right here on the rim of the circle. This is a merry-go-round. And this merry-go-round goes around in circles. And as we're on this merry-go-round has a radius of unit 1. That's our radius, which is the distance from the center of the circle. So at any point on the circle, how far away from the center are we?
1.
One.
We're exactly 1 unit. This is known as the unit circle. And in fact, that is the definition of the unit circle. The collection of all points that are a distance 1 away from a center point. That's the definition of a unit circle. So, what is the only difference between any of these purple points?
Where they are on the circle?
Where they are on the circle, how far around they are. They're all 1 unit away from the middle point, but they are at different points on the circle based on the angle that has been subtended by moving around. Okay, so basically now what we have is a collection of points, all 1 unit away from the center of the circle, but at a bunch of different angles. So as we now redraw this circle, because I'm going to start with a clean circle. Hopefully it's a decent circle. As we do that and we go around the circle in this direction, and we have the x-axis and the y-axis. Notice we have a plus and a minus. We are going to take a measurement of how far along the x-axis we are and how far along the y-axis we are at any given point. So we're going to start with this point over here. And we know that this is a unit circle, so it has a radius of 1. So at 0 degrees, how far are we along the x-axis? What is our distance? Yep.
1.
And what's our distance from the y-axis? Along
0.
the y-axis, it would be 0. So I could draw a graph. I'm going to draw actually 2 graphs. We're going to look at the x and we're going to look at the y. At this starting point, which is 0 degrees, we are 1 unit above on the x, and we are right on the ground for y. How about when we get up to, let's say, here? We're going to be somewhat less. This is 45 degrees. I'm going to mark these off. So this is our 45-degree mark. And we're going to be a little bit less, but now our y position is going to be changing. We're going to be increasing. Everyone agree with that?
Yes.
Okay, how about when we get up to 90 degrees at the top?
X is 0, Y is 1.
X is 0, and y is up to 1. Okay. Now, how about if we continue across here? We drop down here, and we're back down here, because we've actually gone negative with respect to the x. Our y is still above the ground. And then how about when we're way over here at 180 degrees?
X would be -1.
X is -1, and y
Is 0.
is 0. Well, we continue this along, and we continue just making the dots, and we go like this, and we give one up here, and then one up here, all the way at the end, and then we have another one here, and down here, and there, and guess what we end up drawing?
Sine curve.
A sine wave, yes. This is a very important looking picture. And why is that so important? Where do we find sine waves?
And frequency.
Oh, we're not even in frequency yet. Where do we find sine waves?
Everywhere.
Everywhere. How about the length of a day during the seasons? That is defined by a sine wave, because the Earth goes around and it tilts and it spins. It's a round thing. Things that are round, when you start looking at the map that they make, it ends up being a sine wave. So by definition, actually, this is actually known as a sine wave, and this is known as a cosine wave.
So
Now,
I'm a little bit confused
mhm.
on when you made the dot on the circle that was
Oops. Yep,
45.
hold on, I made a mistake there. I need to fix that. Okay, keep going. There we go. That's a cosine wave.
Wouldn't I still be at Y0
Up here?
and
No. You've now gone up with respect to the ground. This is the ground.
okay. All right.
So you now have this thing's called a cosine wave and a sine wave. And does either of these have an actual beginning or an end?
No.
It does not. So I could actually draw these extending forever in both directions. So what do you notice is very similar about these things? They are the exact same shape, aren't they?
Just different position.
Just different
Yeah.
positions. The position, because it's an angle, is known as the phase. These are shifted in phase by 90 degrees from each other, which actually makes sense when you start to look at how they're made. So that's known as the phase of the angle. Okay, so now we've got a cosine wave and a sine wave. For simplicity's sake, we usually just consider things to be sine waves because a cosine wave is just a phase shifted version of a sine wave. So we call everything sine waves, and now what we can do is we can take our sine wave and we can start looking at what makes it interesting. And so Artan, to answer your question, this is the reason that I do things in this particular order, because I feel that an understanding of the mathematics is very important in understanding the everything else that's coming next. So we look at a sine wave. What made that sine wave?
Circle.
Yeah, we were going around in a circle, right? The fact that we were on a circle turning is what created that sine wave. We were measuring something. And in particular, because it's a sine wave, we are actually looking at the vertical displacement in the y direction. So here's the plus and the minus, and we start over here at 0. We map out that sine wave. And when in fact we can look at it, here's 0 degrees, here's 90, here's 180, here's 270, and here's 360, which has another name,
0.
which would be 0. Okay, so we could start all over again. So as we go around the circle, we map out this sine wave. So what are some things that we can change about this merry-go-round that we're sitting on?
Size of the circle.
We could change the size. Yeah, we could make it a bigger merry-go-round. If that were true and we are mapping how high and low we are going, the way that this was set up with the unit circle, we would go from 1 to -1. What if we made the merry-go-round twice as big?
You'd have twice the size of the wavelength.
Well,
2 to minus
Or
2.
not the wavelength, but
it would be the amplitude would go from 2 to -2. How about if we made it 3? What if we made the radius 3?
Bigger yet.
It would go to 3. What if we made the air? What if we made it from? What if we shrunk it down to a half?
0.5 to minus 0.5?
Is it still a sine wave?
Yes.
Yes.
Okay. Have we changed anything fundamentally about how fast it's happening?
No.
We have not.
No.
Okay. So clearly, what we could do is, let's say that we managed to somehow relate this to time, so that we went around the circle one time in 1 second. If we were to do that, let me redraw the circle again. I'm going to move the circle because now it's in the way. If we were to redraw this circle so that it's over here, And we started and we went all the way around 360 degrees, and it took 1 second. How long would it take for us to make that graph that we see?
1 second.
It would take exactly 1 second. That's right. Okay, so this would be 1 second. Okay, so the unit of one cycle, this is a full cycle. 1 cycle per second has a name.
Frequency.
Nope.
Hertz.
That
One
is
hertz.
Wavelength.
that is a hertz. That is
Wow.
a measure of the frequency. How many times? Frequency is just how many somethings per second. I can clap twice in a second. My frequency is 2 claps per second. Specifically, a hertz is a cycle per second. That is what a hertz is.
Okay.
Now, we could also say that the frequency is 2 hertz, but a hertz, by definition, is a cycle per second. So, what if we were to say, well, our merry-go-round is making me nauseous going at that speed. I want to slow it down to 2 seconds. How long would it take to make that picture?
2 seconds.
2 seconds. Okay, so if it takes 2 seconds to make that picture, how many cycles would we make every second?
Half.
Half.
That's right. So our frequency would then be 1/2 of a cycle per second, which would be 1/2 of a hertz. Okay, now if I was a daredevil, and let's say that I was training to be an astronaut at NASA, and I wanted somebody to put me in a centrifuge and spin me up really fast so I could experience what it felt like to black out at high G's. And this went around, let's say 50 times per second, so that I intentionally passed out so I could experience a ridiculous number of G's. How many maps would that make every second?
50.
50.
Okay, so that would make 50 of those per second. That's a cycle. A cycle per second is a hertz, so what would my frequency be?
50 hertz.
That would be 50 hertz. So this basically now relates a frequency and a wavelength, because we're going to take a look at this particular wave. Notice we haven't done anything about distance yet, right? We've just done frequency and time. But now what we're going to do is we're going to take this circle, and we're going to, what happens if you take a circle and you're looking at, let's say this is a bicycle wheel. Here's all the spokes. Don't try riding it, it'll probably collapse. You take this bicycle wheel and you turn it sideways. What will it look like?
Piece of paper.
It'll look like that. Right? A really narrow bicycle wheel will look like that. Agreed?
Yes.
Yes.
Okay, so if I was on this merry-go-round or bicycle wheel, which I'm going to erase, I'm just going to represent it with a plain old circle. And it still has 0 degrees, and I'm spinning around on the circle like this. And I rotated it so that it was looking at it sideways. When I was at 0 degrees, where would the dot that represents me be?
In the middle?
In the middle, right there. Where would 90 degrees be?
Top.
At the
At
top?
the top. Where would 180 degrees be?
Bottom.
No.
Bottom.
No, it would be right there in the
No,
middle
it'd be
again.
right to the middle.
Sorry.
How about at the
Actually,
bottom?
yeah.
How about at the bottom?
270.
270. And how about at 360?
Back to 0.
Back to 0.
The middle again.
So I would be going like this: up, down, up, down, up, down, up, down, up, down. You would see nothing of any real interest except for a dot moving up and down periodically. Right?
At
So-
the eighth, what time?
basically what you would see by looking at that is you would see this flashlight that I'm holding up on my phone. You would see this. And its highest rate of change would be right in the middle when it's sweeping through. This is what it would look like. Okay, so now, can everybody see that light moving up and down?
Yep.
What if I were to take this and instead move it while I'm going up and down and add another portion of motion moving side to side? What do you now see? What shape does that make?
Another sine curve.
Another sine wave. Yeah, okay.
Yep.
Ooh, okay, so we just modified it a little bit. We added another axis of motion. And what we now did is we have this picture now being stretched out by how fast this bicycle wheel is moving side to side. So now this moving just up and down is stretched out to look like this. For a given frequency of the original circle going around, if I move the thing faster to the side, it will look like this. If I move it slower, it will look like this.
Tighter.
What is this? Speed. We can also say velocity because it has a direction. What is that?
Be a light?
Well, no, we haven't said that yet. What is that? How do we measure speed?
In seconds, so it'd be cycles per second.
No. If I'm walking, how fast am I walking?
Distance?
Distance per unit
Of time.
of time. Meters, kilograms, and seconds in the metric system, the MKS units, we use meters per second. Okay, now. Well, what we now have is a velocity or a speed that's measured in meters per second. What do we have our thing going around the circle measured in?
Hertz?
Yes, and what is the
Cycles
unit
per
of hertz?
second.
That's right, it's cycles per second. So we have hertz over here in cycles. Okay, so we are going to make a leap. And the reason we can make a leap is because math is awesome.
Yes.
Excuse me, what did you say the unit of measure was on the section you just erased there? Did you say that was I missed that.
Which down
Meters
here?
per second.
We haven't done that yet.
Okay, I'm sorry.
Yeah, we haven't done that yet. What I said is math allows us to do what we want because math is awesome. So long as we follow the rules, we can do anything we want in math. So I am going to arbitrarily say, I'm going to look at these two things that we have, which are speed and frequency. So here's our frequency, and here's our speed. And you notice something common about both of them. What is the one connecting rod between the two?
Units per second.
Which
Second.
one? That's right, per second. So I have cycles per second, and I also have meters per second. Okay. Well, if I divide one by the other, the per seconds would cancel out.
Mm-hmm.
So I can creatively say, because math is awesome and I can do that, I can choose to do what I want with math. I want to take, just arbitrarily, we will go with our speed, and we're going to divide it by our frequency and see what we get. And we're going to call this unit the big letter, we'll just use the big letter N, because I can pick any letter I want. Okay, so what are the units of speed?
Meters.
Meters per second.
Meters per second. What are the units of frequency?
Cycles
Cycles
per
per second.
The cycles per second and the meters per second both have time, and it's both per second. So what we can do is we can take these and we can cancel those out.
And
now we
cycle.
have meters per cycle. Okay. Well, this arbitrary unit n that I came up with now has these units of meters per cycle. In other words, I can now say that I have this wave, which is being made by something with a frequency, moving at a velocity v, making a sine wave, which has a what? Would you say that's one cycle?
Yes.
Yep.
Now it has a what? That's a length. It's actually carving out a length in space. Well, this thing, if you think about the ocean, this is a wave. This is now known as a wavelength.
Oh.
And instead of the letter n, we actually used the Greek letter lambda for that.
Thank God.
And now what we have is something with a natural frequency and something that is moving sideways at a speed, and we have a wavelength of the wave. R10, this is why I do this first, because this is the fundamental basis of everything we're doing. Okay.
Thank you, Scott.
Yep. See, that's why we do it. That's why I do it this way. Others may not like doing it this way. I like doing it this way. Okay, so now we have this thing, which is a circle, going around at a frequency, moving, turned on its side, and then moving at a velocity. I divided, this is in cycles per second, and this is in meters per second. I divided velocity, divided by frequency, and I got meters per cycle, and I got this Greek letter lambda, which gives me meters per cycle, which is also known as a wavelength. So we are now going to play with this because we can. So we are going to take, okay, are there any musicians in the house?
Yes.
What is a concert A? What frequency?
440.
440. It's amazing that everybody knows that, including myself. 440 what? Hertz. Okay. 432 is a low concert A. You can tune to 432, but by definition concert A is 440. Okay. So 440 hertz. Okay. What kind of wave is that we listen to?
Pressure?
Yes. Which we hear as what?
Sound.
That's a sound wave. That is a pressure wave, also known as a transverse wave. And okay, so we basically hear these rarefactions in air. It pushes against our eardrum 440 times per second, and we get the sensation of hearing an A. Okay, so now the question is, what is the actual wavelength? Well, how would we figure that out? How would we calculate that? Somebody take me through it. We're missing something.
Speed of sound.
Speed of sound, yes. Speed of sound is about 330 meters per second at sea level. It changes with density. It changes in water. Okay, so if we know that we are at 330 meters per second and our frequency is 440 hertz, which is cycles per second, we
get
can
2
then
carats.
divide them, and what do we get?
Wavelength.
Right? What's our velocity?
330
330.
percent.
Okay, 330 meters per second divided by 440 cycles per second. Whoops. Is 0.75 meters. That's a physical wave. At sea level, a concert A covers a distance of 0.75 meters. Which means if we were to actually look at it and do this, each wave crest would be 0.75 meters from the next one as it's traveling through the air. Okay, so this actually has a really profound impact as well. Anyone play a wind instrument?
Yes.
Okay, what do you play?
Recorder.
Okay, so I play the flute. Anyone else?
I used to play the flute. Now I play Irish flute and whistle.
Okay, so let us say that you are playing your flute and you are doing a tune-up with the orchestra and you notice that you are flat. What does flat mean? What does it mean if you're flat?
That I'm not up to 0.75 meters.
No. What does it mean if you're flat? It means your pitch is too what?
Low.
Too low. That's right. If your pitch is too low, your frequency is too low. How do you tune the instrument?
By making my pitch higher.
How do you make your pitch higher?
Reduce the distance.
What do you do with with the head of the flute?
You shorten the reed.
You shorten it. That's right. If you're sharp, what does it mean if you are sharp?
Too high.
You're too high. Your frequency is too high. How do you tune your instrument, your wind instrument?
Lengthen the reed.
You pull the headpiece out of the body of the flute and you make the column longer. Okay, this is actually important too because a flute is a resonant cavity. The length of the cavity is closed on one end, it's open on the other. You blow across it just like a soda bottle. When you do that, the length of the cavity, depending on where you push the keys down, determines how long that cavity is.
Right.
The length of the cavity means that it is able to sustain a particular frequency and wavelength within the cavity. The longer the cavity, the lower the frequency. The shorter the cavity, the higher the frequency.
It takes so much wind to get those low D flutes going.
Well, that's true too, especially if you play like a bass flute or a baritone flute.
Right.
But the key is that the longer the body of the instrument, the lower the note will be. The same thing with like a pipe organ. Okay? This has an analog to radio, which we are not going to get into exactly yet, but here we go. So now we are going to say, here's our circle again. Here's our 0 degree marker. We're going to go around the circle like this, round and round and round. We're going to turn it on its side again, and now we're going to move it toward the side at a velocity. So we have a frequency and a velocity. And now we are going to look at a different kind of wave, which is not a sound wave. We are going to look at a different sort of wave called an electromagnetic wave. Here we go. Okay, so these are electromagnetic waves. And what do you notice about these electromagnetic waves? What's all the way here at the right-hand side?
Light.
And in particular, the colors of light.
Infrared.
And here's red, orange, yellow, blue, red, orange, yellow, green, blue, indigo, violet. Roy G. Biv. Notice we have our wavelengths down here. We have 1 micron, and we have 100 nanometers. We also have our frequencies up here. And so this tiny little band is Roy G. Biv. Longer wavelength than red, we get into something called infrared. Shorter wavelength than red, we get into something called UV, which is
Ultraviolet.
Ultraviolet.
and then beyond that, we get into
X-rays.
X-rays, and then we get into gamma rays and cosmic rays and all kinds of stuff. So now let's look at infrared. Here's our wavelength, 1 micron, 10 microns, 100 microns, 1 millimeter. At a millimeter, well, you can actually picture what a millimeter is. I mean, you can stick your fingers fairly close together and put them a millimeter apart and look and see what that is. It's 25.4 millimeters per inch. Right there is the breakpoint between what we consider long infrared waves and microwaves at about 1 millimeter, which translates to 300 gigahertz, which is 300 billion hertz. As we keep going, we see that microwaves then give way to UHF, which is ultra high frequency, VHF, which is very high frequency, HF, which is high frequency, and then there's medium and low and extra low. All that stuff, including microwaves, is known as radio. Those are all part of radio. And in fact, those are all part of what we know as the electromagnetic spectrum. And we're going to get into why it's called the electromagnetic spectrum. But the key about the electromagnetic spectrum is that all of these different waves, all of these different forms of electromagnetic radiation are all the same. They are all carried by a particle called a
photon.
They have different wavelengths,
Right.
they have different frequencies, and they also have different energies. But there is fundamentally no difference between a red photon, an X-ray photon, or a radio photon, except that they have different wavelengths, different frequencies, and different energies. And really what it comes down to is that they have different energies, and that defines the wavelength and the frequency. They are all the same. So why is it that we see red as red?
The frequency wavelength. No, the wavelength.
Both. How does that translate to red?
You have rods and cones in the back of your eye.
That's right. Your eyes have come to acknowledge that a certain range of frequencies looks red. How about blue?
The higher wavelength.
Higher frequency, lower wavelength, shows up as blue. Our brains interpret it as blue. All those colors are just our eyes' and brain's way of representing different colors, different wavelengths as colors. So, is it possible that is it possible for us to see ultraviolet?
Yeah.
Yes.
Not directly.
No,
right? But you could build a detector that could see ultraviolet. Are there animals that see ultraviolet?
Yes.
I believe birds and bees see ultraviolet. There are animals that can pick up infrared. Are there any animals that can pick up radio waves? Unclear,
Yeah,
right?
bats.
Unclear. Well, no, bats are echolocation by sound. Low frequencies, but I guess it's possible that they could pick up radio waves, but we certainly cannot. So, in order to be able to pick up radio waves, what do we have to do?
You have to have some sort of a receiver.
You have to have some way to look at it. In order to be able to pick up infrared, let's say you have a, let's say, who was studying for the electrician's license?
What?
Who was studying for their electrician's license?
Me.
Okay, what's a FLIR? Have you covered the FLIR yet?
FLIR?
Yeah.
That's infrared, isn't it?
What do you use it for? I use a FLIR at work sometimes.
Thermal imaging?
Yep, you use that for thermal imaging, looking for stuff, right? Looking for stuff that's hot when it shouldn't be. So the reason that we use a FLIR is because, with the exception of touching something with our bare hands, if it's carrying high voltage, we don't want to do that. We can look and see with this camera, which is light sensitive at different frequencies, we can develop a picture of hotspots. So we have to develop some kind of receiver to pick up what is being emitted at frequencies that we can't detect. Radio waves are the exact same way. We have to develop a receiver that then takes those waves and translates them into something that we can figure out and can work with. Any questions before we go on?
I have just a kind of unrelated question. Do you know where the term radio comes from?
Yeah, I do not. I mean, you'd have to look back in the annals of what Maxwell and those guys did.
Yeah.
Probably radio, something to do with radiation, radiating.
Yeah, that makes sense.
Yeah. Any other questions?
Well, no.
Questions are good. You can't be the only one thinking it. No? Okay.
I was wondering about the thermal imaging for, say a police chase or something along those lines.
Yep.
So it's using that technology, but how does it see it so far away from a helicopter, for instance?
I mean, it's if there's a wavelength and if there's a wavelength being emitted and there's nothing in the way to stop it, if there's energy being emitted and there's nothing in the way to stop it, it's going to get there.
Yeah.
So we're getting into electromagnetic radiation right now, and I'm going to share a whiteboard. Okay, so let us take a look at this wave being generated by a circle going around and moving up and down when you turn it sideways. This has a frequency, and it also has a wavelength, but how fast is it now moving? How fast do electromagnetic waves travel, considering that light waves are a form of electromagnetic waves?
Speed of light.
The speed of light, which is known as the letter C, which is approximately 3 times 10 to the 8th meters per second, or 300 million meters per second, which is pretty darn fast. Now, that is true in vacuum. It is very close to being true in the air as well. It is very different when you get into other media like water or plastic or glass or concrete or any other medium. But in vacuum, which is also applicable to our air, this is approximately the value of C. That's our velocity. So we can now rewrite where we had lambda is equal to V over F. We can move these things around, and we can write F equals C over lambda. Or C is equal to F times lambda, where this is the frequency in hertz, and this is the wavelength in meters. This right here is the formula for our speed of light is equal to the frequency times the wavelength. So I could write this like this and say this is 300 million. Does that ever change in vacuum? Thanks to Einstein, what do we know about the speed of light?
Constant?
It's constant, yes. Okay, so I could now say that for any given frequency or any given wavelength, could I figure out the other one?
Yes.
I could, yes, because the speed of light is constant. Thank you, Einstein. Okay, so I could say that for, let's say I had a frequency of 100 hertz. I could say C is equal to 300 million is equal to 100 times wavelength. Okay, so how do I get rid of the 100 on both sides? Divide both sides by 100, replace this with a 3, and replace this with a 1, and I get wavelength is equal to 3 million meters. That is a really long wavelength, isn't it? It's 3 million meters long. It's 3,000 kilometers, or about the distance from where I am in Oregon to, let's say, Chicago. That is one wave. And why is it so long? Because the speed of light is?
Constant.
No, because it's really, really big. Right? Light moves really, really fast, which means that even a modest frequency of 100 hertz is going to carve out a wave that is 3,000 kilometers long. That is a really long wave. So, is it practical to pick that particular wavelength to send information if you're a normal human being? And you try to build something to do that, it is not practical to do that. So what we typically do then is we pick frequencies that are much, 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 much higher. We start with C is equal to 300 million again, meters per second. And we have C is equal to F times lambda. And now we're going to pick a frequency of 1 million hertz. Okay, so we can redraw all this. We have 300 million is equal to 1 million times lambda. Well, what's 300 million divided by a million, everybody?
300.
Lambda is equal to 300 meters. Okay, how long is 300 meters? It's about 1,000 feet. Well, okay. That's still pretty big, right? But it's a lot smaller than it was. But what do you notice now in order to get to things that are practical? What do we have to do for our frequencies?
Increase it.
We have to really pick some really big frequencies. Okay. So what do you notice also about these equations? What do we have a lot of?
A lot of zeros.
A lot of zeros, yeah. Zeros are great, but zeros can also be replaced with things. So we have to get to something called powers of 10. So what's 10 to the 0 power? That's 1. 10 to the 1 is 10. 10 to the second is 100. What's 10 to the 8th? 1 with 8 zeros after it. So what's nice here is that we now can take all those zeros and suck them up into this scientific notation. Exponents. Base of 10, exponents. The other nice thing about this is if we have 100 times 100, this is the same as 10 to the second times 10 to the second is 10,000. And how many zeros are there in that?
4.
All we have to do is add our exponents and we get the answer, which makes it a lot easier to work with. The other thing that we have at our disposal is the fact that we have shorthand. We have these things that we use which are letters that represent a certain number of zeros that have now been absorbed. So that being said, we have a little letter K. K, it means kilo, which is 10 to the third power. M is mega, which is 10 to the sixth power. Giga is 10 to the ninth power. And tera is 10 to the 12th power. We can also represent things that get smaller. We can use a little letter m, which is 10 to the minus third, which is, you start with a 1 and then go 1, 2, 3. We get 0.001. That's milli. Micro is 10 to the minus sixth, which is 0.000001. Nano is 10 to the minus ninth, and pico is 10 to the minus 12th. What's convenient about this is that now we have a single letter that represents how many factors of 10, how many powers of 10 we have eliminated from our ugly looking math. So we can now say, what is our frequency? Well, we can say that it's 1,000,000 hertz. Or what else can we say about our frequency?
1 megahertz.
We can say that it's 1 megahertz. Exactly. We can also say that the speed of light is 300 megameters per second, if we were to want to do that. And actually, we do want to do that because we can use that to our benefit by making our equation a lot easier. If we assume that we're mostly going to be operating in the megahertz range, we can say that the speed of light is 300 megameters per second. And we can say that our frequency is, let's say, 1 megahertz. And we can write our equation again, C equals F lambda. And now we can do this, and we can say that 300 megameters per second is equal to 1 megahertz times the wavelength. The megas conveniently cancel out, and we're just left with 300 divided by 1, and we get 300 meters. The reason that we do that, again, is because we are working in a realm of mathematics where we don't really ever care about the really long wavelengths because they're impractical to use and so on and so forth. So what we can also do is say that if we are writing our equation, C equals F times lambda, we can say that if we assume that frequency is in megahertz, then C, instead of 3 times 10 to the 8th, just becomes 300. There's an implied mega in there, which makes our math a lot easier. And in fact, the way that we now do this is I draw this circle, 300, F in megahertz, and wavelength in meters. The reason that we do this is that it is really, really easy to remember. You don't have to wonder which one comes first, which one's on which side. It doesn't matter. You just draw this circle and you will never get it wrong. So now, in order to apply this, let's say we have a frequency of 15 megahertz. And you say, what is the wavelength? Okay, well, we can just go to the circle and we can replace F by 15, and we know that it's in megahertz. And what's the thing we don't know? I think we agree that it's meters, right? And look at that, we have this division bar right there. Lambda is equal to 300 divided by 15 is?
20.
20 meters. A frequency of 15 megahertz will have a wavelength of 20 meters for electromagnetics at the speed of light. How about if we experimentally found, we're going to draw that circle again. Remember, this is in megahertz. This is in meters. Okay, so we experimentally found a wavelength of, let's say, 30 meters. And we say, what frequency is making that? We would say, okay, we know this, so we're going to plug in 30. We have a division bar. We have a divisor bar right there. So we can say our frequency in megahertz is 300 divided by 30 is 10 megahertz. Ta-da! And this is how we convert frequencies to wavelengths and vice versa. And it's all based on the speed of light.
Can you leave that up for just a second?
Yep.
My father taught me something very similar to this, but with Ohm's law.
We're doing that next.
Oh.
We're going to get there.
Thank you.
So, would this work with light?
Yeah.
Sure. Absolutely. Okay, so now that can I move on from there?
Yes.
Okay, good.
Thank you.
Yep. Okay, so now that we've done that, we can now pop this back up. And what do you notice? Way over here at 300 meters, 300 megahertz, what's the wavelength?
1 meter.
1 meter.
1 meter.
What's 300 times 1?
300.
300. Okay, so let's move over here. At 3 megahertz, what's the wavelength?
That's 1 meter.
Now, at 3 megahertz, the wavelength is 100.
That's 100 meters.
What's 3 times 100?
300.
300.
Yeah, okay. How about at 300 kilohertz? 300 kilohertz is 1/10 of 3 megahertz. So what's 0.3 times 1,000? Because a kilometer is a kilometer is 1,000. What's 0.3 times 1,000? It's 300. You guys see a common theme here? What relates the top line and the bottom line? The speed of
light.
Speed of light.
Sound.
Okay. No, who said sound? Definitely not sound. This is the speed of light. Because electromagnetic waves are traveling at the speed of light. Okay, so the next thing that's important to note here is these operate in something called decades. A decade is a factor of 10. Notice that 0.3, 3, 30, 300, this would be 3,000, 30,000, 300,000. Each one is 10 times bigger than the last one, right?
Right.
Okay, so what is the actual spacing in here between, this is known as the high frequency band, between 3 megahertz and 30 megahertz? How much room is there in there? Between the high end and the low end?
7 megahertz.
27 megahertz. How about between 30 and 300?
270.
270. That's known as the VHF band. How about up here between 300 megahertz and this is 3,000 megahertz?
2,700.
2,700. That's right. This is known as UHF. How about between 3,000 and 30,000?
2,700.
27. Between 3,000 and 30,000 is 27,000 megahertz. So what you may notice about this is that each one of these, in addition to being 10 times the number, actually has 10 times more space inside it. This is a very important distinction because let us say that I am going to take a wave and I'm going to draw this wave and it looks like this. And it has a frequency. And we're going to mark it with frequency C, just the letter C. Okay? Now, I am going to look at this wave in a different way. We're going to look at this is the time spectrum, and this is the frequency spectrum. What is the minimum frequency you can have?
1.
0.
0. What is the maximum frequency you can have?
Infinity.
Infinity, yeah. Okay, so I'm going to arbitrarily mark our FC right here and say, how much energy is there in this wave that shows up at this frequency? And the answer is all of it. This is known as a spectrum. This is a frequency spectrum. And you will notice that because all of the energy is contained in this frequency, it shows up at that place on the spectrum. What's important about this is that if I just have a frequency that has one, or a signal that has one particular frequency, what is the one thing that you know about it?
I know what the wavelength is.
Yeah, you know the frequency and you know the wavelength. Do you know anything else? Can it possibly tell you anything else? If it's always there from the beginning of time until the end of time, is there anything else it can possibly tell you? Maybe how big it is.
The amplitude?
Right, but is there anything else if it never changes? Is there anything else it can possibly tell you?
The velocity?
No. I mean, that's not changing. I mean, if you look across
the phase?
No, because it's not changing.
Duration?
It's not changing. If it never changes, is there anything else it can possibly tell you other than it's there?
No.
No. But you just gave me an answer. How do you make it so that you can actually say something with it? What could you do with it if you could alter it somehow?
You could do continuous wave where you turn it off and on, like for Morse code.
You can turn it on and off. Okay, so you can go on and off. What else could you do with it?
Adjust amplitude.
Somebody said you could change the phase. Who said that? You could shift it. Yep. You could change the amplitude. You change the size. What else? What else could you do with it? Not much else like that. But what else could you do if you were the creator of this thing? Could you move it a little bit this way? If you had the power to do so? Could you move it a little bit that way?
Change the frequency one way or the other.
Change the frequency one way or the other. The act of doing any of these things is known as modulation. That is the act of changing a wave to make it contain information. So we can change the frequency, we can change the amplitude, we can change the phase, we can change whether or not it's there. Okay, so the one thing that happens when we do that is that the simple act of doing that makes this signal, even if it's just turning on and off, it makes it take up room. Mathematically, it makes it take up room. The more information you put into it, the more room it takes up.
Is
The
that bandwidth?
faster you change it, the faster you change the frequency, the faster you change the amplitude, the more you change it. Like if you change the amplitude a lot, if you change the phase frequently, versus, if you change it a lot, the more space it takes up. The more information you make it carry, the more room it takes up.
Scott, is that the same thing as bandwidth, or is that something different?
That is bandwidth. That is exactly right. That is known as bandwidth. Okay, so now we're going to look back at this. Okay, everybody remember looking at this just a minute ago? Yep. Given the fact that we now have established that the more information you transmit, the more space it takes up, which of these places would be a better place to put stuff that has a lot of information?
Between 300 megahertz and 3 gigahertz?
Or even higher. Where do you, does anyone enjoy their really slow Wi-Fi at home? Everybody?
Not
you
really.
You love your slow Wi-Fi? No, we love our gigabit Wi-Fi. Why is that?
I don't enjoy it, but I'm in that slow microwave bandwidth.
Yes. So if we want really fast Wi-Fi, we want a lot of data, a lot of information going across, you have to pick the highest possible frequency you can as a starting point, because the higher the frequency you go, the more space there is to work with. If you were to try to do Wi-Fi down here on the HF band, how much space do you have right here? Between 3 and 30 megahertz.
27 megahertz.
27 megahertz. That actually translates to a literal amount of bandwidth, which is a direct result, if you're going to modulate a signal, of the amount of information that you're going to put across. Data that you're receiving on your computer right now, the fact that you can hear me is all digital. The fact that you can see this screen is all digital data. It has to be transmitted. It takes up bandwidth. If you were to look at a frequency spectrum, you would see that it takes up a big swath of this area around 3 gigahertz. That channel is at least 100 megahertz wide just to watch your Wi-Fi. At the same time, that's exactly why you are using that part of the spectrum.
So this explains why, like the 2.5 gigahertz or whatever versus the 5,000 or the 5 gigahertz.
That's right. That's right. That's right. This is a practical explanation of why things are the way they are.
I'm sorry, I didn't hear the gentleman who just said that's why I...
Oh, that's why if you're on 5 gigahertz Wi-Fi, you can get really, really great bandwidths on your Wi-Fi. Because there's a lot of room to put those signals.
Gotcha.
There's a lot of space. Now, the next thing I'm going to do is I'm going to pop up this screen right here. This is the NTIA frequency chart. Has anyone ever seen this before?
Yes.
No.
Ooh, really? Okay. This is United States frequency allocations, and notice how it is spread apart.
Wow.
Okay. Notice how it is separated. I'm going to try to zoom in. Okay, so what we have here is we have these same bands that we had set up. Okay, so like this one starts at 300 kilohertz and goes up to 3 megahertz. The next one down is 3 megahertz and it goes up to 30 megahertz. The next one down is 30 megahertz and it goes up to 300 megahertz. Then 300 megahertz up to 3 gigahertz, and so on and so forth, all the way down. And what do you notice about up here? Well, it turns out that on the high frequency band, between 3 megahertz and 30 megahertz, you notice that these slices are not terribly plentiful and they're not terribly thin because there's only 27 megahertz to carve up. But as you go higher and higher and higher in frequency, notice what happens. There's just that much more room, and guess what? They get used for a lot of different things, don't they?
Oh yeah.
Bandwidth allocation is a valuable resource. Amateur radio operators have, wherever you see this kind of like dark teal color, that means that we have an amateur band there. This is at 142 gigahertz. Notice we have an amateur band, amateur satellite. At 240 gigahertz, we have an amateur band. At 47 gigahertz, we have an amateur band. Everywhere you go that you see that same color is a ham radio band that you have access to. All the way from way down here at very, very long waves. Like, there's one. That's the 160 meter band. Notice it goes from 1.8 to 1.9. It's only 100 kilohertz wide. Actually, really, there's two bands, but so it's actually 200 kilohertz wide. You come down here and you see that this is from 241 gigahertz up to 248, 255. This is 14 gigahertz wide. We can do all kinds of crazy stuff up there. Who else do you think wants to do all kinds of crazy stuff up there?
Telecom company.
Telecom companies, exactly. Our frequencies are extremely valuable to a lot of people who would be very, very happy to have them available to them. So that is one of the things that is always happening on Capitol Hill and at the FCC, is that American Radio Relay League, which is the organization that represents hams in the United States, goes up in front of the FCC and says, you know what, we need these allocations, and here's why. We provide all of this valuable service. Our hams, of which there are 750,000 in the United States, use these frequencies to provide at no cost all of these services to the public in the public good.
Scott, one question for you. You can dodge this if it's out of scope, but what stops us from going, higher? What stops us from, continuing to go up?
Higher than what?
No, I mean, I'm just looking at this chart, but
higher than that is light. Anyone can do it. They're not allocated above that. Okay. And whoever, Ben, thank you for posting the link to that NTIA page. So with that, now you kind of have a little bit of a picture of what the spectrum looks like and why certain frequencies fit into certain things. So the next thing we're going to do right after we take a 5-minute break is we are going to start by doing this. Let me erase that, and we're going to clear that. We're going to draw this.
Three dimensions.
Yes, we're going to do 3 dimensions. We're going to start by doing that. We're going to start by figuring out how waves actually travel through space. 5-minute break. All right. No complaint.
Yeah, move.
5-minute break. I don't know how to mute the microphone to where we can talk and hear while I'm listening to it. So that's the only reason. I took me a minute to figure out how to unmute it because I was trying to ask questions that wasn't going through. I finally got to mute it and I even answered a couple questions. Of course, one more. A couple of them are wrong, but still, but yeah.
that? Like that's getting a little the beeping.
Okay, and before we get started, I'm going to say I always try to make this time available for people to ask me questions. So, if you have a question, ask. If you have a question, you're probably not the only one with that question. And if not, that means I'm doing my job.
I'm still having a little bit of correlation issue, but that's just, I just have to look at it more.
Let's go ahead and ask it. Between what and what?
So I'm still looking at the that chart that you had up with the radio on it, and you've got the
What, this one?
Yes.
Uh-huh.
And the frequency and the wavelength, I'm still getting there.
What's the relationship between them?
So like when somebody says, "Oh, we're on the 48 meter band."
Mm-hmm. Okay, so the colloquial use of wavelengths and frequencies is approximate. So in order to do this, we're going to just go back to that 300. You always go back to this, right? Always go back to doing the circle. So let's say that we're on the 50 megahertz band. What's the approximate wavelength of 50 megahertz? That's a frequency. So what's 300 divided by 50?
6.
Okay, so that'd be the 6 meter band. So we can now go over here back to our frequency chart, which I don't know if I still have open. I probably don't, but maybe I do. And what do you know? 6 meter band. What is 6 meter band?
50 to
50 megahertz.
54
50 to
megahertz.
54. So we colloquially call things by their approximate wavelengths because it's a lot easier to give a name to a band. You know, they do that. We do this on shortwave too. The 15 meter band, by the math, would be exactly at 20 megahertz. In effect, it's from 21 to 21.45. We colloquially call it 15. Same thing on
Okay.
20 meters. 20 meters would be 15 megahertz, but colloquially, it's 20 meters. Really, it's between 14 and 14.35, but we call it 20 because it's easier to just call it that.
Okay.
All right. Other questions before we go? Nope. Okay.
Thank you.
You bet. See, you're not the only one who's got that question. I guarantee. Okay, so what we have here is a wave in 3 dimensions. It is traveling toward the right. This is defined by something called the S vector or the pointing vector, Poynting. You do not need to know this for anything other than your own edification. It's pointing to the right. It's actually the pointing vector. It's spelled differently, but it's pointing to the right. So, everybody hold up your right hand and your thumb, your index finger, and your middle finger. Right? 3 fingers. Okay. Your thumb represents the electric field, the direction of the electric field. Your index finger represents the direction of the magnetic field. If your hand is built like most hands, what do you notice about your thumb and your index finger? What angle do they make from each other?
Right angle, 90 degrees.
They make right angles. Okay, now take your index finger and stick it out straight. What do you notice about those fingers? All 3 of them. They're all at right angles, mutual right angles from each other. Right? Okay, your thumb is the electric field. Lays out on this axis. Your index finger is the other half of it, which is known as the magnetic field. And we use the letter B for that. And the direction of movement is your index finger. So what you'll notice is, let's say you take your middle finger and you point it directly at yourself and you rotate your hand. What do you notice about the electric and magnetic fields?
They rotate.
They rotate. The field, the energy is still coming toward you, but the fields change direction. But they're always 90 degrees apart from each other. Always, always. Right. Electric and magnetic fields are always at right angles to each other and right angles to the direction of movement. Is there anything saying that in order to keep this true, you can't have a field where something is moving toward you, but the electric and magnetic fields continually rotate? So long as they stay in right angles to each other, everything is okay. That is known as circular polarization if they rotate around in circles. If they don't move and they stay constant, that is known as linear polarization. They're both valid. They're both fine. So long as that basic rule, which is the right-hand rule, stays true.
Say the second one a second, Tom. I got the circular. You said the second one was
linear. Because if you look at it, it's always like I've drawn a linearly polarized thing here. Because it's always on one axis. They're not rotating with respect to each other.
Are you writing to us still, Scott?
On
the whiteboard?
I should be, yeah.
We haven't gotten anything in a well. Maybe I should ask everyone else.
We can see it.
I can see it.
Oh, let me
up at the top of the
good.
screen. There are 2. You'll have 2 tabs. One says meeting, and the other one says iPad screen.
Oh yeah, I just need to restart or something. I've had the same thing since the break. Okay, thanks.
Okay, so notice the E field I've drawn in blue, or sorry, in green, and the B field I've drawn in purple. So this is, why would it do that?
So the purple field is what?
The magnetic field.
Magnetic field.
Yeah, and of course it uses the letter B. Of course. Right? Doesn't that make sense, everyone?
Yeah. Yes.
Okay, that actually goes back a long way. Okay, so all of this work that defined these things, these are defined by something called Maxwell's equations.
And the green one was called?
The green is the electric field.
So I have a question. Can you control which one is doing, either circular or linear?
Yes. Yes, you can. And this one is the magnetic field, the lavender one. And notice that they are always perpendicular, and they are always going in the positive direction at the same time and the negative direction at the same time, but they're always perpendicular to each other. And the proportions, the sizes of which they are to each other are defined by the material that they're passing through.
And the orange is the direction, correct?
The orange is the direction of movement. And if you want to do a deep dive into the brilliant mathematics that came up with this, you can look up James Clerk Maxwell. He was, I believe, a Scottish scientist and a mathematician, and he was the one who figured out all this stuff and wrote down 4 equations that relate electric and magnetic field movements.
What was his name again?
Wow.
James Clerk Maxwell in the 1880s. Radio waves have been known about for a long time.
Just to clarify, direction is positive and negative. Your orange axis.
This is always moving in the positive direction.
Always positive, so it's really a direction through time.
Yep. The polarization of a wave is defined by the electric field. So that's why I say that as I've drawn, this is a linearly polarized wave because it's always in the same direction back and forth along one axis.
Mm-hmm.
If it's rotating, it would be a circular, it could be elliptical, it could be any number of different things. Elliptical, it could be like a wave that is changing in amplitude over time. So it would carve out an ellipse instead of a circle. A rotating wave would actually make like a spiral pattern. Interestingly, if you look at how these waves actually create, how we receive them, we have to get into the electrical side of things, which is what we're about to do. So a wave that has a field, an electric field that is in this direction with respect to our Earth. So here's the ground.
Mm-hmm.
This would be a linearly polarized, horizontally polarized wave because it's horizontal to the ground. It is equally valid to take a wave that does this. And that would be a vertically polarized wave because it is perpendicular to the ground. We think of standing up and down as vertical. So if, let's say, you have a wave that is horizontal and you have a device that is looking for only vertically polarized waves, will you see the horizontal wave?
No.
Good question.
It's kind of got the wrong key, doesn't it?
Yeah.
That's known as cross polarization. Does anyone have a pair of polarizing sunglasses for driving?
For fishing.
No.
Okay,
Yes.
what does it do? What do your polarizing sunglasses do?
Supposed to block wavelengths, isn't it?
No.
Oh.
What do your polarizing sunglasses do?
they only allow a certain direction of light, polarized
That's right.
light through.
They're
And
supposed
all
to
the others can't get through.
they're supposed to reduce glare. Glare is light that bounces off your the hood of your car, for instance, or off the water.
Right.
When it hits the water, the polarization of that particular light goes in one direction typically, and we see that as glare. By having lenses that are specifically designed to only allow the opposite, the perpendicular polarization to that, you essentially block those waves. It doesn't allow them to pass, so your glare disappears. Okay. Well, now we cannot talk about these things unless we give them a practical use. So what we've talked about is what waves actually look like, but now we have to talk about, oh shoot, I meant to clear that. We actually have to draw this. And I'm going to put the letters CU. Anyone know what that would be?
Copper atom.
That would be copper, yeah. Okay, so we have to start talking about atomic nuclei and electrons. So what are the two portions of an electromagnetic wave? There's two parts to it.
The electric field and the magnetic field.
Yeah, electro and a magnetic. There's an electric field and a magnetic field. Okay, so we have electrons in our atom. We have our protons and neutrons in the nucleus. Protons are positively charged, and our electrons are tiny, 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 fast-moving things, and they float around, and they have a negative charge. In an atom, you will have an equal number of protons and electrons, keeping them electrically neutral. So what we now have is we take this number of electrons, and we take the number of protons, and we have a neutral atom, and now we try to take an electron from outside, and we try to stuff it into this atom, which is electrically neutral and very happy. What will happen to that electron if it gets accepted? Well, it'll either ionize that atom, in which case it will have one extra electron and become captured, or it will take that electron, and when one floats in, it will take an electron and pop it out the other side. So if we take an electron in our atom and we push an electron in and we get one out the other side, what have we effectively done?
Replace one.
Yeah. Well, we've put one in over here and it has magically appeared on the other side. In effect, what has happened is that the electron has moved, has it not?
Right.
Right. Okay. So if we take a whole bunch of these atoms and we line them up like this, and we put an electron in one side, where will that electron eventually come out?
The other side.
The other end.
The other end. Okay. The movement of an
Creating
electron.
electrical flow.
The movement of an electron is known as a current.
Yep.
The movement of an electron is known as a current. A current is defined by the unit of an ampere, which is actually a very, very, very big number of electrons. Electrons are very small. A very, very big number of electrons passing through a given point per second. An amp is a lot of electrons, but electrons are very tiny. This is named after Ampere. I don't know why my pencil's acting weird today. That's named after ampere, and we call this unit an amp, colloquially. So, as a current moves through a piece of material, it is known as a current. A current, as it is the movement of a charged particle, generates a magnetic field in a loop around the current.
Okay.
Okay. Well, now, if we take a look at our electric field and our magnetic field, which is being floated around through space. Remember, we have this. Here's our electric field. And we have our magnetic field perpendicular to it. But notice it's always changing direction. Well, if an electron moving makes a magnetic field, what do you think a magnetic field moving will do to an electron that it finds?
Induce a current.
It'll make a current. And if it's switching back and forth, plus and minus and plus and minus, what do you think it will do to that electron that it encounters?
Exert a force?
It will move it back and forth. It will exert a force. That's right, back and forth. At what frequency? What frequency?
Hertz.
Whatever that electromagnetic wave's frequency was. That electron will shake back and forth at whatever that frequency was. So, where do you find a collection of electrons with a whole bunch of copper?
In a wire.
Yeah, okay. Well, so now what we have is an electromagnetic field that is just floating around, traveling through space, and as it does so, it encounters this piece of copper wire. Just sitting there. And all of a sudden, there is this magnetic field, which then goes like this. At a given frequency. What will it do with the electrons in that wire?
Move them.
It will move them back and forth at the same frequency. Right? Well, what if I'm able to measure it? What if I'm able to cause that to do something else? What if I can actually convert it into something I can listen to? This has a name.
Endpoint?
That is an antenna.
Yeah, I can see that.
So, a piece of wire in a magnetic field that is moving back and forth functions as an antenna. Does that have to be an intentional antenna? No.
No.
Any piece of wire that experiences a magnetic field will have what moving back and forth?
Electrons.
It will have electrons moving back and forth. The motion of the electrons is being induced by that magnetic field. This is pretty cool, right? So now, if instead I was to be able to go in reverse, and I could take this piece of wire and break it in the middle and feed power into it and make my electrons move this way, periodically I would change direction and make them move this way, and then I'd make them move this way, and then I'd make them move this way. What would happen? If a magnetic field makes a current at a given frequency, what does what is electrons moving, which is current, at a given frequency make?
A magnetic field of that same frequency.
A magnetic field at that same frequency.
It would shift it would shift it.
It would not.
When you went back and forth.
It would shift the direction.
Yes.
Yes. Which makes a magnetic field that is time varying and is doing what as it leaves? How fast does a magnetic field travel through space?
Speed of light.
Speed of light. By moving electrons back and forth in this piece of wire, we have created an electromagnetic field. So it works in both directions. An antenna experiencing a magnetic field, there is a current induced in the wire. If we can somehow push electrons back and forth along that wire, we make a magnetic field, which at the same time makes an electric field, which then is sent out into space. And what have we then created? What are those things?
Waves.
They're radio waves. And not only are they radio waves, by changing the frequency at which we switch back and forth, what can we do to those radio waves?
Make them the frequencies that we want.
Exactly. So if we were to do that, 28.450, we are not on any page, Jack. If we are doing this at 28, come on, why is my pencil acting up today? At a frequency of 28.450 megahertz, which is 28.450 million times per second. Yep, the tip is solid. What would our frequency be of our wave that is transmitted into space? Here's our electric field.
4.5 megahertz.
Yeah, exactly. We have intentionally made, by shaking electrons back and forth, a wave with a frequency of 28.45 megahertz. So all we need to do now to make a radio wave is do what? We have to have something that can move electrons back and forth at a given frequency, right?
A transmitter.
Well, it's an oscillator. We have to be able to make a given frequency. We're not doing that yet. We can't do that yet because what don't we have? What are we missing?
Power supply, antenna.
Oh yeah, we're missing all our parts. We haven't done any of that yet. So what we have to do now is go back and we have to go back to the new beginning, which is defining our parts and pieces that allow us to do that kind of thing. So we're going to start with this. This is a battery. Maybe my hand is getting in the way. Okay, this is a battery. It has a plus and a minus. This is a resistor. Resistor has an intrinsic property called resistance. It blocks the flow of current a certain amount. A battery has the ability to generate a force known as an EMF, which is an electromotive force. If you look at the things that make up the words electromotive force, electron, motive, movement, force. A battery generates an EMF, which is an electromotive force, which is the ability to move electrons. We measure that in V, which is volts. A battery is measured in volts. We also use the letter E for that, for electromotive force. For a resistor, we measure its units of ohms, which are that right Greek letter omega. So with this, we can actually build a, you can only see if it's black. I don't know how to help you there. So what we're going to do is we're going to draw this battery, and we're going to draw a resistor. So I have a plus terminal and a minus terminal. I have a big letter E for electromotive force. And we're going to say that our battery is 12 volts. So we have a 12-volt battery. All right, and then we have our resistor. And we're going to say that our resistance is 1 ohm. Okay, so what do we know about electrons? What charge does an electron have?
Positive.
Plus or minus?
Negative. Minus.
Negative. Okay, an electron is a minus charge. So where do electrons come flying out of on this battery, considering it has a plus terminal and a minus terminal? What would you guess?
Negative.
You'd be correct. So the electrons come this way. Like this and like this. Okay, but how do we define current? Unfortunately, we define current as coming out of the positive terminal, because the people who were working on electrical stuff long time ago in the 1850s did not know that there was such a thing as an electron that had a negative charge. So as a result, they got it wrong. And by convention, we now say that current comes out of the plus and back to the minus, which, you know, depending on how you think about things, actually makes a lot of sense. We think about things going from higher to lower. Okay, so now this thing on the ground is called ground. This is our 0 volts reference point. So that's 0 volts for the whole circuit. We call this a circuit because it makes a circle like a racetrack. If you have an open circuit, you can't get around the whole track. If you have a closed circuit like this, that's a whole circle. Okay, so now that we have this entire thing, we can start at any given point, and we're going to start right here at the bottom of the battery. Now, unless there is voltage lost because something is traveling through something with resistance, we're going to assume that it's a perfect conductor. A conductor, I hate this iPad. Okay, so there's our conductor. A conductor looks like this. It is typically a piece of some material that electrons that go in will result in an electron coming out the other side very, very easily. So, name some conducting materials.
Silver.
Silver. Good.
Copper.
Water.
Copper.
Aluminum.
Iron.
Iron. Not as
Gold.
good, but yep, gold is good.
And lead.
Lead is okay.
Aluminum.
Yep, aluminum's on there already. Actually, aluminum's an excellent conductor, but the problem with aluminum is that it oxidizes very quickly on the surface.
Yeah.
So this is copper is a nice point because it's not as rare as some of the other things. It doesn't oxidize that quickly, so we typically do a lot of copper. So copper is the most common conductor that we'll use. Okay, so copper, for the case of this circuit, it's assumed that the wires are made of perfect copper, which has no losses. It's a perfect resistor in that it has zero resistance. That would make it a superconductor. So for the case of this circuit, we're going to assume that it's a superconductor. Yes, water is an insulator. Water with minerals like salt water make it a very good conductor, which is actually why our bodies are good conductors. The water itself is not, but since we're largely salt, that salt makes us a really good conductor once you get through the skin. Okay, so let's talk about things that are insulating. Things that are insulating. What would the things that are insulating? That would be with things that have a high resistance.
Rubber.
Rubber or plastic?
Yeah, rubber, plastic, ceramic, glass, other things.
Bakelite.
Bakelite, yeah, plastic. That's a form of plastic. Wood. If it's dry. How about air?
Anything can be a conductor if there's enough power.
Yeah. How about air? Is air good or bad?
Humidity.
If it's dry,
insulator.
If it's dry, air is a pretty good insulator. So yeah, exactly. Air is unpredictable. If you live near the ocean, air is actually a pretty good conductor. So air itself is a pretty good insulator, but air near the ocean, because it has salt water in it, not so good. Okay, so now what we're going to do is go around our circuit, remembering that a circuit makes a full circle. And I'm going to redraw this because it's getting a little crowded. And here's our circuit. Here's our battery. And I'm going to put my resistor up here. Here's my E, 12 volts, plus and minus. Here's my R of 1 ohm. Okay, so Ohm's law says that, this is named after Georg Simon Ohm, who did his work in the 1820s, 1830s, I think. He determined that a particular resistor will block a certain amount of current flow. The bigger the resistor, the more it blocks the flow of current. Current, again, is the flow from the plus to the minus. The bigger the resistor, the more the current is blocked from flowing through the circuit. And the proportion of that is defined by this formula. E equals I times R. That is Ohm's law. Of course, named after himself. Where I is current, E is voltage or electromotive force, and R is your resistance. And if you are not talking, if you got noise in the background, try to mute yourself. Barking dogs, stuff like that. Okay, so E is equal to I times R. So for this particular circuit, E is 12 volts. R, 1 ohm. So looking at that, we can actually go through and rearrange it. We can do I is equal to E divided by R equals 12 divided by 1 is equal to 12 amps. Now, sometimes we like to redraw this. We redraw this like this. And that same circle thing.
There it is.
Yep, you've probably seen that before. And since we don't know the I, we would cross out the I, and now we have E divided by R, which is exactly where we ended up way over here. So that's a nice, quick, easy way to remember how the formula gets laid out. Well, as it turns out, that's a lot of electrons moving through that circuit. But that's okay. That's what the math says. We can change this circuit around a little bit. We can have like that. And now we have R1 and R2, and here's our E. And we have our I. Okay, so now, how much current, whatever that current happens to be, flows through R1 compared to R2?
Everything.
Everything. It's the exact same. Because the current that flows out has to be the same amount of current that flows back by something called Kirchhoff's current law, unless you have a circuit that actually does accumulate electrons, like with a capacitor in it. You cannot have electrons accumulating anywhere. The electrons flowing into any point has to be equal to the electrons flowing out of any point. And that was come up by a guy named Kirchhoff. So, given that, the current flowing through R1 must be the same as the current flowing through R2. Now, interestingly, how much voltage does this 12-volt battery have to supply? How many volts?
12.
12 volts. Okay, well, if this is at plus 12, and by definition, this is our ground. Ground means 0 volts. How many volts are on the other side of the battery? We have 0 volts on the other side of the battery, which means that in the process of going around the circuit, how much voltage has to be burned off?
12 volts.
12 volts. Okay. So how do you figure out which one of these resistors takes what voltage across it? Somebody's law. Whose law would that be?
Ohm's law?
Ohm's law. Yes. You can figure out whatever that I is. You can figure out what the voltage is for this resistor and the voltage is for this resistor. These resistors are in series, which means that they are in a lineup with each other. And what this means now is that since they have to experience the same current, Ohm's law is E is equal to times R for each of them. If the resistors are different, what's going to happen with the E's? They're also going to be different. Right? So they will experience the same current but a different voltage. Well, so now this brings up our next thing, which is Ohm's law for power. Oh, this pen is driving me insane. Now it's going slower than I can think, which is bad. Okay, so if power is equal to, which is letter P, we measure power in units of watts, just like James Watt, who did the steam engine. That looks like Walt. Come on. Okay, so we measure power in terms of watts. A watt is interesting because it's a joule per unit time, a joule per second. A joule is a unit of energy, so power is a measure of energy per unit time dissipated. So power is equal to our voltage times our current, or current times voltage. We can also draw that same circle, P, I, E. We do the same thing with that. So let's say that we find that we get a voltage of 3 volts across this one and 9 volts across this one. And we have 1 amp. Okay, so what's our power in our first resistor?
3.
Well, that's P equals I times
volt.
E.
3 watts.
Yep. P equals I times E. So that'd be 3 watts. And then the second one?
9.
That'd be 9. So that would be 9 watts. So the cool thing about this, of course, is that since you're noticing that defined by your different resistors, that determines what happens to your power. And it's different in different things. If the resistors are different, well, is there any time you can think of that would be a problem? So we're going to draw a circuit again. And let us say that this is our string of Christmas tree lights. 'Tis the season, right? And this one has a power output of 3 watts. And this pen has a power output of 9 watts. Because of slight variations in the manufacturing process. What's going to happen to those 2 lights?
One's going to be brighter than the other one?
One's going to be significantly brighter than the other one. And you really don't want that, right? How about if this is inside your home and you wire up your house lighting this way?
Oh, your house will be all kinds of weird things.
Yeah.
Weird things. Huh?
So let's say that you added another light right here, and now this dropped to 2 watts, and this dropped to 6 watts, and you only had 12 watts available, so this was now 4 watts. So by adding another device, what did you do to your other lights? You just made them dimmer. Yeah. Do you want to do that to your house? Do you want to do that in your home? I personally don't.
Not really.
Okay, so what we do to keep that from happening at home is that we wire our things in a different way. This is still a circuit. We still have our E. We still have our R. We still have our I. But now, if we want to add additional ones, we do this.
Put it in
P,
parallel.
does P equals I times E have a name? Yeah, it's Ohm's law for power. So now we have our different resistors. And what can you say about the voltages that are experienced by each of these devices?
It will be the same.
It will be exactly the same because they're all on this same voltage buses. You have this at 0 volts because that's at ground, and this at, let's say, 12 volts. So all of these different things will experience the same amount of voltage. Now, because they're experiencing the same amount of voltage, that means that the current going through each one will be different. Which is fine. What is the one thing that you have to make sure of when you're doing this? Could I keep adding stuff?
No.
Sure. I could keep adding resistors.
Right.
I could keep adding, what would be the problem with that? At some point, I'm going to add so many resistors and so much load, as it's called, that I'm now taxing the power supply or the battery to the point where it can no longer supply enough power to run everything. So let's say that my current is now 15 amps. All right, so I'm now drawing a total of 15 amps through here. And my power supply is only good to 10 amps. What's going to happen?
Hopefully we have a fuse on there.
Hopefully so. So, no, I won't get a short. I'll get an overload. Basically, the power supply can't do what you're asking it for, and it will either damage the circuit or it will say, well, if I've drawn this circuit correctly, what I'm going to do is add an element right here, which it's a piece of wire with a certain resistance, such that if a certain amount of current passes through it, at a certain voltage, a certain amount of power will be dissipated, which power that's dissipated in a resistor comes out as something. It comes out as heat. So if it comes out as heat and it's heating up a small piece of very finely sized wire, eventually if it's got too much current dissipating too much power, it will take that wire and cause it to melt.
Right.
And when it melts, what happens to the circuit?
It breaks it.
It breaks the circuit. You get something called an open circuit right here, at which point, how much more current flows through it?
Nothing.
None.
You get nothing. That's right. You get an open circuit. So that is called a fuse. A reusable one could be called a circuit breaker. And it's important to note that if you have a circuit breaker that is sized for a particular size, let's say you have a 10 amp breaker or 10 amp fuse. Why is it sized for that size?
So
I
the
don't know,
circuit
because
doesn't exceed the 10 amps.
Why
You've
would you?
got 15 going through, so wouldn't
Well,
you want it to be?
What
A
if
little
it's
more,
sized
for that size so that it matches the output of the power supply?
That's right, because you want to protect something. So let's say even though you've got 15 amps going through there, you have a 10 amp power supply down here. I would probably size, knowing the fact that I have a 10 amp power supply, I would probably size my wires such that I had enough ampacity to carry 10 amps. What if I'm carrying, knowing now that wire is not perfect? Wire has some resistance. We just went from assuming that wire is perfect to wire not being perfect. What happens when the wire is no longer perfect and it has resistance? Ohm's law.
You lose voltage.
P, well, yeah, but more importantly, P is equal to I times E, Ohm's law for power.
Right.
Right? And E is equal to I times R, which means that if you have a resistance in a piece of wire, you will heat up. It will dissipate energy as heat. The size of the wire determines how much you can carry. If your wire is sized for 10 amps and you decide and suddenly it starts carrying 15 amps, you are carrying much more current than it's designed for, you're generating more heat. If that happens to be inside your wall, what will it do?
Start fire.
It'll
Oh,
start
you'll
a
cause a
fire and burn
fire.
your house down. Exactly.
Absolutely.
Yep. So that is why we always use the same size fuse that is designed to be used in a circuit. If somebody came up with it, and unless you know exactly what you're doing, you don't replace a fuse with a bigger fuse because you'll burn your house down. Nobody
So
wants to do that.
I want to make sure I understand this. I'm going to say it back. You're saying that my battery is 10 amps. It's rated at 10 amps.
It's rated to deliver 10 amps of current.
How do I end up with 15 in my...
You made a mistake.
Okay, by putting too much, demanding too much. So that's why
Right.
the 10 amp fuse, because
mean-
that way it can't go over the 10 that it's rated for in the battery.
Right. The battery's going to
Exactly.
try. The battery or the power supply is going to try if you ask it to. And what will happen is it will get very hot, and either a fuse will blow or you'll damage something or set something on fire.
Okay.
Exactly. All right. Any other questions before we move on? Because I feel like taking a 5-minute break. And maybe taking this Apple Pencil and doing something bad with it. Trying to figure out what's wrong with it.
Didn't sound right.
Yeah. Trying to figure out what's wrong with it. It must be getting old. I'm sure I have another tip somewhere. Yeah, it's still at 45%, so I don't know. All right, any other questions before we go take a 5-minute break? Nada? Everybody's happy?
Yes.
Okay, then I'm happy. All right, see y'all in 5 minutes.
That big boy. Yeah, Daddy's gonna have to boil you for a few hours. You'll get over it. Daddy learning something really cool.
Hey, Blue G84, you may want to mute before you say something you don't want everybody to hear.
Oh. I'm trying to get glasses clean. Scratch nothing. Oh. Right.
You're unmuted. You're unmuted so we can hear everything you're saying.
Who are you talking to? I can't hear anything.
I'm talking to Blue G84.
Okay, I can't hear.
Okay, what are you hearing? Because I'm not saying nothing.
Yeah, I don't
You
hear
were
anything. I just
talking
see
in the
you dancing.
background to somebody, and we could hear the.
Oh, my radio's going. My stereo's going on very low volume. My girlfriend has it playing. So if it's bothering anybody, I can turn it off.
No, we wanted you to know we could hear everything you were saying.
Plus, I'm talking to one of my dogs here too. So,
Blue, if you're gonna be on, you should be muted unless you're speaking to this group.
I believe it or not, I'm on my telephone, so I actually cannot find the way to mute the thing. I found out how to unmute it, but I wasn't able to mute it back. So I'm just trying to keep everything as quiet as I can in the meantime.
Blue G84, when Scott comes back, ask him to mute you. He'll be able to mute you, and then won't be a problem.
Yes, sir. I appreciate that. I didn't realize that the whole group can still hear everything I'm saying. But I'm not. Oh, yeah. They heard me talking to people. Told me that if I'm not talking
We
about
can especially hear you when you
to the
whisper.
class or the group that I should mute my phone. I'm like, what the hell does that matter? We're on 5 minute break. Y'all off to that.
Hey, I hear I hear talking.
Take basic math all the way.
Lots of talking, no muted mics.
Oh yeah, he wants you to mute him. He doesn't know how to do it there.
Who?
Blue 84.
Done.
Thanks.
All right, so let's see. I don't know that my pencil's going to work any better now, but we're certainly going to try.
Scott, I just sent you a private note. I'm going to bail for 1 hour.
Okay. Well, we're gonna break at like 12:30 or something for an hour, so or half an hour. So.
I have SST with my students looking for me.
Oh, cool. All right. Let's see. Questions before we move on. Questions? Anyone? Bueller? Anyone? Okay, so what we've just first established is that we have this battery. And it looks like that. And what we have with this is the fact that our battery has a plus terminal and a minus terminal. And the plus and minus terminal are the source and the endpoint for our current, which is in the form of electrons. So what we're now going to do is we are going to define this as what's known as DC, or direct current. Direct current is current that flows directly from one point to another in one direction. And what we're now going to say is, okay, if it's always flowing in one direction, can we do something with it to make it not flow in one direction all the time? And the answer is yes, of course. We can always do creative stuff like that. We can make it flow in multiple directions. We can switch it back and forth. Creatively, we can have it flow to the right. Why is this doing that? Ugh! We can have it flow one way. We can have it flow the other way. This pencil is driving me up the wall. I might have to use just my finger if I can. That doesn't
You said
seem to
you had
work
another
either.
tip, maybe?
I tried. This is another tip. And I wonder if I have to reboot the iPad. You know, I'm going to try that. You never know, right? It is an iOS. Okay. And, okay, so, you know, I'm going to try to get through it, and I'm going to save that until break time.
Sometimes reconnecting it'll help.
Yeah, okay, well, let me leave. Make sure I'm not a host. I'm a co-host. Okay, I just left the meeting, and I'm going to restart.
Well, I meant reconnecting the pencil.
Oh.
To the iPad. Sorry.
True. Okay. Stay co-host. Oh, it thinks that hold on. Disconnect audio. There we go. My apologies. And I am not 100% sure how I want to disconnect this. So let me just try to see if I restart it. Maybe I'll get lucky. Okay, we're gonna try with that. Happy squiggles. All right, so now what we're going to do is we're going to start with this. And we have a plus and ooh, it already seems a little bit better. So we have our I flowing in this direction, and we have our E over here, and we have our R right here. This is the definition of DC, or direct current. Direct current means that it's only flowing in one direction. For this circuit, clearly it is only flowing in one direction. However, if I were able to hijack this circuit and make it so that I could do this with it. So I'm going to draw this circuit, and here's my E, such that I had current flowing this way out of the plus. And then a split second later, I could do this, and I could very creatively reverse the battery in its socket and draw it like this. Which way would the current now be flowing?
Yeah, the
Other
way.
direction.
Like that. Okay, and then I go through and I do it again, and I take the battery manually and do this with it, and so I draw it like this, and the current's flowing this way. If I were to look at this on a graph, what I would see is that my current would look like this. Sometimes it's plus, and sometimes it's minus. Would you say that it is alternating directions? Alternating polarities? Okay.
Mm-hmm.
This is known as AC, or alternating current. Now, this is also known as a square wave. Alternating current in the form of a square wave. Well, we're not doing a square wave for the most part. Yeah, you can do square waves, but for the most part, things in the world don't work as square waves. Especially if we're looking at a voltage that is being generated by a rotating generator. So, if you think of something that's rotating, what shape is most often made by things that are rotating?
Round.
Round, circles, yes. So the voltage that you actually find coming out of the wall, for instance, will actually, instead of being a square wave, will not be a square wave, it will be a sine wave, and it will look like this. And we represent this by a battery that has a sine wave coming out of it.
So when you look at an inverter and it says pure sine wave, what it's telling you is it's got the very, very nice curves and not squared off at all.
Yes, exactly that. So the reason that that's important is because a lot of devices don't like operating on chunky looking sine waves. Now, if you were to look at, let's say, okay, what's the frequency? How often what's the frequency of power that we use in the United States?
60 hertz.
60 hertz. At what voltage nominally?
110.
110 to 120 volts AC. Okay, so if you have an inverter and it is using DC and making AC out of it, there are a couple of ways to do this. You can make very, very high frequency and you can filter it, or you can just basically synthesize it by using a DC circuit. So if you were to synthesize it, essentially, depending on how fast you did it, let's say that you know that you want your voltage to look like that, but you don't have anything that'll operate that fast, so you want to simulate something that looks like that. So you make a DC voltage here, and another one here, and another one here, and then you connect the dots, and another one, and another one, and then another one, and another one, another, like that. What you end up with is something that is not beautiful, and it's not perfect, and you notice it looks kind of chunky. And now if I were to get rid of the original picture of the sine wave, it kind of looks like a sine wave, right? Right, but it's got distortion.
Right.
It's got distortion because it's got discontinuities in it. So that is basically noisy DC power. Now you could filter that, or you could do a sine wave generator that instead of operating at, let's see, 10 times. So that would be making a voltage 600 times a second instead of 60 times a second. You're basically looking at, let's say, 20 times that, so 1200 hertz. You could, for more money, build a sine wave generator that looked like this. The more accurately you make it, the more samples you take, the better the sine wave will end up looking. The less distortion it will have. The closer you get to a real sine wave, the better the sine wave.
How would you filter it?
We're getting to filters next. Okay, the discontinuities present themselves in the form of high frequency energy. What is the frequency of our sine wave?
60 hertz.
More or less 60 hertz.
60 hertz.
We are getting to that right now. Okay, in order to filter that, God, I love this. You guys are great. This is a great class, I got to tell you. I get so many good leading questions. Thank you for that. I like interaction. Okay, so now we have to add a couple more devices to our thing. We've already got this, which is what?
Resistor.
And what does a resistor do?
Resistor.
It blocks the flow of
Or impede.
current.
Impede.
Well, we're almost to impedance. Yes, it does impede, but it blocks the flow of DC and AC. All right, so we've got this. What's that? That's a battery. We've got a source of AC, which looks like that. Okay, none of those are really anything other than things that stay constant in time, right? They just do what they do. But now we're going to add a couple of things. Well, we're going to add this. That's a capacitor. A capacitor is a device that stores energy in an electric field. We measure this in C for capacitance, and we measure its ability to store an electric field and charge by the letter F, which is farads, named after Michael Faraday. So if we provide a source of electrons and not electrons, pluses and minuses, what will happen is we now develop an abundance of pluses over here and an abundance of negatives over here. Everyone agree with that? Because what's in between? What is that filled with?
Air?
It could be air, it could be plastic. It's an insulating thing. It doesn't allow it's designed for a particular voltage, because above a certain voltage the charges will actually puncture it and jump. Below that voltage, that's why a capacitor has a voltage rating. Below that voltage, they will just accumulate and sit there and wait. Now, what do those charges desperately want to do?
Jump.
Or
flow.
Move. Well, since they're contained in those plates, what do they desperately want to do? If they can't move, if they can't jump, they want to smash those plates together, don't they? Yeah. They're attracting each other, and those plates it's trying to pull those plates together. Mm-hmm. That is known as an electric field that is created between those things. You're basically exerting a mechanical force holding those plates apart. That energy that's stored in there is how a capacitor stores energy.
Ah.
I mean, it's basically energy storage in an electric field. The field is what is existing between those two plates. Now, on a microscopic scale, the positive plate is full of positives, and the negative plate is full of negatives. If I were to disconnect the battery and make it go away, what would I be left with?
Pretty much a battery.
Yeah, for a little while, yeah. That is basically a charged capacitor. It has charge built up, and if you hooked it up to a resistor that looked like this, what would happen to the resistor?
The capacitor would discharge into the resistor?
You'd get a current through the resistor, at least for a little while. And as that resistor dissipated that charge and burned up the energy as heat, what would happen is that your capacitor voltage would drop, the stored charge would drop. For a capacitor, Q is equal to CV, where C is its ability to store energy, and Q is the charge that it holds. So this discharges energy at something called an negative RC, e to the minus.
So does putting a wire, is that why you see large capacitors, industrial capacitors, they put a wire across it so that people don't get shocked?
That is
Because
right.
the wire dissipates what it would
that's why
out of the air.
That's why most capacitors have a bleeder resistor across them. Like this would be a very high resistance resistor, and when you disconnected it, it would eventually discharge it. It prevents a capacitor from basically building any kind of significant charge and maintaining it. Now there's a particular type of capacitor which we don't see very much these days, but it looked like this. And this would be
TV.
That would be an old TV, a cathode ray tube, where your electron beam would basically come out this way and be deflected by your yolks, and essentially it would light up the screen. Well, so this is an electron beam. This is a vacuum inside it, and typically between here and here, you would have about 25 kV. So when you disconnected this from the power supply and you made all this stuff go away, how much voltage is still contained inside that TV?
25.
About
25,000 volts.
Yeah.
Yeah. So unless you have a way to take a screwdriver or something and stick it under this rubber boot and ground it out, which makes a huge spark, you can get a very nice shock from that. It's a giant static shock. Okay, so that is a form of a capacitor, because what in effect is a capacitor? It's two metal plates separated by a distance. That is what a capacitor is. If you look at this TV screen, that's what a TV screen is. Because this is made of glass. And what's glass? It's an insulator. And what's vacuum? It's a very good insulator. So essentially you have a giant capacitor. So now we have to bring up the next thing, which is that I am going to hook up my capacitor like this. Here's my C, here's my plus and my minus. I have a bunch of pluses here and minuses here. I get plus charges on the capacitor and minus charges over here. If I have 12 volts here, what will my capacitor charge up to? How many volts?
12
volts. Yeah, my capacitor will charge up to 12 volts. It will hold 12 volts at whatever, depending on the size of the plates, that will determine, and the spacing of the plates, that will determine how much charge it will hold. So that being said, once it's at 12 volts, looking at Ohm's law, looking at Kirchhoff's law, looking at the fact that this is at 0 volts, if I go around the circuit and I go plus 12 and then minus 12 down to 0, how much current is flowing when it's fully charged? When you can no longer put more stuff in it, how much current flows?
0.
Nothing. Right, so you go from the fact that you have current flow into it while it's charging up, and then it fully charges up and there's no more space, so it doesn't charge anymore. It's fully charged. If you were to measure that over time and look at current versus time, you would see this as it charges up. And that's actually an RC time constant, where you have a little bit of resistance and then a capacitor. E to the minus T over RC. You don't have to know that, but that's a time constant. That's how a capacitor charges and discharges.
So
Okay.
it fills up and then it discharges, which allows it to fill again.
Only if you discharge it. I mean, if you don't hook anything up to it and don't use the charge, where does the charge go? Like, let's say you just have this circuit and it charges up the capacitor and has nowhere to go. What will happen?
Okay.
Just fully charges up. Okay, but now let's say that you were to creatively switch out this battery and flip it upside down. And you change the polarity, and now you have the pluses here and the minuses here. And what's your capacitor already charged to? It's charged to the opposite. So what's going to happen to the charges that are in the capacitor?
Going to dissipate, right?
They're going to go and flow back to the battery. And once they have all flowed back to the battery, you have no charge on the capacitor. But then what's going to happen?
Flip the battery again and it'll charge again, right?
That's right, except that it'll be reversed.
Does it automatically do that, or do you
you don't have any say in the matter. I mean, if I'm flipping the battery, sure. Okay, so basically what that means is that the battery will charge up the capacitor the other way until it's full, and then I go and I do this on purpose. Say, I'm going to switch this battery yet again. I'm going to decide I feel like switching the battery again. So what's going to happen to those charges again?
They're going to discharge to the
They're
battery.
going to go back to the battery, and then once the capacitor is empty, the capacitor is going to start to
charge the other way again.
Charge back up, and then you end up with positive charges. Oop. And this is just physics at work. Okay, so now what if I start to discharge and flip the battery faster than the capacitor can charge? So it never gets fully charged. What will the capacitor just sit there doing?
It'll hold the charge.
What
if
charge?
It's not full, right?
What charge? It never gets fully charged. And as soon as it gets partway charged, I start to discharge it. And then as soon as it empties out and gets partway charged the other way, I flip it around and do it the other way.
Does it behave the same way as if it was fully charged, or does it behave differently?
Well, does it ever fully charge?
Yes.
Sounds like you're almost. Sounds like you're creating alternating current.
I am.
Just thinking that. Yep.
So if I hook it up to alternating current, the capacitor never completely charges up. If my frequency is high enough, it never completely gets charged up. Well, if it never charges up completely, does my current ever stop? Because the only time a capacitor will block current is if it's completely charged. But since it never gets there, will there be any way to stop this current?
Oh.
No. So if I knew there was a wall here and I could not see what was behind this wall, we're starting to look at equivalence. If I could not tell what was behind that wall, but all I knew is that independent of which way my power supply was, either on the positive side or the negative side of the sine wave, as it went up and down, all I knew was that there was current flowing that way, and there's then current flowing that way. What could I equivalently assume was on the other side? If there's nothing that blocks energy on the other side.
A capacitor?
AC?
No. If there's nothing that stops the energy from moving. What's the name for something that doesn't...
A conductor?
Yeah. A short circuit.
Open circuit.
No, a short circuit.
Oh, short circuit.
A capacitor for AC is a short circuit.
Oh.
What happens if it's DC? It charges up and then it doesn't conduct anymore. If it doesn't conduct anymore, it might as well look like this. What is that?
Open circuit?
An open circuit. There you go. Okay, so now we have to draw the analog to the capacitor. A capacitor stores energy in an electric field. What stores energy in a magnetic field? That would be called an inductor. We go back to this piece of wire. Electrons are moving along the piece of wire.
Right.
This, as they are moving, make a magnetic field that makes loops around the wire. That's the magnetic field. If I were to take that and coil that up like this, I would get a magnetic field that looked like this. This is known as a solenoid. Those are my magnetic field lines. With regard to a piece of wire and DC, if I were to just have a piece of wire, what is the resistance of a piece of wire? Not a trick question. What's the resistance of a piece of wire?
If it's perfect, nothing, right?
Yep. What would be the resistance?
Be zero.
It'd be zero. Well, if that were the case, but yes, if you want to record it, yeah, go ahead. I don't care. That sounds great to me. I'm recording it too. So you have current flowing here, current flowing through here, current flowing through here, making a magnetic field. This is DC. An inductor is a letter L. It's measured in henries. That's called inductance. As the current is flowing, it generates a magnetic field. There's nothing in the way to stop it. What happens? It gets to a certain point where there's magnetic field energy that's storing energy, and your current keeps flowing, and what happens? How long will this keep going like that?
Till the source.
Yeah, till the battery's dead. Yeah, exactly. Right? It'll store energy in a magnetic field and blah 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 blah. Everybody's
It's not going to store it. It's not going to store it unless it has power going into it, right?
Right. Right. But basically that magnetic field, the existence of that magnetic field is energy storage.
So forget this stupid question, but is this similar to a transformer, or am I way off?
Part of a transformer. We're getting there.
Okay.
So this would be a short circuit.
Yeah, that'd be so for an inductor, DC for an inductor is a short circuit. I think you guys are getting this. Okay, so now what we're going to take this DC source and we're going to flip it around. And we're going to go this way. Well, which way is the current going to flow?
The other way.
The other way. But what already exists? What's
current going the other way?
Not current. Yeah, there's current going the other way, but what already exists around that solenoid? There's energy stored in that magnetic field. That energy in the magnetic field does not want to dissipate. It wants to be stable and happy. And what ends up happening is that magnetic field resists change. And it actually fights back by creating an opposite voltage and an opposite current until the battery finally wins. Because that energy has to go somewhere. The only place for it to go is back down into the battery. So it resists that change. So when you hook up an inductor to an AC circuit, AC for an inductor is an open circuit because it fights like heck because of that energy that's stored in the magnetic field. So, what do we have? We have DC for a capacitor is an open circuit, and AC for a capacitor is a short. Well, okay, what do you notice about these?
They're opposites.
They're opposite, yeah. Well, that means that if we have DC and AC and we try to creatively use them, like we try to creatively use these devices, here's the first mind-blowing part. Let's say we have a power supply of unknown cleanliness. We then take this power supply and we run it through this. And this goes through our load. We can have another capacitor here, like that. Okay, what is that power supply made of? What does that waveform look like? How clean is it? It's probably made up of some AC and some DC of different frequencies.
That's going to be a square wave then?
It could be anything. What is going to go through that capacitor? Look how a capacitor behaves.
It's only going to let part of it through.
Which one?
Just the AC.
Just the AC, because for a capacitor, AC is a short circuit, which means that you're left with what part going this way? Up top.
The DC.
Okay, so now when it gets to that inductor, what's it going to find? Look at an inductor. How does an inductor behave? AC is an open circuit, so if there's any AC left, it's going to hit a wall. And what's going to happen to the DC? It's going to find a
short circuit.
Short circuit. So yeah, DC definitely comes through. If there's any AC left, which way is it going to go?
Going to follow the second capacitor.
Going to go through the second capacitor. So what's left over here?
Just DC.
DC. What have we just done? You asked before. We didn't do a transformer. We just filtered it. Capacitors and inductors are the basis for filters. If I reversed the positions of these, and change this around so that I went like this. And here's my load. Load is the thing that uses power. Okay, so I have some AC and some DC right here coming out of this power supply. Okay, what's going to go through this inductor? Look how an inductor behaves.
DC.
DC is a short circuit, so the DC is going to go this way. What's going to be left over here? The AC. What's going to happen with the capacitor? Look at how a capacitor behaves for AC and DC.
It's going to let the AC through.
AC goes through. If there's any DC, it's going to get blocked. How about when it gets to this other inductor? If there's any DC left, it's going to go this way. And what am I left with over here?
AC to the load.
AC to the load. What if I also had higher frequency stuff? I could change the different devices, and so essentially this allows me, this particular configuration would be a high pass filter because it allows the AC to pass. It has frequency. The DC is shunted to ground, and I now have an AC filter. Pretty cool, right? Capacitors and inductors allow me to use frequency-dependent behavior to separate different things. And where does this stuff show up? Where do we use this kind of thing? Come on, everybody. Where do we use this kind of thing?
In the tuner?
No. Think about your real world. The
Oh,
answer is
sine wave,
Speakers? Like
sine
an
wave
inverter?
generator,
yeah. Where do
like
we use this kind of stuff?
Computer?
in the inverter to make it a clean sine wave.
We use this everywhere.
Every time we plug something into the wall.
Every time you plug something into the wall, every time you plug in a power supply to charge up your cell phone, every time you plug in your computer power supply. I mean, so now we are into designing this next thing. Here we go. Okay, so we have this. What is that thing called?
Resistor.
I hope it's an inductor.
Inductor.
Inductor, okay. Inductor, an inductor allows DC to pass. Well, it also turns out that AC will pass at low frequencies.
Boy, here we go.
Yep. Okay. So if AC will pass at low frequencies and I create a core which is made of iron, what does an inductor operate in? It operates in the magnetic domain. It generates magnetic field lines that look like this, that pass right through the center. They are concentrated in that center. What this core, usually made of iron, does, it allows us to concentrate the magnetic field energy inside there. So instead of being out here, it is largely contained inside that iron core. So now, if I have magnetic field lines that are generated by a low frequency AC current, and I now generate a second number of coils on the other side, what is passing through those coils? What kind of field?
Electromagnetic?
That's a magnetic field. The magnetic field is contained inside this iron core. It's basically a loop. Now I have a magnetic field that is passing through that second core. If a current makes a magnetic field, what does a magnetic field make?
So it induces a current in that second coil.
It induces a current in the second coil. This is called the primary, and this is called the secondary. This device is called a
transformer.
Transformer. The number of turns, this is N1 and N2, the voltage and the current are proportional to the number of turns of wire wrapped around it. Voltage is directly proportional. Current is inversely proportional. The reason that's true is because it is assumed that a transformer is 100% efficient, and what does Ohm's law say? P is equal to what?
I times E.
And if something is 100% efficient, that means how much power gets lost?
Zero.
Nothing. And if no power gets lost, then the I times E on both sides has to be the same. So if one goes up, the other one has to go down. So if I have, let's say, 100 turns over here and 10 turns over here, what is my ratio? It's a factor of 10. Okay. It's a factor of 10 because it's 100 to 10. So if I have 1200 volts over here, AC, how much will I get out on the other side? 120 volts. Guess what? What did I just do? I transformed 1200 volts AC to 120 volts AC. Where can I use 120 volts?
Everywhere in your house.
All over your house. Where can I use 1200 volts? I don't want it anywhere near me. Anyone?
From the substation to my house.
Yeah, yeah. And in fact, this is not usually the case. It's not 1200 volts. Usually, this transformer is going to be on the order of 1,000 turns per 10 turns. And what is that ratio of 1,000 to 1,000 to 100? 100 to 1. It's 100 to 1. So that means I have 12,000 volts AC outside.
Wait. Go back to the 100 and the 10. I'm kind of stuck.
What's 1,000 divided by 10?
100.
There you go. My turns ratio is 100 to 1. I have 100 times more turns on the primary than on the secondary. Therefore, I have 100 times more voltage on the primary than the secondary. So if I have 120 volts in my house, I must have 12,000 volts outside. If you're crazy enough to go outside and measure the voltage on your power lines, it's probably on the order of 12,000 volts. Yes, at the pole.
Somewhere I missed something because you said 100 to 10 and then you got 120 and
I changed it to 1,000 to 10 because I said 100 to 10 is really not what you find. It's really 1,000 to 10. If you have 120 volts inside, you have, at that turns ratio, 12,000 volts. I'll even redraw it.
Okay, got it. No, I got it. I got it.
So if you have 1,000 turns, and here's your core, and you have 10 turns inside, you have a ratio of 1,000 to 100, or sorry, 1,000 to 10, which is 100 to 1. That's your turns ratio. Your voltage is equal to N2 over N1 is equal to 100 times. So if I have my did I get that right? Well, this is V1 and this is V2. I'm trying to remember if I got that right. I think that's inverted. So V2 over V1, let's see, V2 over V1. It's actually N2 over N1. Is equal to 1 divided by 100. So if I have 12,000 volts outside, then I have 120 volts inside. So this is out on your power line. You have 12,000 volts. Inside you have a nice, friendly 120 volts. So why doesn't, let's assume that you have inside your house enough devices running that you draw 100 amps. Okay, what's your total power consumption by Ohm's law? Everybody? Don't be shy. Current is here.
1,200? I mean 12,000.
12,000. Yep, you have 100 amps times 120 is 12,000 watts. If you have a perfect transformer, which you're going to assume 100% efficient, if you have 12,000 watts being consumed over here, how much is on the other side? I hope it's 12,000 watts. At 12,000 volts, and we go through our formula again, P is I times E, 12,000 is equal to 12,000 times what?
1.
We get 1 amp. So why would we want to carry 1 amp instead of 100 amps?
Requirements for your wire would be a lot smaller, right?
Your wire's a lot smaller. Yep. What else?
Less loss.
Less loss because P is equal to I times E is equal to I squared. E is equal to I times R is equal to I squared R. So that would be ohmic losses, and that generates heat. So the less current you have, the less heat you're generating, and the less loss you have in your power lines. And why is that good? Because if the power company loses energy in the power lines, who pays for that?
Me.
Yeah, you will. That's right. So what's the only consideration if you're now running at 12,000 volts out on the power lines? Let's say that they transform that again up to 365,000 volts.
How big around the wire is?
No, well, the current is actually going to go down. What do they have to do the higher the voltage they go? What does voltage like to do? Essentially, it forms a capacitor.
Would it jump?
It'll jump. So
Bigger
what does that mean?
insulators?
Yep, you need bigger insulators. You need to
Spacing?
keep them further apart. At break, if you have outside power lines, take a look up at the power lines and notice that they're pretty far apart. There's a reason for that. Because otherwise you'll get arcing, and that's a bad thing.
And is that what you're hearing when you go under the power line? When you hear when
You're hearing a little bit of leakage.
Right, and you hear
Yep.
crackling? Okay.
You'll hear some leakage.
Wow.
Especially if it's a humid day.
Yeah, that's when it happens. Yeah.
Yeah. Or if you go out to the coast and you hear zzz, if it's really like a foggy morning and you get that ocean air.
Okay, yeah. So they're losing a lot of power when that happens then.
Yep. Anytime energy can neither be created nor destroyed, it just changes forms. Things that make light, things that make sound, that consumes power. Consumes energy. If it makes noise, if it makes an arc, that's lost power.
And there's just no way to get away from that.
Nope.
On the lines, you just have to use a gigantic
further apart. Yeah.
Further apart.
Make it harder for it to happen.
Yeah. Very interesting.
All right, so that's transformers. Now, what we're going on to now is the fact that we can do all kinds of other cool stuff with this. So we have an AC power supply. Now we can use these to our benefit. We're going to add another device. Anybody know what that is? That is a diode, which has a plus and a minus terminal.
LED, yep.
No, not an LED. LED is a special kind of diode. This is the cathode.
Oh, okay.
As a diode physical device, it'll have a band at the cathode end, which looks like a minus sign. So what happens with a diode is this is a one-way street in the direction of the arrow. It allows current to flow when there is at least, for silicon, 0.7 volts across it, or for germanium, it's about 0.3 volts. When there's a forward bias, it allows the current to flow from the anode to the cathode, which basically turns on the circuit, allows it to flow. Well, if we were to then look at this being a sine wave, at what point in that sine wave, given that this is plus and this is minus, would you say that it is plus? Where do the pluses happen?
Above the x-axis.
Above the x-axis. There you go.
Okay.
There you go. So what happens when it goes below? It doesn't work. So now your new waveform looks like this. It chops off the bottom part. This is known as half-wave rectification. This actually has a name. What would you call this kind of voltage? Over here on the left, this is AC. What would you call that on the right-hand side?
DC.
Except that it's ugly. I'd call it ugly DC because it's not really clean. All right, so when you actually were to look at this, this actually has DC, but it has AC components. What would you use to separate the AC and the DC out? We just did it a minute ago.
You do it with the inductor and the capacitor.
Okay, so which way do you want any AC to go? You want it to disappear.
Go down to the ground.
Right? So you'd put a capacitor here. That would take any of the AC down. Macroscopically, what you could see is that when it got to the peak, it would charge up. And when it went down to the trough, the capacitor would discharge and smooth out the dips. So the new waveform would look something like this. It wouldn't be nearly as ugly. It would smooth it out. Now, it's still bumpy, right? What could you add in there to make it a little smoother even? I could add an inductor, right? I could add another filter cap like that. Every time I do that, it gets a little bit cleaner. So now my waveform kind of looks like this. It's still a little noisy though, right? My electronics are not going to like that. So what I do at that point is I take my slightly noisy DC and I take this through another device known as a Zener diode. A Zener diode looks like this. A diode is a one-way street. A Zener diode is actually a backwards thing. Remember that a diode, we just did, goes in the forward direction. A Zener diode actually works in the forward direction, but it also works in the backwards direction if there's enough voltage across that point. What it does is up to a certain point, it will start to work. But yeah, we're going to take a break in just a minute. Up to a certain point, if the voltage goes above that, it will allow enough current to flow to cap that off. And what would you say about that blue line now?
Much smoother.
It's pretty smooth, yeah. So if I had a Zener diode that was, let's say, a 5-volt Zener diode, that would probably blow up in this case, but, you know, I'd have to put a little bit of protection in there, like throw a resistor in, maybe a resistor here, and this is typically going to be 12 volts AC. If
my voltage gets too big, it passes the Zener diode.
Correct.
It defeats it.
Correct. The Zener will limit the amount of voltage that gets to the other side. It basically changes its impedance so that it limits the voltage that appears at the output terminal here. So, given the fact that this is 12 volts AC, how do we make 12 volts AC from the wall? What would we use right there? What would you use to make 120 volts AC into 12 volts AC?
Transformer?
A transformer. Looks just like that. So this would be 120, and this would be 12 volts. Okay, here's my transformer. Where do you find this?
Phone chargers, everything.
Phone charger! This is a phone charger. This is a half-wave rectified phone charger. Ta-da! If you change the output voltage, change the input voltage, it becomes a computer charger. Change it again, it becomes a USB-C charger.
That's what those little blocks are on like outlets, right? Yep. I did just realize that. Got it. Thank you.
Can you, okay, I'm still a little stuck on this Zener diode. So why would I want that? Why would I want it to let through what I don't want to allow through?
Okay, so let's say that you took the Zener diode away. this is what your voltage looks like. Would you want to put that into a circuit that was looking for DC?
No.
No. So what a Zener diode does, it provides a voltage reference to say that if there's anything higher than that certain voltage, I'm going to allow current to flow so that there's enough voltage drop so that I only get 5 volts. No matter what was there, I'm going to allow enough current to flow across this circuit so that I only get 5 volts. And actually, I wouldn't be here. It would be that other resistor. That is the beauty of the Zener diode. It's a voltage reference diode.
Isn't that similar to that of a solenoid using reference power?
I don't know. I don't know the answer to that.
So I'm taking 12 and I'm only allowing 5 to go through the rest of my circuit.
But they're different flavors. Yeah. Essentially, what happens is if the voltage if it's at 5 volts for a particular time, the Zener's not going to pass anything. If it goes up to 8, the Zener is going to pass enough current through so that there's enough voltage drop so that you only get 5 volts. The Zener is a special device that changes the way it behaves so that it only allows a certain voltage to exist.
Okay.
Kind of a magical diode. And what was that other question? What happens if you take a shortcut and put the Zener right after your first diode? Ooh. That is an interesting question. My guess is that the Zener will be overworked. I mean, it could work. It'll flat top. It'll flat top the output. All right. Very last thing we do before lunch. Here we go. Very last thing we do before lunch. We take a diode that looks like this. A diode is a one-way street. We now take a couple of diodes. Okay, there are two types of material. There's a P and an N semiconductor material. Diodes are made of something called a semiconductor, silicon or germanium. They're elements that have a partially full outer valence shell, which means they can accept an electron, you can take one away, and they don't really complain all that much. What it really means is that they're not really conductors and they're not really insulators. They fall inside that happy medium, which means that if you throw a couple of extra protons in on one side or a couple of extra electrons in on one side, it will sort of behave like one or the other, like a conductor or a not a conductor. And if you put a voltage across it, it will change how it behaves, which is why it works in one direction. If there's enough voltage, it will flow, and if there's not enough voltage, it will block. So this is how a semiconductor diode is built. You can also do them with vacuum tubes, oddly enough. Well, really old school. However, if you were to take this and sandwich three things together and make this a P, an N, and a P, or an N and a P and an N, and then put this extra wire in between, you now have a three-terminal device. This is called a transistor. And the way a transistor works, we draw it like this. Notice this is our diode. There's a diode. This is actually back-to-back diodes. This is known as a bipolar junction transistor. If we have this diode right here, which goes from the P to the N, and then we have an N. If we put a small amount of voltage and current through this path, what we end up with is an avalanche coming through this way. Well, if we have, let's say, 1 unit of current flowing this way, we might get 200 units of current flowing that way. If we drop this down to 0.5, we will only get 100. If that keeps happening, what is that the definition of? Everybody. Come on, somebody has to know.
An avalanche circuit? I don't know.
Amplifier.
That is an amplifier. It takes
Amplified.
something and makes something bigger out of it. It makes a bigger copy. That is the definition of an amplifier. So a bipolar junction transistor, which contains a base and a collector and an emitter, those are its terminal names, is a three-terminal device that can function as an amplifier, which means to make a bigger copy of something.
So the circuit comes through the B.
This is my bias. This is my bias. This is my driver. My driver signal. What I want to make a copy of.
And so that comes in B and goes out of C?
No, it comes out of, everything comes out of here through the bottom.
Okay.
So I have two halves to this circuit. This is the first half, and this is the second half. The stuff that goes from the base to the emitter is a very large copy is made from the collector to the emitter. It's a separate power supply. And what's really cool about this is that I can use this two different ways. So if I have a graph of input on that axis and output on this axis, up to a certain point it does nothing, and then all of a sudden, whoa, it works. And then above a certain point it starts to become full and doesn't do anything anymore. Well, these are three distinctly different regions. This makes this a pretty much straight line. This is known as the linear region because it makes a line. This is known as the cutoff, and this is saturation. In other words, it's saturated. You increase the input and nothing else happens. These have distinctly different purposes. This is used for an amplifier. Let's say you want to make a larger copy of somebody's voice. Because it's linear, it's proportional. It'll make a nice clean copy. When would you ever want something to be completely off or completely on? Can anyone think of anything that's either a 1 or a 0, true or false?
It's noise.
Can you think of anything? Any reason why you would ever want something that's either completely on or completely off, true or false?
Power button.
CD.
Every computer command.
Every computer known to mankind. This is digital logic. So this is analog, and your zeros and ones are shut off and saturation. That's your digital use. There's another form of a transistor that was known as a BJT that looked like this. There's another one that looks like this, which is known as a FET. This is how most electronic devices are made now. It's known as a field effect transistor. And if I've drawn it properly, you will understand why it's called a field effect transistor. This is the gate and the source and the drain. Do you see anything that the gate is attached to? What does that look like? We just drew that a minute ago. What does this thing look like right there?
Capacitor.
That looks like a capacitor. So by putting a voltage across here, that can change what happens on the other side. But because there's a big empty space, how much current flow is there out of the gate? It's just enough to charge up that plate. And then nothing. Which means how much current is actually used. Once it's fully charged, how much current is there to flow?
Zero.
Zero. If there's no current, how much power is there? There's no power used.
None.
If there's no power used, how much heat does that transistor make?
None.
Nothing. If you have 2 billion of those on your little computer chip, what does that mean?
Nothing.
It
That means
dissipates the heat.
it dissipates the heat. There's very little heat made, which is why FETs are used for power amplifiers as well as digital computer circuits because they are very efficient as far as power and heat generation goes. That's why that is the basis of most computer chips. All right, everybody ready for lunch? Or a late or Tomislav ready to go have a beer or something?
Now I'll have another cup of coffee to survive this.
Yeah, okay.
So that's MOSFETs.
A MOSFET is a metal oxide semiconductor field effect transistor.
Okay.
An EGFET is an insulated gate field effect transistor. A JFET is a junction field effect transistor. They're all FETs. They're all field effect transistors, which means that the basic unit that's inside them is a capacitor. So they're voltage controlled devices instead of current controlled devices, which makes them more efficient. And actually, more like how a vacuum tube works.
Oh, I don't know that one.
A vacuum tube is essentially it creates an electric field, and that pulls current through. A vacuum tube is actually like a field effect device. Good old school vacuum tubes.
Oh, okay.
Got a couple of those laying around.
Yeah, they're still useful. Other questions before lunch? Take 30 minutes for lunch. So whatever time it is where you are, take 30 minutes. Is everybody okay? Everyone happy?
Oh, yeah.
Getting money's worth?
Yep, we'll see you. Yeah.
I always offer a double your money back guarantee. So that's a great thing about doing it for free. I'm never really out anything. All right. Good work, everybody. See you after lunch.
Okay, thanks.
if anybody has any questions, this is good time to do it. I'm just sitting here. I finished my lunch.
So Scott,
Yes.
since no one else is jumping in, I have a question. I'm a little confused about the short circuit, open circuit terminology.
Mm-hmm.
And what it looks like in your drawings is that the short circuit allows the power to continue through the
Right.
circuit.
Right.
An open circuit means it's got a gap in it, and so the power cannot go through it.
Correct.
Correct?
Mm-hmm.
So why is it always bad when you hear someone say, uh-oh, you've got a short circuit?
Well, I mean, ideally, if you think about it, a short circuit, depending on where it is an uncontrolled path.
Okay.
If you're talking about power, it's an uncontrolled path, which is very bad because a true short circuit. Let's say you're running a motor or something. A motor is designed to pull a certain amount of current. If you have a short circuit, how much current is it going to pull?
So it's an unintended short circuit is what
Yeah.
you're talking about. Okay.
Yeah.
Okay. All right. I think I understand better. Thank you.
Yeah, and we're going to get back to the definition of a short circuit versus an open circuit and capacitors and inductors because was what we covered was in the extreme, but in reality, it doesn't quite work like that. Essentially, what we were looking at was where the frequency is either zero or infinity, and in between you get a very wide range of how things react. We're going to do that right after we come back.
Okay. Thanks.
Because that's that's the basis for frequency dependence, and frequency dependence is essentially how we can synthesize frequencies, make them ourselves so we can use them.
Okay.
And that's the basis of being able to build a radio in the first place. The ability to synthesize a frequency by using devices creatively.
Which I would love to take a class to do that. I think it would help me a lot understand this all better.
Well, I think yes, but there's nothing stopping you. If you want to build a kit radio and see what it really feels like to wind a coil, there's no substitute for that. I've done that. It's pretty great.
Heathkit.
Well, except Heathkit hasn't existed for a long time, but there are
Yeah, you can
still
get a lot of them on eBay nowadays.
Yeah, exactly.
Like 200 a series. Old
Right, but
green ones.
not unbuilt.
Correct. Yeah.
So
that's the
if you
sad
want
part.
an unbuilt kit, basically you're looking at a single band QRP CW transmitter or something, and I'm sure you can still get that. Let's see.
I'd say
And I
Radio
just want to
Shack,
say,
but we're out of luck.
yeah, I just want to say thanks again, Scott, for offering these classes. They're awesome. You're a great asset.
Thank you. I enjoy doing
Thank
it.
you.
I agree.
Thank you. Like I said, double your money back. So double your money back if not satisfied. Let's see. So, here we go. You can still get one of these. All right, Hilltopper, I guess, tall boy. Let's see. You can still get the benefit of learning to do it yourself. Let's go for 20 meters. $152. It's not cheap, but it's a decent, decent little radio.
What was the price on it again?
$150 for a
150
single band.
bucks?
But it's all analog.
Yeah.
You can build a micro bit X kit from a kit for like $75 or $80.
Yeah.
And let's see, QRP guys. Let's see what they sell. Oh, yeah. Micro SDX.
Baofeng. Nope, not those.
Multi DC. Digital transceiver. Oh, 40 meter shortwave Pixie kit.
Pixie kit.
Yeah, Pixie. Bless you.
Wow.
Thank you.
You can still get stuff.
Yeah,
Oh, if you build your own tuner, you get to wind your own coils. See?
Well, that's not bad for somebody who hasn't seen
There's a coil for them.
resistors and capacitors and whatnot.
Yeah, being able to do something like this firsthand is actually quite useful. Hey, it's 120.
Is Heathkit still around? Because my
Oh,
father's got one.
they've been out of business for
Scanner out of it.
years and years.
I kind of figured they were.
Yeah, they've been out of business for years and years. They tried to come back for a little while, and that was unsuccessful. But there are a lot of small kit manufacturers still out there. So
I'm trying to think of a kit that I can bring. I teach the radio merit badge for Boy Scouts or Scouting
so do I.
USA
It's
now.
hard to get the kids to show up for
No.
that.
Oh
I've had
my
trouble.
goodness gracious! It's sold out every time I teach it.
Really?
Yeah,
I
I've actually
can't.
had to start teaching a morning and an afternoon class over the weekend in order to facilitate. I have about 30 scouts per class.
Where?
It's Camp Tonakita in Jupiter, Florida, right next to Jonathan Dickinson State Park. So just above Palm Beach.
Here we go. Here's a QCX Mini. And it's digital. Look at that. I don't know how much. Wow, there's not much to it. That's the board. There's not much to that. It's all software defined. All right, everybody ready? All right, we've lost a few people. That normally happens. There's a lot of stuff. Tomislav, you're still awake. That's great. Okay, so let's see if my pencil is at 100%. It's at 93%. That's a very good start. Okay, so whoops, didn't mean to do that. Meant to share a whiteboard. Okay, are there any questions before we get started again? No, nada. Okay. All right, here we go. Continuing right along. So now we have figured out that, yes, I will be sending a link. I'll putting it on YouTube and sending a link to the link of the recording to everybody. Okay, so here we go. So now we are talking about that and that. Okay, so this is a resistor over here, and this is a capacitor, and an inductor, and a resistor. So, does a resistor care what frequency is passing through it? Yes or no? Anyone? Can everybody hear me?
All right, I didn't hear the question.
I'll guess no.
Can everybody hear me okay? Well, a resistor just basically reacts directly. What's the formula for a resistor? E equals I times R. It is directly proportional. The current is directly proportional to the voltage, right? So it doesn't care what's passing through it. Agreed? Okay, so Resistor is not frequency dependent. There are actually two things. One is called resistance, which is how something behaves with regard to DC. There is another component to this, which is X, which is called reactance, which is how something behaves with regard to alternating current. We measure resistance in what unit?
Ohms.
Ohms. We measure reactance in ohms. Okay, so ohms. They're both ohms. Great. Okay. So now there's another unit which is the letter Z, which is impedance. This is how something reacts to a combination of AC and DC. And how do you think we measure that? Unfortunately, that's also ohms. Okay, so as it turns out, though, you can prove this mathematically, but we're not going to now.
Is impedance? Impedance.
Impedance.
Oh my lord! Never mind.
Impedance, not impotence.
Impedance.
Yeah.
Is that a measurement of how much current is not being passed through based on the input voltage or current?
Impedance, well, if you think about to resist and to impede, resistors impede the flow of DC current. They also impede the flow of AC current. So they have resistance and impedance, and they happen to be the same.
Okay.
A capacitor, for instance, and an inductor, they have different values for resistance and impedance, right? They react differently when there's AC involved. So how they react, X is known as reactance. And that's how something behaves with regard to AC. And impedance is a combination of AC and DC. So there's resistance, reactance, and impedance. Those would right now seem to be very confusing, and I'm going to try to clear that up right now. So there's a coordinate axis. We call this the resistance axis. And we call this the reactance axis. Notice that they appear at right angles to each other. Everybody agree with that?
Mm-hmm.
Okay.
Yeah.
This is measured in ohms, and this is measured in ohms. Resistance is how something behaves with regard to DC. Reactance is how something reacts with regard to AC. There is now a complex, because these are perpendicular axes, there is a complex form. It becomes complicated how something would react to DC and AC. So the way that this works is, you just got to go with me on this one, is there such a thing as negative resistance? That you've ever heard of? In practical terms, I think it exists. It can exist, but nobody ever uses it. So basically, this half of the plane, it doesn't exist for all intents and purposes. So that leaves the positive resistance and positive and negative reactances. So given that we have resistance, which can go all the way from 0 up to infinity, and reactance, which can go from negative infinity all the way up to infinity, there's a really kind of infinite number of different things that we can have here. So let us say that we have let's say we have a device that has been measured to have a resistance of 3 ohms and a reactance of plus 4 ohms. Well, okay, so this is where it gets a little bit tricky. Does everybody remember Pythagoras' theorem?
Yeah.
X squared plus y squared equals z squared? All
Yes.
right, so we have to plot these. So we go 3 units over. So this is 3 ohms of resistance. And we go up 4 units. So I have chosen those numbers for a reason, because what is, if we have a 3, 4 something right triangle, this is 5 ohms. Our impedance, the magnitude of our impedance is 5 ohms. We have 3 ohms of resistance, and we have 4 ohms of reactance, and they're perpendicular to each other. Well, okay, let's say that we take another device and we take a measurement on it, and we find that it has a resistance of 3 ohms, but an impedance of negative 4 ohms. What would we do with that? We go over to 3, but this time we go down. Four. What is the impedance of that device? It's also 5 ohms. Yeah, okay. But isn't it on a different place? Isn't it in a different spot on that graph?
Yeah, I have
Okay.
a question about that, Scott. Why
Yep.
can you have a negative reactance but not a negative resistance?
That's a very good question. Well, negative resistance, there's just no practical way to do it. I mean, if you think about it, that would mean that if you had a given voltage, you'd have a negative current. That doesn't really exist. So there may be a device that does that, but no one's really ever, practically
So when
found
would
it.
you have a negative reactance?
No.
Well, I'm getting there. Okay, so as it turns out, if you go and start looking at how capacitors and inductors really behave, what you'll find is that XL is equal to 2 times pi times the frequency times the inductance. And XC is equal to, which is a capacitor, minus 1 over 2 pi FC. The reason that this exists is that if you redraw Ohm's law, everybody, what's Ohm's law? Come on, everybody, tell me. Ohm's law.
E equals I times R.
Right. Except
Yeah.
that that's a specific form for resistors. And in reality, E is actually equal to I times Z, where Z is impedance. And Z is equal to R plus little I, which is the perpendicular axis, times X. Well, you see we have the R and the X axes, right? They already exist on that graph. So what ends up happening is that because a capacitor has this negative sign in front of it, that means that if I have a given current, I have a voltage that is the multiple of it, but there's also this imaginary thing. There's an angle right there.
Mm-hmm.
And this is super, super, super important. And I know it looks weird, but it's incredibly important. Yes, L is an inductor. It's super important because what ends up happening here is that if I look at the inductor up top, its impedance is actually Z is equal to 5 ohms with an angle of about 50 degrees. And it's a positive 50 degrees. That's this angle, roughly 50 degrees. If I look at the capacitor, I will find that the impedance is 5 ohms with an angle of negative 50 degrees, which means that the angle swings down. Which now, if I plug those values in here, I will find that for a given current, the voltage will actually be ahead of the current or behind the current by a given angle, which is defined up there. It actually changes the phase of the signal. And remember we talked about sine waves? This is a sine wave. What's the phase? The phase is where it starts and ends. I can shift the phase like this. I can shift it ahead, or I could shift it back. That's one of those things that you can change. You can change where the wave starts. That is what capacitors and inductors actually do when they create a voltage or a current from the other. They actually cause a phase shift. They cause an amplitude change, and they cause a change in phase. So now, let me ask you this question. Given the fact that we have just defined this, looking at this graph over here, I would ask this question. What is the sum of this plus this? Those 2 points. If I were to try to add those 2 points together.
That's 0. 0?
Well,
Yeah.
the resistances would add, but the reactances would cancel, so it would actually be out here. Because these parts would add together, but then the this part and the this part cancel each other out. So, in other words, this actually is an inductor at a given frequency. Anyone guess what this one is down below? That would be a capacitor. So, an inductor and a capacitor have reactances that when taken together can cancel each other out. This is actually very profound. The reason it's so profound is because if I have my XL is equal to this formula, 2 pi f L, and XC is equal to 1 or negative 1 over 2 pi f C. What do you notice that appears besides the 2 pi in both of those? What letter shows up in both?
Frequency.
The frequency.
Yeah, okay.
Yep.
So, the frequency, which means that the reactance of an inductor and the reactance of a capacitor, in other words, how it behaves with regard to frequency, determines how it looks. So what if I were to take a frequency of 0? What does an inductor look like? 2 times pi times 0.
It would just be what the
0.
inductor was.
No, it would be 0. Anything times 0 is 0.
0.
Right? How about a
Yep.
capacitor? If I have 0 in the denominator, what does that mean?
Undefined.
It means infinity. Okay? If I have frequency of infinity, what does that mean for an inductor? 2 times pi times infinity.
Infinity.
Okay, and how about for the capacitor?
It'd be 0.
It'd be 0. So, does everybody remember what happened when we tried? What does frequency of 0 equal? What does that mean?
No flow.
That's DC. That is direct current. There's no frequency. It's frequency of 0. Well, before lunch, we said that an inductor at DC is a short circuit. It has 0 resistance. An inductor at high frequency has infinite resistance. In the extreme, it's an open circuit. Infinite resistance is an open circuit. And for AC of very high frequency, a capacitor looks like a short circuit, which would be 0. And an inductor looks like infinite impedance, which would be an open circuit. So these formulas work in the example that we tried right before lunch. But in reality, those were simplifications. What really happens is that you have these formulas that are at play. So all this works. But now what happens to all those frequencies in between 0 and infinity? Well, and it turns out that if you notice that this one is positive and this one is negative. Is it possible to set them equal? Absolutely. So I can select a black box. I'm going to say that this is my capacitor. And this is my inductor. This is my letter C, my letter L. These add together for impedances and for reactances. Can I make it so that these are equal and opposite to each other so that XC plus XL is 0? Could I make it so they completely cancel out? Given that one is plus and one is minus? Okay. It turns out that if I take those two formulas up above, I get frequency is equal to 1 over 2 pi square root of LC. So, given my choice of L and C, my reactance goes to 0 at a particular frequency. If I have a graph of my reactance and it looks like this, where this is my frequency and this is my reactance, what does that mean right here? What is my reactance right there?
0.
If it's 0 and I draw a circuit that has that in there, and I have my AC circuit with a whole bunch of different frequencies in it, what frequency is going to get through the best?
The high frequencies.
Which one? There's only one. Which one? I can't even read that. My pen is acting weird again. Which frequency is going to get through the best? Just that one for which the impedance is as low as possible. This is known as a condition called
Resonance.
Resonance. So, by picking the values of our devices, this allows us to select the frequency at which they resonate naturally together. That is really cool. Because if we can take that frequency and we can amplify it, what can we do? What can we do with it? If we can basically select a frequency and put it in an oscillator, what frequency is it going to select to make? Oh, somebody speak up. Anyone ever played a musical instrument? When you put
Well,
down
it'd be
key, when
off.
you push down keys and you blow into the flute, what note comes out?
The note that that the chamber is the correct length
And
to
why?
give me.
How come not the other ones?
It'd be the one with the less impedance.
That's right. It would be the one that
Less
there's.
resistance.
That's right. It would be the one for which there's less resistance. When you make a circuit with a certain size of, with a certain inductor and capacitor, you have basically used those to select the perfect frequency to make. So if I have a circuit that looks like this, and I have a variable capacitor, what does that mean I can do with my circuit?
You can tune it.
I can tune it.
Mm-hmm.
I can also make this variable. I can do all kinds of crazy stuff with this. I can make a circuit that looks like this.
Would you use that in an antenna?
You'd use that to tune an antenna. You'd use that to tune, it's called a tank circuit. This is this is a common design known as a T-type antenna tuner, where this is your antenna up here of some unknown impedance, and you have all of those are variable devices, variable impedance, because you can change their values. And because you can change their values, you can change how they resonate with each other. You can transform one impedance into another. You can magically make something look like something else using this. And what are the basic devices that make that happen? There's two of them. Come on, everybody.
A capacitor and an inductor.
Yep, that's it. Capacitors and inductors are the basis for analog tuned circuits. That's it. Let me take a picture here. Oh, look at that. Perfect. I'm going to share this. Okay, so this is the inside of an MFJ 949E antenna tuner. What does everybody see?
Coil.
Okay,
capacitor.
there's a big coil. How many capacitors?
Two big variable ones.
Two big air variable capacitors. Those are tunable by knobs on the front. The inductor has taps that allow you to short out a section of the inductor, thereby changing its inductance. This is a T circuit that allows you to take an antenna which is connected to the outside world, use your variable inductor and capacitors and make it look like something else. That your feed lines, which are designed for a particular impedance, typically 50 ohms, and your transmitter, which is a 50 ohm transmitter impedance, can send power into. And all that is being done by what?
Inductor and capacitors.
Inductor and capacitor. If you take those and you have a resonance circuit and you take those and drive them into a transistor, and you take the output of the transistor amplifier and feed it back into the input, and you amplify a signal at a given frequency, you have something called an oscillator. What does an oscillator do? Anyone?
It oscillates.
It oscillates. At what frequency?
Whatever frequency that you are sending the electrons at. So,
which is defined by what?
Hertz?
It's defined by the two devices that you picked. The capacitor and the inductor. That causes it to oscillate at a given frequency. You take the output of the transistor of the amplifier and feed it back into the input, and it just goes around and around, and it oscillates at the frequency that is designed by the choices that you made. So if you want to change the frequency at which it oscillates, you take your tuning knob and you change your capacitor, and that changes the value of the resonant frequency. That changes the output of your amplifier. That changes that. If you can vary the frequency, that's called a variable frequency oscillator, or a VFO. Every older radio before about 1995 had a circuit in it that did that. I'll say 1975. That actually had a variable inductor and a variable capacitor that allowed you to do that. Now they typically use direct digital synthesis, which is a way of making a frequency using a computer chip. But all filters are use inductors and capacitors. If you want to filter something by frequency, you pick, for instance, let's say that I have a whole mess of frequencies. Here's my antenna, and I don't know what's coming down off the antenna. Just a bunch of stuff. And I want one set of frequencies to come through right here to the other side. If I were to draw, if I were to draw the frequency spectrum out here in the world, I would have every frequency known to mankind. It's all out there. If I only wanted to pick this particular range of frequencies, what would I do? I would build a circuit that looked like this. Here's my, it would have a high impedance, high impedance, high impedance, low impedance, and then back up to a high impedance. Well, I can do that using inductors and capacitors. So I want, let's say I start with this circuit. What frequencies would pass through this inductor, AC or DC? High frequency, low frequency. DC. AC goes this way, goes down. So I have low frequencies. That would be called a low pass filter. If I drew it the other way, and I looked at it like this, I would have AC going through and DC being blocked. And if that were the case, then I would allow the high pass frequencies to go through. If I were to draw these two graphs, then I could have something that looked like this. So here's my low pass frequency, or my low pass filter, looking at my impedances. Depending on what my high pass frequency cutoffs look like, I could have it look like this. If I put them in series, I get the sum total of them. And that's my band pass filter right there, if I put them together in series. I get just that little set of frequencies coming through, just by putting things in the right order and picking the frequency values. And fortunately, if you're ever curious about doing this, for instance, there are lots of different characteristic filters out there. There's Butterworth, there's Chebyshev. They're all based on polynomials that mathematicians have come up with over the last 100 years or so. And they're really easy to design. You just basically pick frequencies and you select values of components from that. All right. Questions about that? Nothing? No one? It's a pretty heavy stuff.
Yeah, I got a question.
Yeah.
Yeah, I wanted to know, could you repeat why there would be a certain point where you would have a low impedance?
Yeah. Okay. So you're going to answer it for me. So what happens if an inductor has a positive reactance. A capacitor has a negative reactance. Could you pick the two such that they are equal and opposite each other?
Yeah.
Okay, if they're equal and opposite, what do they add up to?
Zero.
If
Oh,
they add,
zero.
oops, sorry, I have to. Oh, shut up. There we go. Disconnect audio. So if they're equal and opposite and they cancel each other out, then the sum total is zero and there's no reactance. The impedance becomes zero. It just basically becomes the resistance of the circuit, which is usually very low. In other words, magic. It's not quite magic, but it behaves like magic. Okay. You ready to move on to the next thing? Okay, here we go. So now, let's say that we have a device that makes a frequency. And what are the components in there that cause that frequency to be made?
Capacitor and resistor.
Nope, you got half of it.
Capacitor and inductor.
Capacitor and an inductor. Okay, so you have used that F is equal to 1 over 2 pi square root of LC to figure out what your resonant frequency is going to be. You put it through an oscillator. You've done a little bit of manipulation, and you now have a frequency being generated. There's your sine wave at a specific frequency that you wanted to make. Well, now what are you going to do with it? You got to send it out into the world.
Yeah.
Okay, so we got to send this thing out into the world. That's right, we got to transmit it because otherwise nobody can hear it. So we have to send it out into the world. So now that we have generated this frequency, we have to make good. So we have to amplify it a few times. What's the basis for amplification? What do we use for amplifiers?
Transistors.
Transistor. Okay, so we have an oscillator, and we feed that into a transistor. Transistors are not particularly clean necessarily. They'll make some nonlinear amplification. You'll end up with some dirty signal. How do you filter that out? What do you use to filter stuff? Two devices. What do you use? You use the capacitors and
Diodes.
Inductors, and you filter it out. Okay, then maybe you mix it, combine it with another frequency. A mixer is another device that allows you to combine two frequencies together and get sums and differences, and then you maybe amplify it again. What do you use for an amplifier?
Transistors.
A transistor. Okay, and then it's going to be dirty, so you have to filter it again. What do you use to filter it?
Inductors and capacitors.
Inductors and capacitors. Okay, right. Okay, so now you have a signal that is big enough and ready for the world. So you started with an oscillator and you built up that signal and you filtered it, and now it's nice and clean, and your output impedance is 50 ohms. That is what your output impedance of your device is. Impedance matching is used to make sure that power signals that are being generated can be transferred efficiently out into the rest of the world. This is inside a box. Right? So for now, we're going to take this as a black box. This black box is, its only function is to do what? To produce a signal that is ready for the world, right? Okay, but it's a black box. It has a terminal on the outside. Here's our box, And here's our PL259 terminal and our connector screws to it. Right? Until we get a piece of cable hooked up to it, this doesn't do anything. So we connect our cable to it. Our output impedance of our device is 50 ohms. Our cable, in order to be efficient, we try to make 50 ohms.
50 ohms.
A matching impedance is good for transferring power from one thing to another. If we don't have a 50 ohm match, we can add a device which changes it. This is called a tuner or an impedance matching box. You might find something like this if you hook up a pair of headphones. You might see that there's a low Z, high Z headphone connection. You can use a transformer to match those. You can also use inductors and capacitors. From there, it goes up to your antenna through another piece of cable. Okay, so this is our basic system. Well, in order now to match this, we have our 50 ohm cable and we go up to our antenna. Ideally, what's the impedance of our antenna going to be?
50 ohms.
50 ohms.
50 ohms.
Yep. So if our cable is 50 ohms and our transmitter is 50 ohms, then we have the signal going up and there's no reflection and it goes out into the world and it never comes back. That would be great. That'd be perfect. We would never see it again. We would just send it out into the world and it would be converted into something. What's it converted into?
RF?
Converted into radio frequency energy that travels off into space, ripples in space, never coming back. Hopefully they get somewhere useful. All right, so what we've now done is we have tried to create a device that would convert that energy into something useful. So what does that device look like? So now what we have to do is say we have this frequency that we're generating. When it's traveling through space, this frequency translates to what? What is this wave? What is the
Sine wave.
feature of, yes, and what is the feature of that wave traveling through space? Remember that from this morning, like hours ago?
Wavelength?
Wavelength. As it's traveling through space, we have to give it some way of converting energy from a format where it basically travels up through a piece of cable and somehow ends up in a device that is the proper length to maintain a thing that looks like a wave of the proper length for when it goes into space. There are a couple of ways to do that. The first one is we're going to look at what a wave looks like. All right, so here's a wave. Now, based on the fact that we just did some electrical stuff a little while ago, here's a piece of wire. So there's a piece of wire sitting in space. Is there any restriction really on what the current can be at that particular point?
Current?
Yeah, current. Can you think of any real restriction? I mean, other than, there's so much current that it overheats the wire.
Okay,
But
other than that. Yeah.
is there any practical limitation
Oh.
for any reason you can think of?
No.
No. It could be anything, right? Well, that's at any arbitrary point. There are only 2 points. Let's see if anybody can come up with this. There are only 2 points on this piece of wire where the current has to be something in particular.
Start and the end.
The start and the end. And why is that?
It has to come in somewhere and get to somewhere.
Well, actually, it's because you cannot accumulate any charge anywhere. If you can't accumulate it, if you have current flowing this way, it has to be matched by current flowing out. It can't accumulate anywhere.
So would it start at your transmitter on your radio?
Well,
where the
essentially, yes.
antenna is plugged in?
Well, well, we're just thinking about the piece of wire. I'm not even going there yet. I'm just thinking about this piece of wire. And we're basically dealing with some very, very rudimentary physics at that point. What does the current have to be there and there? It can only be one thing.
0?
It has to be 0. Okay? And it makes the most sense for our current distribution to look like what? Take a look at that wave that we drew.
You can back up for 1 second. I'm sorry. So why does the current have to be 0 at both of those ends?
How much can flow out of how much can flow out of the end? How much current can flow out of the end?
0. There's
nothing. Anything that flows in has to come back. You can't accumulate any electrons there. And if they're not flowing off into space, which they're not, where do they have to go?
Why is it 0 at the start?
Well, at both ends. We haven't defined a start or a finish yet. We just see the endpoints.
Okay.
Because if you had more than 0, it would backfeed. Is that it?
No, I mean, it's not physically possible. How can you have current that if you have current, that means that current is moving. Where would it go? Physically, where would it be able to go?
You're saying because you can't store it in a wire?
You can't store it in a piece of wire, so where does it go?
We're saying it
doesn't get out of the wire.
It would turn to heat.
Heat and melt.
How? I mean, if there was a place for it to go, like if there was something over here and there was a high enough voltage and it arced, yeah, but there's not. So the current has to be nothing. There has to be no current at the ends.
This assumes that nothing's attached to it.
There's nothing attached to it. It's floating in space.
Okay, well then, okay.
So there's nowhere for it to go. So therefore, there must be no current. If there's no current there, and we picked a particular frequency that made a particular wavelength in space, what do you think it would make sense for that particular current waveform to look like? And the answer is...
anything, right?
The answer is that. Well,
sine wave.
A sine wave, yeah, of that particular wavelength. So it has to be 0 on this end. That translates to here. And it has to be 0 on this end. So we start drawing and moving this to here. And we get something that, if it's the right length, it'll go and will fit 1/2 wavelength on that piece of wire.
But I only want half the wavelength on the wire.
Not necessarily. But if it's any shorter than that, you'll never get to the middle. You'll only get like between here, whoops. If it's any shorter than that, you'll only get to like this much and this much. And you'll never you'll miss that entire middle part.
Okay.
So, the shortest antenna that can carry an entire piece, like an entire accurate piece, given the fact that you have to have no current at the ends, is 1/2 wave long. This is a half wave, right?
Yes.
Okay. Since that's a half wave long, a half wave antenna is the shortest antenna that can fit that. Now, could it be longer? Yeah. But a half wave antenna is the shortest antenna that will carry it correctly. This is actually really important. A half wave antenna is the fundamental basic antenna upon which all antennas begin. I won't say all, but many. Because
what was it again?
Well, it's a half wave long.
How do you know what that distance is?
What frequency am I using? What's the formula that combines frequency and wavelength? Time to go back to that. Remember this? That we did this morning. If I know what the frequency is, I know what the wavelength is. if I've picked a particular frequency, let's say I want 100, let's say I want 146 megahertz. Okay, let's do the math. What's the way?
300
Divided
divided
by,
by 146.
yep, is 2 point. Somebody got the calculator up?
I don't.
See who can beat me to it.
I
get
2.05479452005.
Okay, 2.055 meters. And as it turns out, you do have to shorten it slightly by 5%. So your antenna is going to be 1.02. Oops, no, that's not right. 2.055 times 0.95. So you shorten it a little bit, it's 1.95 meters. And then divide it by 2, and it's 0.976 because it's a half wavelength long, times 39.34 to give you inches, and it's 38 inches long. Ideally, the antenna should be straight. It doesn't have to be. We're going to get to that. So a half wave antenna for that frequency will be 38 inches long. And that's because we have that 95% fudge factor.
So let me ask you about this. Is this wavelength? Because I messed with this with a little bit with my SDR, trying to figure out what length to actually set my antenna when I'm talking about this kind of stuff. Is this more important for receiving transmissions or broadcasting, or is it equally for both?
Both. Because this antenna is resonant on how many frequencies?
So you took
one.
The frequency divided.
Oh, I lost you there.
It's resonant only on 2 meters.
It's resonant on one frequency. That's it.
146. Yeah.
Well, one frequency in that band. Now, if you were to look at how good it is on that particular band, it might look like this, depending on how it's built. You know, it might cover a very wide range pretty well.
I apologize, my screen locked up. So you took the wavelength, divided it in half, and then took off 5%.
To give me a half wave antenna. Yep.
Okay.
That's it. That's a half wave antenna. And it turns out that if you break that wire and feed it in the center.
Can an antenna be resonant in multiple frequencies, or does it really have one primary that might be kind of wide?
Well, let's ask this question. If I take some pieces of wire and do this, what will that do?
If the length of the wires are different, it would pull in different frequencies.
That's right. It would be this upper portion would be resonant on one frequency, and this lower portion could be resonant on another frequency. And if their impedances are far enough apart, you know, if that one doesn't affect the other one, it could have two dips. It could have two good resonance points.
These are all ultimately connected to the same wire coming into whatever.
Correct. So this antenna that we just drew has a name. That's a half-wave dipole. This is the fun.
Scott?
Yeah.
Scott, sorry. Just a quick question. Why do you use sometimes to calculate at length 95% and sometimes I have to use 102%?
You're always going to shorten it. I mean, you're always going to shorten it. And that's because of, you know, the wire has capacitance, the wire has self-inductance. I mean, it just turns out what I usually do is I don't start at 95%. If I'm making an antenna, I cut it too long because it's a lot easier to cut wire off than to add it.
Okay.
And I just cut off a centimeter at a time. So what we've gotten here is a half-wave dipole. This has an impedance of about 72 ohms. As it turns out, notice that 72 is not all that far away from 50, is it? Nope. So this is actually a very good, very basic antenna. This is the fundamental antenna that's at the center of all radio communications for the most part.
God, if I could ask you one more question, I don't want to get this on track, but these fairly inexpensive nano VNA devices.
They work great.
Greg, I didn't know if they were junk. I bought one. I just didn't know.
They work great. So what a nano VNA does is, okay, so a nano VNA is a vector network analyzer, and Hewlett-Packard makes vector network analyzers. There are a lot of companies that make vector network analyzers. Essentially, what a vector network analyzer does is, oops, I didn't mean to do that. I meant to do this. And I need to clear that and start another one. Okay, so a vector network analyzer is a 4-terminal device. This is on the extra class exam, by the way. So here's your input and here's your output. This is your device under test, as it's called. That's your antenna or your feed line or whatever. You put a signal in here and it goes over to here. Then you have a signal coming back and another signal coming back, and it allows you to see how much energy is going out, how much is going back, how much is reflected here, how much is reflected out here. And by doing that, it allows you to characterize a particular thing like an antenna or a piece of cable. That's that DUT, or device under test. And a Hewlett-Packard calibrated vector network analyzer can cost $50,000. A nano VNA made in China and available for $75 costs $75 and is 95% as accurate. So do the math. I have a nano VNA. It is good enough. Unless you are doing high precision measurements, a nano VNA is a fabulous tool.
You explain one more thing, and I'm sorry, I don't mean to monopolize this. One more thing related to the kind of the algorithm you just gave us a minute ago, and similar to that. So I play with that Meshtastic stuff. It's cool. It's a little bit of, whatever. But I've got a couple of antennas, right? I got something, the 900 megahertz range. How important is the ground plane, and where does that come into?
Going to that right now. Okay. Here we go. So we drew a half-wave vertical. All right. How long is a half-wave vertical, everybody? Not a trick question.
Half wavelength?
A half wavelength. Okay. So it has a feed point impedance because we can draw the current distribution like this. The feed point impedance is, what's Ohm's law, everybody? Tell me what's Ohm's law. E equals
I times R.
Right. And in this case, we can replace the R with the letter Z. But they really serve the same basic purpose. It turns out that at this feed point, Z is about 72 ohms, which makes for a pretty good match. Because this is our current, and our voltage goes to a minimum at that point. So our E is down here, going through about 0, or minimum. Our current is going through a maximum at that same point. So Z is equal to E divided by I, which is small divided by large. And what's small divided by large? Small. Okay, so now what we're going to do is we're going to empirically move our feed point way down here. Because, is there anything changing the antenna itself? Does the antenna still have to obey the laws of physics?
Yes.
Yes. The antenna is still the antenna. It's still going to behave the same way for that particular frequency and wavelength. Except that at this point, what's my current? Big or small?
Small.
Okay.
Small.
So is E divided by I, and what's my voltage? Big or small?
Big.
Big divided by small is?
Small.
Big.
Okay, so for a center-fed antenna, it's about 72 ohms. For a feed point near the end, it's about 2,400 ohms. Now,
Wow.
yeah. So, what is my coaxial cable? How many ohms?
50.
50.
Okay, so here's a little thing about mismatches. So if I have, this is the easy way to think about impedance mismatches. Let's say I have a rope, right? And this rope is infinitely long, and I lay it on the floor, and I whip it and make this, make this little bump. If the rope goes forever, it'll transfer down the line and down the line, and as it whips around, it'll keep going. And if this rope is infinitely long, what will eventually happen?
We'll come back around.
Well, no, I'll never see it again. Eventually, it'll fade away, and the rope is infinitely long. There's no reason for it to ever come back. That is an impedance. That is a perfect impedance match. It's the same material forevermore. Nothing ever comes back. But now let's take this rope and let's change it. We're going to instead take it and we're going to tie it to a doorknob. And we're going to slam the door shut. Right? And it's a good solid house. And we're going to make this, we're going to whip the rope and make this wave on the rope. It's going to propagate down the rope. And what's going to happen when it gets to the doorknob?
Going to pull on it.
Gonna bounce back.
Yeah,
to
but
ya.
the doorknob can't move because the door is slammed shut. And it will not stop. What happens to the energy?
Bounces back towards you.
It bounces back and it comes back underneath.
Oh, okay.
Right.
It will come back underneath. If I continually make signals going this way, I will continually have a train of pulses going back the other way. This is the equivalent of an impedance mismatch. And what happens is you will, if the door moves, if it's not completely, rigid, you'll have some energy rattling the door. Agreed?
Right.
Continually. But you'll have a lot of energy coming back. And if you keep doing that, you will continue to have a lot of energy coming back. That energy is probably going to eventually get to your hand, isn't it?
Yeah.
And it's going to try to make your hand do something it wasn't planning on doing. Right? Which means you're going to have to exert even more energy to keep that wave going. If this is a transformer, if this is a transmitter, what happens is that energy eventually makes its way back to it. And any energy has to eventually turn into what?
Heat.
Okay, so you have a transmitter that's getting really hot. Mismatches are bad for that very reason. Okay, so now, instead of that, we now take this system and we have created a 50 ohm cable feeding into this 2,400 ohm load right here. This is 50 ohms and this is 2,400 ohms right there where the antenna is broken in half. What will happen to most of the energy when it gets to that point? This is a door that's slammed shut.
Gonna come back.
It's going to come back. Very little energy gets out. And in fact, there's a measurement called standing wave ratio, which is the bigger impedance divided by the smaller impedance. And it's a ratio. In this case, it'd be 2,400 divided by 50, which is 48 to 1, which is ridiculous. Ideally, you want a 1-to-1 match, which means that they're perfectly matched. This is completely unusable. So, however, this antenna actually gets used all the time today. Can you believe that?
Yeah.
I mean, yeah. Does anyone know what this antenna is called? Anyone who's got a license already?
End-fed half wave.
That is called an end-fed half wave, or an EFHW antenna, or an end-fed half wave. The way that this works is that you have 50 ohms, and it transfers from that through a magic box that makes it look like 2,400 ohms. Any idea what might be in that magic box? We've already shown one.
An amplifier?
Not an amplifier. Nope.
Transformer.
A transformer. that looks like that, where you have, notice this mismatch is 48 to 1. Well, it turns out that a transformer that looks like this with N1 and N2 can also, because it changes voltage and changes current, and E equals I times R, or E equals I times Z, holds true because of Ohm's law, that the impedance matching goes up as the square of the turns ratio. So basically this is about a 7 to 1 transformer. Because what is 7 squared?
49.
49. That is very close to 48. So you take that antenna with a transformer, you put in a 7 to 1 turns ratio transformer, and voila, you have a functioning antenna and a way to feed power into it. And it's all done with magic or with electromagnetics. Okay, so we've now gotten into the point where we've done a half-wave dipole. Now, is it logical and practical to build a half-wave dipole? And let's say one of the most useful applications that we have for amateur radio is we have our car. Does anybody want an antenna that looks like this on the roof of their car?
No.
No, pretty dumb,
Not
right?
particularly.
No, that's pretty dumb. What's one reason that you don't want that? One reason you don't want that is because if you were to do that, you look at this antenna, which is a half wavelength long, looking at it from the top, your radiation pattern goes like this and like this. It makes a figure 8 shaped donut around the antenna, which means that if your antenna is
Just started.
which means that if your antenna is oriented like this, your pattern is going to be like that. If you turn your car 90 degrees, what happens to your pattern?
Oh,
What happens?
it rotates.
It rotates. Yeah, if you're trying to have a conversation with somebody and every time you turn your car, you lose them, that's not really great, right? It's not something that you want. So,
Sometime on a halfway dipole antenna. Oh.
okay, so instead, we're going to take our car and we're going to do this with it. Glad I didn't pay for that car. We're going to take just a stick and have it sticking straight up. So, looking at the roof of the car, what does that antenna look like? It looks like a dot. Right? If it's a dot, is there any difference between any of these directions?
No.
No. That is called an omnidirectional pattern. Basically, it looks like this and this in all axes, which is really kind of good, except that we have a problem. One of them is that we can take this antenna and we can make a half-wave dipole. But if that's a half-wave dipole, where do we have to feed it?
In the middle.
In the middle. Okay, this is not practical, is it? Because then that's just not practical. Well, where's another place to put it? We could feed it from the end, very close to the end, in which case, what do we have to put there?
A
transformer, because the impedance is going to be very high. This is actually a system that is used for a lot of cars that have non-metallic bodies. However, if your car has a metallic body, we have another way to do this. We can have a quarter wavelength antenna. All right, so this is going to connect to our cable. Here's another box. Here's a metal plate. Here's our car roof. So these are not connected to each other. How long is that radiator up there? How many waves?
Quarter wave.
Okay, so what does the current have to be at the end, at the very top?
0.
That's right. Okay, so we can draw that. And so far, So good. Okay, well, but wait a minute. We're missing something. What's missing?
The other quarter of the wave.
Yeah, the other quarter. Okay, so what we're going to do right now is do a little thought experiment, and we're going to put somebody way out here, right? Looking that way. There's their eyeball. And what's going to happen is we're going to assume that this is a perfectly reflective surface. And if you're in the distance, you're going to see this top part. Agreed?
Yes.
Okay. If this is a perfectly mirrored surface, what are you going to see?
The reflection of the antenna on that surface.
Going to see the reflection of the antenna on the surface. So it's going to look like there's another half of the antenna down below. Well, if the person who's looking from a distance sees another half of the antenna, it's basically there. It must be there. So this is a little bit of magic that happens if you have a perfectly reflective surface. Now, a car covered with paint is not a perfectly reflective surface, but for radio frequency energy, it is a metallic body. It conducts current. Since it conducts current, you are able to essentially gather up enough electrons in the body of the car that make it actually look like that other half of the antenna is there. It makes it look like a reflective surface, which makes it, to the outside world, look like the other half of the antenna is really there. And since the other half of the antenna looks like it's there, the rest of the world doesn't care. And as it turns out, your antenna doesn't care either. It becomes a balanced antenna where the signal is being radiated by the top part of the antenna, and the bottom part of the antenna, which is being generated by this current in the body of the car, mimics the other half. So if a half wave dipole, center fed, has an impedance of 72 ohms, any guess as to what the impedance would be here?
36.
36. It's actually 36 ohms. Now, the question is, how do you take a box that looks like this, that has a magnet in it, that looks like this? How do you get energy through a piece of plastic which is there to protect the roof of your car? There's a metal plate in here that's connected to this electrode. How do you think energy gets from the yellow line down to the body of the car? Any guess what that thing looks like? What is that? Two metal plates separated by a distance.
Capacitor.
That's a capacitor. Yes, the car is capacitively coupled to the antenna, to the ground of the antenna.
Oh, okay.
Does this work for glass also?
It can. That's how through the glass antennas work.
So
if it's not metallized.
that means you have to have enough power. You have to have alternating power for it to go.
What frequency are we operating on? Let's say it's 2 meters, 146 megahertz. It's AC. It just goes right through it. Magic. Passes right through the capacitor that just got created. Like it wasn't even there. It's like it's hardwired. Isn't that cool?
Yes.
It really is cool. That's how a magnetic mount or mag mount antenna works. Mag mount quarter wave. Now, you could also make your thing 5/8 of a wave, or you could make it even longer. And what you gain by making an antenna longer often is you gain more directionality and higher gain. Okay, so now that we have gone through that process of discussing...
Okay, but wait a
Yes,
minute.
go ahead.
So once again, I know what I'm getting with the quarter wave and the half wave. So if I make it, what did you say, 5/8?
5/8 wave, you get a lower radiation angle.
So I'm going to pull in a completely different frequency. Yes or no?
No, you pull in the resonant frequency. You pull in a lot of frequencies, just with differing success. You can make a resonant antenna that's a lot of waves long. You can make a resonant antenna that looks like this.
So as long as it's...
Where you have matching stubs or delay stubs here, so that all of these pieces of the antenna are resonating in they're resonating in phase with each other, and then their signals add together. I mean, there's all kinds of antennas are an amazing thing.
So if I made it 5/8, that means that I can pull in everything that a quarter of the wave fits on that 5/8. Is that correct?
No. What happens is with a 5/8, essentially, you have what's the current at the end of the wave, at the end of the antenna?
Zero.
It's zero. Okay, so here's a quarter wave. Looks like this. Here's the ground plane. A 5/8 wave will look like this. Then the reflection looks like this. That's a bigger antenna, right?
Right.
It has more capture. It has this entire half wave on top, and because of the additional section down there, it does some frequency. I think it does some impedance matching, and also allows you to have this bigger bottom part.
But what I mean by that is because, like, just from your drawing, then I can take a wave that's longer than that, and as long as it fits before I get to the top of the car, I should be able to pick it up. Yes? No?
I mean, you can any piece of wire will work to pick up any wavelength. The question is how well. If it is resonant at a particular frequency, it will work better than at other frequencies.
Okay.
That is actually one of the problems. Does anyone have a Baofeng?
Yes.
Okay. Does anyone know why, I'm going to say it. Does anyone know why Baofengs are garbage?
Bad receive.
No, the receiver's good, actually.
Well, what's the problem with?
Does anyone know why Baofengs are garbage? Okay.
The best video China made.
Yeah, there's a lot. Motorola's are made in China.
The antennas, you have to change them out if you want to
No,
get...
antenna's fine. What is in a receiver?
Off frequency?
Let's hook this up to an antenna. All right. What frequencies are being caught by that antenna?
All of them.
All of them, right? They're all coming down to the radio. Let's say, okay, everybody ready? I want you all to unmute yourself. Okay? On the count of 3, everybody say your name. Ready? 1, 2, 3. Scott. All right. Chaos, right? There's no selectivity. What happens is that in a well-designed receiver, you will have front-end filtering. The idea of front-end filtering is that if you are, let's say, listening to the range of 140 to 150 megahertz, you will have a pre-filter that blocks everything except for 140 to 150. So that the receiver, because if it comes down to the amplifier right here, there's an amplifier right there. Does that amplifier know what's coming in? No, it has no idea what signals are coming in whatsoever. If those signals make it to the amplifier and there's a lot of stuff that you didn't really intend to listen to, but it's making it in there, the amplifier is wasting its energy amplifying it, and you're not able to hear the stuff that you want to hear. Those radios lack completely this filtering. And that's how they can sell them for 25 bucks. They work fine in an area where you don't have a lot of RF coming in. As soon as you get into a city, they go deaf. The reason they go deaf is because now, instead of just a little stuff, there's all kinds of stuff coming in, and the one thing that you're trying to listen to is completely overwhelmed. You'll never have the ability to amplify the thing you want to listen to.
So even when you change channels, it's not filtering out everything but that channel.
No, the filtering is terrible. And coincidentally, because what does it take to build filters? What are they built out of?
Capacitors and inductors.
They're physical devices. It's the most expensive part of a receiver these days. It's the biggest part and the most expensive part. So, how do you make it cheaper?
Leave them out.
Leave them out! Exactly. And it works much of the time in most cases. But that's why they're garbage.
What is a small radio with filtering? Is there such a thing as a decent handheld?
Sure. You won't spend less than $80.
Okay.
As opposed to 20.
Okay.
What radio?
Anything that's either Yaesu, ICOM, Kenwood, or Alinco. And potentially some of the Anytones and some of the other Chinese radios, which are not, like, for instance, like the Gigaparts and QRZ sell this thing called a QRZ1, which is they sell them for like $22 for if you get a new license. If you get your first ham license, and those are actually quite good because they're $60, $65, $70 radios that they're just selling for 22 bucks for new hams. A Baofeng, any Baofeng, is a $20 radio. Even if it's in a really pretty case, it's a $20 radio. Right?
What are the ones you just mentioned that are good? But they sell for
Yaesu, ICOM, Kenwood, Alinco are the four that are out there that are, that are the solid radios that have always been.
Are Midland's pretty good on that as well?
Midland doesn't make ham gear. So, they're good. They're good for what they make, but they don't make ham gear, and I don't think they ever have.
Okay.
But that's now, having gone through just the first 5 hours of class, you understand something about what it takes to build a decent radio.
Right.
And why some radios are intrinsically better than others.
While we're on the topic, how do you feel about like the SDRs, like the Hack RF SDR? I mean, obviously that's not a replacement for any significant ham gear, but
well, I have SDRs. They're great for what they're designed for. What do you think the weakest link is?
The antenna?
No.
I don't know.
I know I can hook up. I have a oh heck, what is it? SDR. What is it? 2832. I forget what it's called already. What is it? It's anyone remember what that is?
I mean, mine's half duplex. That kind of stinks.
RTL SDR 2832. So people here. There are probably some of you who have actually gotten one of these before. Have you ever seen one of these? RTL SDR?
No.
Okay, an RTL SDR is notice how big it is. It is basically the size of a computer dongle. That's the whole thing. And essentially what it is it listens, it's a device that does a very, very high speed Fourier transform on all the signals that are coming in. It's actually an incredible little device for the price. I mean, you can get one of these for $25, $30. And what happens is you get bulk transfer of data coming into your computer at an insanely high rate over the USB port. At that time, you have software running on your computer that does all the data processing, all the signal processing, and it allows you to listen to and decode just about anything that's out there from like 0 to 2 gigahertz. It's really amazing. And I mean, like, this is literally how big the thing is.
Mine
Let's see how.
actually goes to 6 gigahertz. It's kind of insane. That being said, I haven't touched the surface of figuring it out yet.
Yeah, like here we go. Radio defined SDR dongle. And that's good up to at least 1.7 up to 3.2 megs. Here we go, up to 1.7 gigahertz. It's an incredibly wonderful device for general listening. But in a device that big, what do you think is missing? What could you not possibly build? Yeah, you can't do any filtering whatsoever. There's no room for it. So, and it's only a receiver, but the fact is, as soon as you get into an area with a lot of RF floating around, there's a lot of RF floating around, and it's completely overwhelmed.
Yeah, that's kind of the experience I had. I get just a ton of noise out of it.
The other thing is, if you hook it up to a big antenna, like I've got a 132-foot wire up above my house. If I hook one of these up to that wire, it is completely swamped. It's the same way, like the first time I had a Baofeng and I hooked it up to an outside antenna, I found that on my car when I drove down into town, I couldn't hear anything. Like, well, that doesn't make any sense. But I took that antenna off and then I went back to the small antenna, and what that did is it brought all the signals down in strength to the point where it could actually decode something. Like, oh, yeah, it's overloaded. Okay. Guys ready for a 5-minute break?
Yes.
Okay. All right, who's got questions before we get going again? Questions good.
Scott, not a question.
Hi, Kevin.
It's a comment. How are you today, Scott?
I'm doing all right.
An advantage of a 5/8 wave antenna for those people that'll be putting dual band radios in a car is that the 5/8 wave antenna will be a quarter wave on their 2 meter side and a 5/8 wave on their 440. So both sides of that radio can talk to one antenna.
Well, I just have a quarter wave on 2 meters on the roof, and that's three-quarter waves on 70 centimeters.
Yep.
And I find that, so the radiation angle is a little high, but I don't care. I work, I work the International Space Station with the thing frequently.
And you're trying to get to a repeater, which is usually up high.
Right. Well, most repeaters are fairly low to the ground, but when I'm trying to work through the ISS, that's I look for 30-degree altitude passes, and I can get into that repeater just fine.
Yep.
Because the angle of radiation is pretty high.
I'll back up.
How are you, Kevin?
I am well. We're not going to make Quartz Fest. I'm still on the planning committee, but looks like the doctor wants my attention.
How are the grandkids?
They're in here, two grandkid and one grandkid's fiance. So let's hope they're doing well.
Well, let me ask. How are you guys doing?
Dan and Bryce.
Not too bad.
We're doing pretty good.
Okay. It's a lot of material.
Yeah.
But, the thing is that I know it's a lot of material, but ultimately, this is really supplemental information because you gotta study for the exam anyway.
Yeah.
So trying to plan on taking one of those practice exams that you've linked in the email.
Plan on taking many.
Yeah.
Well, just to get used to it. When I was a kid, I was 17 when I passed my novice technician, general, advanced, and extra. And I certainly never had all the background. I studied for and just practiced the exams until I got up to the point once a month where I could pass.
Oh, okay.
And it wasn't until I got to college that a lot of this stuff started to make sense because I did electrical engineering. I'm like, oh, I get it now. So
Dan has tested already, and I know he did a lot of practice. I had to exclude myself from the VE team, but he missed by one question. So Dan, how many practice sessions have you done? Like 100?
What do you mean?
Well,
how many exams? How many practice exams?
I don't know. I did quite a few back then.
Yeah.
I haven't done much since then.
I've only done one myself.
Yeah.
Well, my philosophy and recommendation is that take practice exams, do it section by section, and then once you've done all the sections, do the whole thing and take practice exams until you're at 85%.
How much harder is the extra over the general?
Different. It's all the technical stuff. I personally think it's easier, but that's me, right? Because I have an engineering degree. For me, the math is the easy part. So, and in fact, when I was in college, I did RF and communications as my focus in grad school. So, this stuff is kind of, second nature to me.
You mentioned something about the general.
Hold on, you guys are doubling.
Sorry, did you mention doing something about the general class tomorrow or something like that, or?
Yeah, well, here's the thing. I am covering in the process of doing this. Has anyone here got their general already?
No, I haven't gotten either yet.
Jay Gutler, are you still there? Hello, Jay. I know you're still here, Jay.
I'm here. I'm just sanding on a piece of wood. So,
how much general class material am I covering, would you say, already?
You're covering a lot. This is, it's the I'm learning a lot, and I've got my extra. So it's a good amount of material. But to give Scott his due, he's putting the pieces together better than I've seen a lot of other courses. And just taking the test exams and all that sort of thing and reading, you don't get the connection. And I think that's what you're getting here more than what you get anywhere else.
Yes. I can second that. And I'm trying for my general, and the part that's killing me is the digital stuff, all these pieces and parts and the PSF and all this. That's the part that's just killing me.
All right, well, you all ready to get going again?
Yes.
And, I'd say let's follow along in the book, but I'm not really following the book in this right now. So, the book is there. We're definitely going to be back to the book in a bit, but so, and here's the thing. I don't mind digressing. In fact, I kind of like digressions because it makes me think in ways that I haven't necessarily thought of, Like really good questions really get me thinking about how I want to teach. So I really appreciate all that input. Okay, so now we've got signals that are coming down off of our antenna. And one thing that's important about antennas is that antennas are something called reciprocal. Reciprocal means that the receive pattern is the exact same as the transmit pattern. So if you want to think about why certain antennas work better than others, here's how an antenna is designed, right? So let's say you have a little piece of antenna that's carrying a certain amount of current. You look at some certain point in space and see what the fields that are generated at that point. Then another one, and then another one, and then you add all of them together, all those contributions, and then you can figure out all those contributions from all those little pieces of antenna, and then you take that spot and you do the same thing for a bazillion different locations. And what that does is that it gives you a 3D representation of what your pattern looks like. The easy way to think of it, however, is just the fact that a dipole antenna has a donut-shaped pattern around it. It's perpendicular to the wire. A vertical antenna, like this, will have part of that donut. How much of the signal is actually transmitted along the direction of the wire? None. So, if there's one takeaway from antennas and radiation patterns and things like that, it's that along the axis of a wire, you typically get no radiation at all. So, this is actually really important because if I have an antenna that looks like this, it's going to be strong broadside to it. My signal is going to go that way. Now, if it's in 3 dimensions, it's also going to go straight up into the sky and straight down into the ground, right? Do those do you any good whatsoever?
So why would you want a horizontal antenna?
Because you can rotate it. And because a vertical typically, let's say you do a vertical, right? Here's a vertical. Typically the pattern is going to look like this, which is fairly low angle of radiation. It's in all directions. The problem is it's in all directions, which means that it's picking up signals from everywhere. A horizontal dipole is going to be more selective. This vertical antenna is going to be picking up stuff from all directions, and as it turns out, this is going to be, because of the direction of the wire, a vertically polarized antenna. A lot of noise sources in the world are vertically polarized, which means it's going to be really good at picking up noise. But at the same time, the radiation angle is fairly low. So now we're getting into the next section of class, which is the fact that we now have, oh, come on, where'd it go? There we go. Okay, so the Earth is a sphere. Radio waves travel along the surface of the globe, and as the globe drops away, well, they will, go into space unless there's something there to block them. I think everybody would agree with that. Some of them go up. Stuff that goes straight up does almost no good. Stuff that goes along the horizon, typically the most useful for most of the stuff that we do. So, as a result, we like antennas that put out signals as low to the horizon as possible, usually. A vertical is actually very good for that, so you trade one thing for another. You can also, for instance, if you have, looking from above, 1, 2, 3, 4, you can have these verticals, which have radiation patterns that look like this, What you can do is you can use different length feed lines to feed them, and that causes them to be fed in phase and out of phase, which tends to make them add in this direction or this direction. And this is called an array factor, which makes them work better than just a single antenna. This is actually an antenna pad. This is actually known as a foursquare. You need a little bit of land for it. You need some poles. It only works for one frequency or one set of frequencies, but it works very well for that. I personally have never built one. I know people who have. They tend to like them a lot. So, moving on from that, we can have another set of antennas. Here's a half-wave dipole. We can put a longer element behind it. This is known as a reflector. And another one in front of it. This is known as a director. These are parasitic elements. They are not, power is not delivered to them. Power is only delivered to the half wave in the middle. What happens is that the signal that comes back this way and the signal that goes back this way, the power that goes backwards is absorbed and re-radiated in the forward direction. The more parasitic elements you have, you basically develop a parasitic array, and you get more and more power going in the forward direction. That makes your antenna pattern look like this, with a tiny little lobe in the back, compared to a dipole, which would basically look like this. So obviously this extra differential means that you're doing more with your antenna in the forward direction. This is known as a Yagi. There are different forms of beams. It's a form of a beam. There are different forms of antennas that are not Yagis, but Yagi is the most common. So a way of, it's important that we cover this right now because there's lots of reasons to be covering it. Okay, so we have factors of 10, powers of 10, like 10 squared. All right, what's 10 squared, everybody?
100.
100. Okay, excellent. What's 10 to the minus 2? It's 1 over 100.
Ah.
Okay, so the negative power means that it's still positive, but it's smaller than 1. Okay, so important to note, 10 squared times 10 to the 4th is 10 to the 6th, because we're just adding zeros. So with the same base, the exponents add. This is the basis for what we call decibels. So Alexander Graham Bell, just like it turned out when dealing with earthquakes and things that were orders of magnitude bigger, figured that signals, because some are very, very small and some are very, very big electrically, it was determined that they needed some way of coming up with a shorthand method of keeping track of all those zeros. Well, it was determined that if we did something like this, the log base 10 of something k2 over k1, this is the end point, and this is the reference that we start with. This is a way of figuring out how many times bigger on a logarithmic scale something is than a reference value. So if we start with 1 milliwatt and we end with 1 watt, how many times bigger is that? What's 1 watt divided by a milliwatt?
1,000.
1,000 times. Okay, so log base 10 of 1,000. That means 10 has to be raised to what power to get 1,000? 10 to the what
3.
power is 1,000? That would be 3.
3.
And Alexander Graham Bell said, we're going to call those bells because we're going to name them after me. So that would be a gain of 3 bells. Well, as it turned out, what ended up happening was that the decimal points were kind of annoying, and a bell was actually kind of a big thing. So they said, well, let's just take that and we make it 10 log base 10 of k2 over k1. And we'll call that a deci, which means a tenth bell. So now we can do the same thing and say that this is 10 log base 10 of 1,000 is 10 times 3 is 30. And we use the ubiquitous dB for decibels. We can do this in positive numbers. We can do that. We can do this in numbers greater than 1. We can use it in numbers less than 1. What's really useful about this decibel stuff is that decibels allow us to very quickly come up with an approximate change without really doing any heavy-duty math. So let's say we have a transmitter and we're going to reference it to 1 milliwatt. That's our reference point. And our transmitter is 30 dBm. So if it's 30 decibels bigger than a milliwatt, that means it's a 1 watt transmitter, because it's 1,000 times bigger than a milliwatt. And we now have a piece of coaxial cable, and that has a loss of minus 10 decibels. And we have an antenna that has a gain of 5 dB. And we have a signal that goes through space, and our path loss is minus 140 dB. And we have a gain antenna here of 5 dB. And a cable loss of minus 10 dB again. And how much signal gets to this receiver? Okay. Well, as it turns out, decibels are really cool because decibels are a way of just adding things together, and that's the same thing as multiplying in the other world. So our exponents add, it's the same thing as multiplying. So compared to a milliwatt, we're going to start by going plus 30. And then what are we going to do? Minus 10, plus 5, minus 140, plus 5 as we go around the loop, minus 10. What do we get? Let's see, 30, 20, 25. 25 minus 115 minus 110 minus 120. Did anybody else get minus 120 dBm? Anyone? Did I do it right?
I think you added 5 instead of deducting it at the end of it.
No, well, that is an addition. Those antennas are gain antennas, so those are adding.
Huh.
So this is a plus.
I'm kind of lost, so.
Well, we just go around. We start at 0, and we just work our way through the whole circuit and add our decibels together. So plus 30 is the gain in the transmitter. Minus 10 is the loss in the cable. Plus 5 is the gain in this. Negative 140 is the loss in the path going through space. Plus 5 is that antenna, and minus 10, which means here's our antenna, here's our received signal strength. So we have a signal strength of minus 120 dBm. That's compared to a milliwatt, which is minus 150 dB compared to a watt. Anyone want to guess how many watts that is? That's how much power is getting to the other end. Is that a usable signal?
That's a really
no, it
small
is.
signal.
That's perfect. You can use that. Minus 120 dBm, that's a perfectly usable signal.
Really?
Yes. That is how much sensitivity and gain receivers have today. That is a perfectly acceptable signal. Using amplification, using filtering, that is a perfectly good signal. We're down into the, not pico, what would that be? Exa? No. Yato? We're down into the ridiculous. We're down into the ridiculous number of watts. That is still a usable signal. That's how much energy is coming down the antenna, and you can still listen to it. Crazy, right?
Yeah.
Yeah. Okay, but what this system has done, what the use of decibels has done for us, is keep us from having to maintain all those extra zeros. So here's the fundamental takeaway from this. 10 dB is 10 times. 3 dB is 2 times. Using those, you can do almost anything, either bigger or smaller. And I can prove this by saying, let's say we have an amplifier that has a 1 watt drive and 852 watts out. We want to know, what is the gain of our amplifier? Okay, so using 10s and 2s, starting at 1 watt, how would we get up to something close to 852? I need a volunteer. Oh, come on, somebody.
I'll bite because I'm lost, so I'll bite.
No, you're not lost. Okay, we start at 1 watt. What's our first step? We want to end up at 852 or something near it using 10s and 2s. Multiplying. What would our first thing be? We go from 1 up to
10.
10. Okay, how about the next step?
We'll
go to 100. Okay,
100.
Next step.
If I'm only going to 852, more hundreds.
Oh no, because the next one would take you to 1,000.
8.
8.
All right, how do you get 8? By 10s and 2s.
So 3 and 3?
No, you can't do by 10s and 2s only.
Oh, 10s and 2s.
2 times 2 times 2.
2. Yeah.
Right, so 200, 400, 800. That's pretty close. Okay, so this, from going from 1 to 10, how many decibels is that?
10.
10 decibels. Yeah.
Yep. Okay. And going from 10 to 100?
Another
Remember,
10.
it's just a ratio. Yeah, that's another 10 decibels. From 100 to 200?
3.
That's 3. Going from 200 to 400?
3.
Okay, going from 400 to 800?
3.
Add them together.
29.
That's it. Okay, so now we're going to see what the math says. And let me unshare this. Stop share, and I'm going to open up my calculator. And here we go. We're going to share my calculator. Okay, we're going to make sure we're in scientific notation. And we're going to say, okay, so we had 852. That's our ending point divided by 1 is 852. And we want to take log base 10 of 852. So we'll go to log and multiply that by 10. And what do we get?
29.
29.3. Good enough for government work, as they say. It's about a 29 dB gain amplifier. Very useful.
Can you go back to your drawing and do it one more time? Before the calculator, what you had up just before the calculator.
Like that?
Mm-hmm.
So let's say somebody gives you an antenna and it has a gain of 6 dB compared to a dipole. What is 6 dB? It's 3 dB plus 3 dB. Agreed?
Yes.
Okay. Every time you use 3 dB, what does that mean for your power?
That you're going up 2 times.
Okay, so if I start with 1 watt and I multiply by 2, and I multiply by 2, my 1 watt appears as how much?
6.
No.
I'm
Multiplication.
sorry, 4.
Multiplication. 4 watts. In the highest gain direction, my 1 watt appears like 4 watts. So let's say I had an antenna that I had let's say I have a 1 watt transmitter. All right. And I put this through a 30 dB gain power amplifier. And I took this and I put it through a dish antenna and I aimed it at the moon. Okay, and this antenna, compared to my wavelength, is very, very big, and I had 30 dB of gain. Okay, how much power do I have coming out of that amplifier if I have 30 dB of gain? What is 30 dB?
It would be...
That's 10 dB plus 10.
Plus 10.
Plus 10.
10.
And every time I have 10 dB, that's how many times?
10 times.
Okay, so I have 1 times 10 times 10 times 10 is?
1,000.
1,000 watts. Effective radiated power in the forward direction. Right, well that's actually 1,000 watts RF. Okay, and I have that feeding into my dish. What do I get out of my dish?
30 dB.
Which is?
It'd be the same thing.
Which
again.
is? Yeah. Times what?
30,000.
1,000 times 1,000 is?
Million.
10,000.
It is not. 1,000 times 1,000?
Sorry, no. I'm looking up above. Sorry, I was looking up at the other part.
1,000 times 1,000?
A million.
It's a million.
It's a megawatt effective radiated power. What was my original transmitter?
1 watt.
And what's my effective radiated power heading up toward the moon?
1 million.
1 megawatt. Yeah. Would I want to be pointed would I want that to be pointed at my neighbor? Unless I maybe didn't like my neighbor.
Yeah, maybe if you don't like him.
Yeah. So, any questions as to why? And by the way, are you allowed to do this with a technician license?
No.
Hell yeah. Absolutely. Any questions as to why you got to take a test?
So you don't fry your neighbor?
So you don't fry your neighbor. Yeah. There are plenty of ways to kill people using RF.
But you cannot prove this one.
No, you can't. The autopsy might show something interesting. It's hard to say. You know, somebody cooked from the inside. I mean, that's how a microwave oven works.
Yep.
That's actually right next to a ham band. We're allowed to run 1,500 watts up there. This could actually very well be right next to a microwave oven band. So this could be at 2.4 gigahertz. That's enough to resonate water molecules and cook a lot of things. Probably wouldn't want to do that though. You didn't hear it from me. Okay, so now that we've covered decibels, time to cover propagation. Here we go with propagation. Okay. Does anyone remember what the frequency limits are for VHF and UHF and HF? This is like super important. Anyone remember? You can go back and
Right off.
commit these to memory. What are those? Say it out loud. Oh, come on. Somebody say it out loud.
I'm looking
VHF
back at
is
the chart.
3 to 30, 30 to 300, and 300 to 3 gig.
Yep. So HF is 3 to 30 megahertz. VHF is 30 to 300. UHF is 300 to 3,000. Super important because they behave totally differently. We have bands in every one of those. They all behave differently, so it's important to understand how they behave and why. Okay, so the first one we cover is VHF and UHF. And so we're going to start with VHF and UHF. All right, so does light go around corners? Yes or no?
Sure does if you got mirrors.
Without mirrors.
No.
Light travels in straight lines, right? That's why we call it that's why we call it line of sight, right? Because light travels in straight lines. Radio waves also mostly travel in straight lines. They can refract around certain things, so can light. Light can actually, if it hits a sharp object, it can actually bend slightly, but that's because it bends slightly. Radio waves, when they travel along the surface of the Earth, can also bend slightly. The longer the wavelength, the more they bend. That's known as ground wave. For VHF and UHF, they typically travel in straight lines. So we're going to build an antenna that looks like this. Everyone remember what that antenna is called?
Yagi.
That's a Yagi.
Yagi.
Right? And this would be 1, 2, 3, 4, 5, 6, 7 element Yagi. Okay, so this has a gain of probably 12 dB in the forward direction. Okay, so we're going to transmit with our Yagi from here up into space. So this is now essentially very similar to what happens when we're dealing with outer space. The atmosphere is largely transparent to VHF and UHF, which means that those signals that we transmit, we're going to draw the lower levels of the atmosphere. So here's the tropo, which is where we live. And then we're going to change colors. Then there's the stratosphere. And then above that, we have something even lighter color. We have the ionosphere. So VHF and UHF signals will typically just pass right on through the troposphere and the stratosphere, which makes them very useful for doing what?
Moon bouncing.
Moon bounce, yes, and also talking to satellites. Yep. Because when you're talking to a satellite is typically going to be up here above the bulk of the atmosphere, which means your signal, you want it to get through the atmosphere. Not always the case. Sometimes you get this thing called a tropoduct because you get temperature inversions up here in the upper atmosphere, and it can actually change the refractive index, kind of like what happens when you're looking down the highway on a hot day and you see a reflection of the sky and the road. The signal will basically bounce around and get trapped there and come out a few hundred miles away. There's also something called troposcatter, which is another mode of propagation where you basically get signals that come up here and hit a layer of the atmosphere, and some of them will actually scatter in forward and reverse directions. That's typically on the 2-meter band. On the 6-meter band, you get a little more interesting stuff. You get this, the ionosphere is split into layers called DE, F1, and F2. The E layer and the D layer are usually quite boring. However, the 6-meter band, the E layer can actually become heavily ionized and bounce signals down. We call this sporadic E. This is typically good for about 1,000 miles on a VHF band that's usually line of sight. So it's kind of interesting. And this is on the 6-meter band. The 6-meter band is also good for auroral propagation, which is literally, I made my first ever auroral contacts. I believe it was last May when we had the really big solar storm where you could see the aurora. I pointed my antennas, or I picked the antennas where I was pointing essentially my signal north to the aurora, bounced the signal back off the aurora, and was able to hear other people doing the same thing. And it was really, really weird. It was very cool. Another thing is that when meteors travel through space, they're running at a high rate of speed. When they hit something like the atmosphere, they burn up and they leave a trail of ionization. The 6-meter band can be used for bouncing signals off of those meteor trails. We call that meteor scatter, which is one of those things that I have never done before and is still on my list of things to do. The 2-meter band, again, is not terribly interesting with regard to most of those weird things. The 70-centimeter band is in UHF, and with the exception of tropoducting, there's not a lot to get in the way. So given the fact that the 70-centimeter band basically passes through everything, that is the one, along with the 2-meter band, that are most commonly used for talking to satellites. So most satellites operate in something called mode UV, which is 70 centimeters going up and 2 meters coming down, because those signals will typically pass right through the atmosphere like it's not even there, which if you're looking for reliable satellite communications, that's what you want. You don't want your signals bouncing back to Earth because they didn't really do anything for you there anyway. With regard to the high frequency bands, this is where we get really interesting, because the high frequency bands interact a lot more with the atmosphere. So we're going to erase this stuff, and we're instead of using that big Yagi, we're going to instead just put up a dipole or something. So this dipole, let's get rid of this. We're going to have to draw a new troposphere. What ends up happening with the HF bands, high frequency, is that we end up having signals which are impacted by interaction between the sun and the Earth. So we're going to draw the sun up here, and the sun is this big ball of nuclear reaction up in the sky. And so what are the things that come out of the sun? Let's hear some things that come out of the sun.
Solar flares.
Solar flares. Okay, other things.
Radiation.
Okay, what kind of radiation?
UV.
A lot of UV. Yep, UV is a great
entire spectrum.
Well, yeah, okay, but that's too easy. That's a catch-all. Give me some other things that come out of the sun in great volume.
Like gamma rays.
Gamma rays, yeah, okay. Other things? A lot of X-rays. We have visible light, infrared, other stuff.
Microwaves.
Heat is, yeah, we got radio. Sun is actually a big emitter of radio waves. Makes a lot of noise. Okay, so we got all kinds of stuff coming out of the sun. Radio waves they make it down to Earth typically, but we're going to ignore them because they don't make any difference up in the atmosphere. Infrared, that causes heating, but it doesn't actually do anything up in the upper atmosphere. Visible light, it makes it to the atmosphere, but it doesn't really do anything that interesting. So now what we're left with is gamma rays. Well, I can't really do a lot with gamma rays. So we're going to erase the gamma rays. So what are we left with?
UV and X-rays.
UV and X-rays, okay. So these are the ones that have, I don't know why I can't erase that V. There we go, I erased the V. So gamma ray, or X-rays and ultraviolet. Okay, what do we know about radiation? The energy of radiation is proportional to its frequency. The higher the frequency, the higher the energy. And energy comes out of the sun in the form of photons, extremely high energy photons, which are packets of energy. And let's say you have all these little photons that are coming down toward the Earth's atmosphere. What is the Earth's atmosphere 99% made of?
Nitrogen.
And 78% nitrogen.
Oxygen.
21% oxygen. That's it. The rest of it is just water vapor and some argon and some other stuff. So the largest components of the Earth's atmosphere are nitrogen and oxygen. What happens is you get all these photons that are flung toward the Earth in immense numbers. And you have oxygen and you have nitrogen in large quantities. The higher the atmosphere, the higher you go in the atmosphere, the lower the density, but they're still there. So you have lots of oxygen and lots of nitrogen and lots of oxygen and lots of nitrogen. So it is a good thing that we have this atmosphere, because if we didn't, the Earth would be a sterile place, not to mention the fact that we couldn't breathe at all. But basically, all that radiation would completely sterilize the planet. So the X-rays have higher energy. They tend to penetrate further than the ultraviolet rays. What ends up happening is when a photon comes along and it strikes, let's say, an oxygen atom, what happens is that it has enough energy to take an electron and fling it loose by transferring the energy to the atom, so that you end up with an oxygen ion, positively charged, and a negatively charged electron, which is then floating loose. This happens in the hundreds and hundreds of millions of times, billions of times, every day, continuously. So you have nitrogen and an electron, and we can pretty much ignore the ions, but notice what we do have that we do care about. And the lower you go, the higher the density, because the thicker the atmosphere. So you get all these electrons floating around. What is electromagnetic radiation? What are radio waves? There's two parts of it. What are those parts?
Electromagnetic.
Electric field and
magnetic
field. What happens is those electric fields and magnetic fields, when the signals that you send, that you create, go up into the atmosphere, they interact, if you're lucky, with those electrons that are floating around, which essentially can just let it pass through. They can absorb the energy. They can absorb the energy and re-radiate it, like a mirror. The F2 layer is between 250 and 600 miles up. The angles that you are able to achieve mean that that signal that goes up into the sky can emerge back on the surface of the Earth 2,500 miles away. So what do you think happens at night?
Well, you lose a lot of that interaction, right?
Well, the sun's not ionizing anything anymore. And what happens to the ions that are left?
They'll recombine with.
They'll recombine. Yeah, exactly. They will eventually find their way back to the atoms that they started with, or more likely atoms that they didn't start with, but they don't care. Every atom's the same. Every electron is the same. And your density will go down, which means that at night, your electron density, your free electron density, tends to fade. So these numbers, let's say, these numbers will go down and you'll start to lose stuff. And it turns out that the ability of the sky, the ability of the ionosphere to reflect or refract waves is proportional to the frequency at which you're using it. So the higher the level of ionization, the higher the frequency at which they work. Which means that during the daytime, the 10-meter band, for instance, would be great. As the ionization tends to go down at night, what you'll find is that the 40-meter band is great, and the 10-meter band is completely dead as soon as the sun goes down. The other thing that's happening is that the D layer, which is the really low layer, this is built up during the day very strongly and performs an absorptive effect on everything up to 10 meters. Or sorry, up to 10 megahertz. So what ends up happening is that during the day, this forms a block on anything 10 meters or 10 megahertz and below. This is why AM radio stations cannot be heard outside of your local area during the day. But as soon as the sun goes down, you can hear AM radio stations, which are in the 0.5 to 1.7 megahertz band. You can hear them from 1,000 miles away.
Scott, I think you covered this early on, but these signals, these basically move at the speed of light, right?
They all move at the speed of light.
So you're talking almost no time to get from one end to the other.
That's exactly right. It's almost instantaneous.
It's amazing.
Yep. So that means that there are day bands and night bands. If we look at the spectrum, if we look at this chart, everybody see this chart?
Yeah.
10 meters. 10 meters is going to be good when the sun goes through 11-year sunspot cycles. We're coming down off the peak. When you're at the peak, 10 meters is great during the day. 12 is great, 15 is great, 17 is great, 20 is good pretty much round the clock. As soon as night falls, these bands start to fade and you start to get into the nighttime bands, which are 30, 40, 60, 80, 160. When you are at the sunspot minimum, you will have entire years where you'll never hear a signal on the 10-meter band or the 12-meter band because there's simply not enough ionizing radiation coming out of the sun to work the atmosphere up to the point where it works. At which point, 15, 17, 20, 30 are good during the day, and then 40, 80, 160 at night. And this is part of the fun of getting on the high frequency bands, is being able to actually experiment with and try to work on, figuring out what bands are going to work to what parts of the planet on any given day. And this is collectively known as propagation. Questions?
So does the direction you point your antenna in take advantage of any of this?
Makes a huge difference. So allow me to demonstrate a little bit of a cool tool out there. Okay, so this is a website called PSK Reporter. And what PSK Reporter is it uses a mode called FT8, which is a digital mode. We're going to take a look at all the signals that have been received by the grid square, CN84, which is where I live, over the last 15 minutes. Come on. Come on, you want to show me. There we go. Okay, so each color represents a different band represented by here. So let's take a look at one particular band. So let's look at the 10-meter band. So notice that we have a lot of signals down into South America, a lot of signals into Japan, into the Southwest Pacific, and then, what do you notice about this? Somebody give me an explanation of that. It's a pretty tight grouping, isn't there?
Is that a repeater?
No. Why is it such a tight grouping?
Are they key?
Why is it such a tight grouping?
No idea.
Somebody take a guess.
Directional antenna.
Nope, not directional.
Or are they key maybe?
Because they're in the dark.
That's what I was going to say. The sun's down.
No. Well, yeah, but there's still enough there's still enough ionization up there for it to be supported. Why such a grouping? Think about geometry. Think about what those signals have to do in order to get from where I am out on the West Coast to where those are. They all have to bounce at about what? About the same angle, because they're about the same distance, right?
Gray line propagation.
Yeah, no, any steeper to get a shorter coverage, for whatever reason, they're punching right on through. Anything less steep, they're not making it, which means that we have a really tight grouping of different distances for which this particular band is working right now. This is physics in action. This is what happens on the air. If we pick a different band, notice that it's not the same, right? This is a 12-meter band. It's actually right next to the 10-meter band, but we have a completely different picture. It's because on that particular frequency, it's behaving totally differently. On the 15-meter band, notice it's way more spread out. It's not behaving the same way.
Is the grouping you're talking about on the right side or the left side? Are you talking about the
On the right?
Oh, okay. I was misunderstanding.
Oh, look at the.
I see what you mean now.
Hold on.
Yeah.
Here's 10. Look at the cluster. They're all within about 1,500 to 2,000 miles, as opposed to, let's say, this band, which is 20 meters, which is all over the place, right? They're all spread out. The reason they're all spread out is because we're dealing with geometry of what the atmosphere is doing. And
looks like they're hitting more close to home. Like there
that's
weren't a
true.
lot going down California, San Diego, straight down, like very close when you did the 10 meter. But that one, they're hitting far away, but they're also hitting close.
Depending on what stuff looks like 500 miles up. Okay, but now look at this band. This is the 40-meter band. This is a nighttime band. Why is this doing that? We're hearing almost nothing out west, but I'm able to hear stuff back east. Any guess?
It's nighttime over there.
It's nighttime. And halfway in between us, it's nighttime. So those signals are getting up. It's still nighttime where they're bouncing off the sky, and they're able to make it all the way to me. If we go to 80 meters, which is the next band down, oops, I stopped the share. Come on.
There it is.
There we go. Okay, what do we hear on 80 meters? One lonely station up here in Alberta.
Yeah.
Where's everybody else? I guarantee you they're there. If I take a look at what's happening back east, you ready for this?
Mm-hmm.
Come on, everybody, show me. You're not going to show me, huh? It's going to be that way. Well, okay, we're going to start it again. What do you mean unable to fetch? Don't give me that. Okay, so I got a problem with the website. Okay. Well, unfortunately, that's not working. But what's interesting about it is that this is continually changing from minute to minute every single day, from season to season, from day to night, literally from hour to hour, minute to minute. Everything changes. There are also other tools that we use to determine what things are going to look like. So let's see, 9 alpha, right?
Yep.
Okay, so there's 9 alpha. And here's us. And if I'm running CW and I'm running, let's say, QRP, show me when I can talk to you. So this shows me around the clock on what band I should start listening to in order for it to work out.
That's slick.
Isn't that cool? This was paid for by our U.S. government. This is VOACAP. It's Voice of America Capacity Project. It was designed for figuring out where to point our antennas and with what kind of power in order to be heard and propagate we'll call it propaganda into other places. Every country does it, but they made it available to everybody. It turns out that it's really useful for amateur radio, especially if you do something like, we go to, Like I spent I spent 2 weeks on Wallis Island, which is in the South Pacific, and we were trying really hard to work into Europe because very few people in Europe have ever worked that place. So this said, okay, we're running 400 watts, so we're just going to say 500 watts. Show us the hot spots where we need to be and when in order to work Europeans. So there you go. We had 6 hours every night to work Europeans, and it was awesome. It was a
Now,
nonstop.
what are you looking at? I see the bands, the 10, 20, that part.
Yeah, and here's the clock. 0, 1, 2. This is in universal time around the outside. So you look for the red. You look for the red zones. The red zones give you your highest probability of making a contact. So you pick your band, you pick your zone, and you go for it.
So then you would put this on your state and then figure it out from there. That's how it works.
Well, I mean, like let's say I wanted to work into the Indian Ocean. All right, so I'll pick me, and then I'll put my dot somewhere in the Indian Ocean, and here we go. We'll go with Sri Lanka. Okay, so going the short route, which is over Asia. These are the hot spots to get into Sri Lanka. It also does cool stuff like, say, show me the other path, which is the long path, which is over the South Pole.
Yeah, you only have one. That's it. Yeah.
Except that I actually have a better chance of doing that. Because as it turns out, that 10-meter band, if there's somebody on the other end, that's a much greater chance. And of course, all of this is then just a starting point. You have to work from there to figure out what's actually going to work. Which is why it's so much fun.
If I'm in Alaska and I want to try to talk to Nebraska.
Are you in Alaska?
Yes.
Well, there you go. Okay.
And
good. This is a practical starting point.
Talk to someone in Nebraska.
Let's do that. Okay, where are you? Anchorage, Fairbanks.
Talkeetna. So I'm between the two.
Okay, like about here?
Yep.
Okay, and you want to talk to where?
Nebraska.
Nebraska. Okay, we'll put you somewhere in Nebraska, which is right about there. Let's see if I hit the dot. Well, I'll go with Omaha. Okay, and we'll go with short path because that's going to work a lot better. We'll knock you down to 100 watts on single sideband, and there you go. There's your propagation. This tells you your hotspots.
That's a handy tool.
Yeah, it's really cool. That's your starting point.
40 meters.
40 meters.
60.
Yeah, well, 40. Because there's no sideband on 60.
Okay.
So 40 meters from like 2300, which is 3 p.m. here, and you're what, 2 hours behind?
I'm an hour.
An hour. So 2 in the afternoon to 6 o'clock. From 2 to 6 on 2 to 7 on 40 meters.
Okay.
And then on 80 for a few hours at night.
Cool.
Yep. There's all kinds of cool tools. Other questions before we move on? Anything you want to ask? You know what? While we're doing that, you know what I would like to do? I would like to, considering that you all have survived this long, and we have talked about a lot of different things. We have a lot of stuff still to cover, but I'm going to very briefly talk about feed lines because feed lines are very important. But then we're just going to take a few minutes and go around the room, and you can all introduce yourselves because you're already the survivors. So kudos to everybody here for asking so many great questions and for still being here. So okay, so feed line loss chart. Okay, loss chart, loss calculator. There we go. Okay, I want to bring that page up. And I know you probably can't see it, which is fine. Okay, so there we go. Feed line loss calculator. Okay, Notice that every antenna that you buy and every feed line that you buy, everything is measured in what units? Everybody.
Ohms.
No.
Hertz.
Yes.
Decibels, 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 decibels. And what's great about decibels is that they apply to everything. They apply to antenna gain. They apply to coax cable loss. They apply to power amplifier gains and preamplifier gains. Everything's measured in decibels. When you buy an antenna, it's measured in dB of gain. The front to back ratio is measured in
Decibels.
decibels. The front to side ratio is measured in
Decibels.
everything's in decibels,
Decibels.
right? It is universal, which makes it really easy to deal with. Okay, so these cables that are listed here are all 50 ohm cables. These all are coaxial cables, which means they have a center conductor and a ring around the outside. The RF fields, magnetic and electric, exist in between them and propagate from one end of the cable to the other. Notice, let's say we take let's say LMR 240. At 3.5 megahertz, the loss is 0.45 dB. As you go up in frequency, what happens to your losses?
Climbs.
It goes up, yes. Now, okay, so important thing to note, as frequency goes up, your losses increase. As the size of the cable goes down, your losses increase. So LMR 400 is great cable for very, very high frequencies. Look at RG58. Look at RG58 at 9.9 feet. What's the loss? Or sorry, at 440 megahertz. What's the loss?
9.9.
That's 10 dB, right? What does 10 dB mean?
You lost all the signal.
That means if you put in 100 watts, how much gets out the other end?
What?
No.
1,000. One.
No. What is 10 dB, everybody? How many times? Remember, you only got to remember 2 things. 10 times. So if you lose 10 dB and you start with 100 watts, how much comes out?
10.
10 watts. Where's the other 90 watts?
Heat.
It came out as heat. It heated the cable, right? So if you're trying to keep your cable from freezing, sure, that's great, but it doesn't come out as power. Let's go with LMR 400 at that same frequency. How much power gets lost?
2.7.
So if you put 100 watts in, you lost about 3 dB. What's 3 dB?
Times 2, so
That's half.
50.
Yeah. That's half because it's loss. So 100 watts in, how much makes it out?
50.
50. So just by picking a different cable, you either have 10 watts out or 50 watts out. Depending on how long your cable is, that could make a very big difference because this is per 100 feet. So if you have a 3-foot piece of cable, no big deal. If you have a 200-foot run to your tower, it's a really big deal, isn't it?
Lost a lot.
Because they add up.
Got one question. What's the benefit between the different cables?
Well, okay. So the benefit between different cables. Well, okay, so let's talk about cable very briefly. And so this is what coaxial cable looks like. Right? You have the shield and you have the center conductor. In between the shield and the center conductor, you have a dielectric material, which is basically like polyethylene or air or any number of different things that give you insulation. And the spacing is continuous, so that if you have the center conductor and the shield around it, you have 2 metal plates. What do those form?
Capacitor.
That's a capacitor. And because you have a piece of wire that has inductance. And actually, they're not drawn quite like that. They're actually drawn kind of like this. So it's actually drawn like this. So, whoop. So you have an endless series of inductors and capacitors, and they are not burning up power, but what they are doing is they're giving you a characteristic impedance, each pad, because you can split your inductors and capacitors up into pieces, they basically will give you a characteristic impedance based on the spacing between the two. So a cable that's that big versus a cable that's this big, so long as the proportions are still the same, can still be 50 ohms. So a cable that is as big as your arm, it can be 50 ohms. A cable that is as small as your pinky finger can still be 50 ohms. A cable that's as small as this pencil tip can still be 50 ohms. Because the proportions are what defines it. So now, given those things, which one can handle the most power?
I would think the bigger one.
That's right. And it also has less loss because of Ohm's law. A bigger conductor is going to have lower resistance, period. So the bigger the conductors are, the more power it can handle, the less loss you have, the less heat it generates. Any questions about that? There are other forms of feed line, as it's called. You can have two wires in parallel separated by a spacer. This is called ladder line. The reason that I use ladder line is because these are physically separated by a distance in air. That is they're very far spaced. The losses are extremely low, on the order of like 0.1 dB per 100 feet.
Hard to keep. The wind moving around too much.
I don't care.
Does moisture?
Water does actually change things a little bit. So the measured standing wave ratio actually will change based on whether or not they're wet. So there's also something called standing wave ratio. Standing wave ratio is a measure of how well matched an antenna is. If I have going in and here's an out and I have a junction right here, standing wave ratio is a measure of how much energy is coming back. So I have a little bit going out. This again is the larger of the impedance divided by the smaller impedance.
So this may be off topic. You can tell me later if it doesn't apply to now. Somebody was trying to explain to me that because of where I am and putting out that you can wind antenna line like almost like a spider web, like in multiple circles to make an antenna because you need the length on it.
I don't know, what kind of antenna are we talking? I mean, if you're talking like do this with it. Okay.
I got the picture of concentric circles was what I got the picture.
I'm not sure about that, but we'll get to that in a sec. Okay, so let's say I have a feed line that's 50 ohms and a match of 200 ohms here. Larger impedance divided by the smaller is 200 divided by 50 is 4:1 SWR. 4:1 is a mismatch. It will potentially damage your transmitter. 2:1 is okay. 1:1 is perfect. Most radios, because this will actually damage the transmitter, will sense what the standing wave ratio is, or SWR, and they will intentionally reduce the transmitter power to keep from destroying itself. So sometimes that can take you a little bit by surprise. You typically don't want to ever have a mismatch like this. If you do have a mismatch like that, it usually indicates that there's some kind of severe problem out there. The other thing is, let's say that I have a piece of cable that is old and decrepit, right? How did it get old and decrepit? I left it out in the rain. Well, if I left it out in the rain, what did it get filled with?
Water.
Okay, so what happened to the copper when it got wet?
Oxidized.
It oxidized. It got corroded. Okay, essentially, yeah, it rusted. So what'll end up happening if your cable gets wet is that your SWR will go crazy often. What'll happen is also that you get a lot of loss in this cable. You may actually see that it's not looking so bad, But let's say that you lose 90% of your power in that cable.
This is because the cable's damaged. Is that why?
Yeah, because the cable's physically damaged. How much of your power is going to come back if you lose 90% of it in the first place before it even gets out? You're going to have almost nothing coming back. That cable might actually look kind of okay because you're trying to figure out what your reflected power is, and most of it's disappearing anyway. Well, you don't really know how much of it's coming back. Like, what if you were to transmit your transmitter into this? What is that? Let's say that's a 50 ohm resistor. That's also known as a dummy load. How much of your signal makes it out into the world?
Well,
Nothing. Virtually nothing. Right? Is it a good match?
no.
Oh yeah, it's a perfect match. You have 50 ohm cable and a 50 ohm non-inductive wire wound resistor. That's a perfect match. All your power goes somewhere. So how much of it ever comes back?
Nothing.
0. That's a perfect one-to-one SWR. But how much of it actually goes out into the world as RF?
It goes out as heat.
That's right. It goes out as heat instead of RF. So there's a very subtle difference between good SWR and a decent antenna that actually works. So,
is a dummy load what you use when you're working on your radio itself?
yeah, if you're trying to do RF testing without putting out a signal, you want to see if it's actually working. You can transmit into a dummy load. You can run a kilowatt into a dummy load, and it just gets hot. So I think that's probably enough for the day. If anybody wants to stick around and just say hi and say who they are, congratulations, you've made it through the first day. I'm happy to do that for like another 15 minutes. So would anyone like to start if you're not in a huge hurry to leave?
Yeah,
I'm
Him.
Like how you ended up here and what you want to do, and how you ended up here really.
Yeah, so I'm Ben Sadler.
Neighbor of mine. Oh, go ahead.
Okay. Anyway, my name is Ben Sadler. I'm an IT guy by trade, but most of my life has been screwing around art somewhere or another. Was one of the youngest operations managers for Clear Channel back in the day. Right out of college, I ran WPA 1170, which is a 50,000 watt AM station. Pretty cool. I was just the operations, but I did everything I could to kind of watch what the engineer was doing. He was kind of a miserable son of a bitch, and he didn't like to share a lot of information. But I paid a good bit of attention to him back in the day. These days, a lot of what I'm doing is whether it's just fighting with Comcast to get their signals, in a decent shape for my internet at work, or a lot of the stuff, we use ARPANET type of technology at work, and a lot of stuff to go to coax with signals. But I guess most recently I've been playing with Meshtastic and just building out a wireless mesh network here and learning a lot about antennas and stuff like that. So I've been having a lot of fun with that. This ham license is something I wanted to do for a long time, just never spent any time to really do it. So,
And where are you?
really West Virginia.
West Virginia. Where?
Wheeling, Northern Panhandle, right up between.
I know where it is.
WWVA, yeah, that's where it all kind of started for me.
All right, who else? Who wants to go?
So I'm sort of on the opposite end of the spectrum. My name's Eric, and a neighbor of mine is big into ham radio, and his wife sent me an email to link to this class, and I'm just curious. So I know nothing about this other than what you've taught us today, and have no background in electronics. So it's been interesting.
Who's your neighbor?
His name's Robert, and he's in Eugene.
Robert what?
I don't know his call sign. I'm trying to remember his last name. I know most.
Where do you live?
Eugene, Oregon.
No, I know. I'm in Eugene. Where do you live?
Oh, he's over on University Avenue.
Oh, that's Robert Albano, K7RNA.
That's correct, Albano. Yeah.
Robert and Kathleen. Yeah, they're friends of mine.
That's right. Yeah, good people. All right.
Have you been totally overwhelmed so far?
Pretty well. You lost me a little bit in the middle. Came
Okay,
back a little bit. We'll see how it goes tomorrow.
cool.
Yeah. But I've got time to study before a test.
Yes. All right, who else?
Hi. My name is Russell. I am in high school and I'm in my aviation academy at my high school. And both my parents are in radio, both my parents are in IT as well. And I have a little bit of knowledge in this, but I'm kind of going into this blind. But this would really help me with my goal to become a private pilot
Yep.
because there's an entire section that I'm going over next quarter about radio and frequencies, and both my parents have you know uh been in radio. My dad has his radio license. He is we're in Boca Raton, Florida.
Which is in Palm Beach County.
So so how old are you?
I'm
What grade?
16. I'm
So
in 10th grade.
so planning on going to college?
Yeah,
So you know about the scholarship programs, right?
yeah.
You know all about the scholarship programs?
No.
I know about the scholarship programs for the college that I'm trying to go to.
No, the ARRL scholarships.
No, I don't.
Okay, well, see, that means that somebody's not doing their job. So
Just look.
somebody's not doing their job. So this right here, I'm going to share this right here. Why isn't it loading? There we go. Okay, see this ARRL scholarship program? ARRL Foundation
Yeah.
Scholarship Program? You've not seen this before.
No, I have not seen this before.
Did you say your parents are both hams?
My dad is.
Dad, shame on you. This is
it's terrible, isn't it?
This is the best reason for kids to get licensed, other than the career stuff.
I mean, I want to be.
I probably should have mentioned something about this a while ago.
My daughter has her extra, and when she was 18, she got a scholarship through ARRL. When she was 19, she got a scholarship through ARRL. When she was 20, she got a scholarship through ARRL, and when she was 21, she got a scholarship through ARRL. They have $800,000 to give away in the form of about 170 scholarships or something, 150 scholarships, and you have to have a license in order to apply. The higher the license class you have, and the more active you are, the more likely you are to get a decent. I mean, you can get up to $25,000.
That's great.
Yeah.
So that would probably help me
Yeah,
with my goal as well to join the military.
Over a period of 4 years, and my daughter, I proudly say, she got $60,000 in scholarships just for doing ham radio.
Good for her.
Wow.
So
There's a set of 16-year-olds that better be listening to this.
I know.
Yeah,
Yeah.
hear this? Get moving.
Yeah, I know, and I am. I
hear you.
I work with high school I work with high school students. I work with college students, and I, say, you know what? Get those applications done. It's not that hard, but and the money. Typically, I think they said last year, 70% of applicants got a scholarship. Like not 7 or 17, 70%. It's significant. So
I'll go next. I think it's a good time. My name is Gary Manus. I'm from the Rochester, New York area, and I'm a public school official. So I'm really glad to, Russell, you're making me very proud to be in education. So that's wonderful. I've always wanted to get into ham radio, and so my workout instructor is a employee at the emergency management department in our county, and she told me about this course. So that's why I'm here today, and I'm really enjoying it. We've got looks like people from all over. I'm also watching the show Pluribus right now on Apple TV, and
yeah, but we could go on for years about
a
that.
lot of the things you talked about today. I'm envisioning that signal that came to Earth. So, all right. Well, nice to meet everybody.
Can you see what I have on the screen right now?
The scholarship application.
No. The other thing that I just put on the screen.
Still scholarship. Oh, Teachers Institute for Wireless.
Yeah, that one's for teachers.
That's for teachers.
Oh no, I didn't see it. Okay,
that's for educators, and you don't
okay,
even.
Thank you.
And that is open to it's taught out of numerous different places in the United States, and that is designed for educators at all levels who want to teach using ham radio in their classrooms.
Oh, thank you. All right, I'll stop talking. Who would like to go next?
Let me do this honor then.
Yeah, you need to go to sleep, man. Actually,
yeah,
no. You need to
1 o'clock now.
You need to get on 160. 160 should just be really good right now.
It should be, but I don't have the antenna for that monster. So 80 is the best I can do. Well, my name is Tomislav. I'm from Croatia, aircraft engineer. I just got into this ham business a couple of months ago because I broke both of my arms and I didn't have any other thing to do.
Oh, before I forget, I'm going to stop recording.